Okay, on the welcome everyone. Can you hear us from outside? Please give some feedback.
Now I can, yes.
Okay, excellent. At least one guy we have. So okay, so we are here in the Wigner GPU Laboratories GPU Day, for which we are now celebrating the 10th anniversary of this event, which started a long time ago. And I just would like to say a few words on this event because some of you are newcomers. So just to highlight what we are here, why we are here, and what we have done so far. So the Wigner GPU Laboratory is part of the Wigner Institute. It's a special unit which dedicated to join the computing, the scientists, and sometimes the industrial fields. So here on the slide you can see that, what kind of topics we used to have, and of course if you can go to our web page. So we formed this unit within the Wigner Institute 10 years ago, and the main aim was to join together those who would like to speed up the scientific calculations and researches with parallel computational techniques. At the time, the GPU was the most trivial tool for this one. Today, there are many others like FPGAs or even quantum computers. So these things all together form this unit, and this unit is dedicated to join people who are expert in programming, in parallel computing, and would like to solve certain physical or non-physical problems. Here you can see the brief history. So the original idea came in 2005-2008, and when I returned from the US, we decided to form this group. The first two guests or former students of mine was Máté Nagyegri and Daniel Verényi, who pushed me to form this unit in the Wigner. And of course, since we are coming from the high energy physics and gravitational fields, so we decided to dedicate this direction. But later we had many other topics, and starting from 2010, so just 1 year after the start of the GPU laboratory, we figured out that it would be nice to advertise ourselves and to share the ideas with others, and this is why we started the GPU Day event. And from 2016, we also started an educational part, these lectures on modern computing in science series. And that was the same day when we opened a kind of fellowship to the general audience or general public to sign up with projects for the GPU laboratory to join us from outside, and maybe we can continue later, and this was very fruitful. Here you see the stuff at the moment, so you cannot see, but you will see during the days, Balázs Kacskovics, Balázs Szigeti, and Gábor Bíró, and myself, who are supporting the online event and the real GPU laboratory. Here you see the many logos of the academic and industrial partners during the last 10 years. And finally, you can see some results in numbers. So far we had 6 educational lectures on modern computing in science. This is the 10th GPU Day. You see since 2015 we have statistics. The first light blue is for the academic partner, the second is for the industrial, and the third part are the students. So as you see, we have about 80 or around 120 people yearly joining us on these events. So far during the 10 years, we had 25 fellowships, 14 is already finished and resulted in a nice publication, and we have 11 running projects from many fields. We had 23 more than 23 industrial and academic partners, as you could see the logos in the previous slide. And of course, we have more than 25 scientific publications and the open available codes related in our activities. So I have to give some few words on our sponsors. Of course, the Wigner Institute, which is the main host, who is providing the computational facilities and on the Wigner's activity, Peter Domokos, the next speaker, will give a bright view. We have a joint industrial partner, the Lombic Limited, which we have a long-term contract with them on a very interesting project, and you will see some talk on this in a couple of minutes or a couple of hours. And this event was supported by also the Ericsson research, especially on the quantum computing side. So this is an era of mixing virtual and real things, and here you see an interesting pictures which I took from board Panda. So you see that these times we have virtual worlds and we have the real worlds, and sometimes in quantum computing or in artificial intelligence, these things can mix up. So as you see, Trump as giving this piece of paper, and you should think on this very funny sentence that lamps in video games use real electricity, which is true, actually. Okay, so if you want to have more information, of course, the gpuday.com is the main web page. We have also the Indico site where we will provide all the talks and everything. And of course, if you are interested on the activities of the laboratories, you can just go to gpu.wigner.edu website. And thank you very much. And now I'm giving the stage to Peter Domokos, who is the Vice General Director of the Wigner Institute, and he will give a little bit of overview of the local Wigner activities in general and the Hungarian quantum computing. So please speak.
Okay, so welcome everybody, and let me open this day officially from the part of the Wigner Research Center. And first thing to say is that I'm very happy to host this event, and I thank the organizers for keeping on organizing this event, which is a good occasion to assemble people, mainly physicists, but not only physicists, who are heavily interested in this large-scale computing. So this is, I think, a very good activity within the institute. So that early this year, beginning of this year, the Wigner Research Center had to define the focus area of research in which we feel we are the strongest and we want to develop further. And 5 such subfields have been defined. The order is not relevant here, but the first one is quantum optics and photonics-based quantum technologies. This was one of them. Then the second is fundamental interactions, new experimental technologies. Third one is structural study of new materials at the atomic scale. Fourth one is artificial intelligence, deep learning, and big data. And the fifth one is somewhat smaller, but there are a lot of researches here which are related to environment protection, things like this. So you can see that 2 of those subfields or focus area are connected to this GPU day. So directly connected is the 4th one, which is related to computation. But also the second one, which, as we learned from the previous introduction, the study of fundamental interactions is the field of physics which demands this high capacity of computation. And now it seems that the first line is quantum optics, quantum technology joins also this demand, or also this participation in the field of computation. So just a brief to set the scheme. So as you see, the horizontal line represents somehow that the physics, the various scales. So starting from the smallest scale, which is elementary particles, up to the largest scale, the largest large scale structure of universe. So the Wigner Research Center has activities all over this line, and so the very end, right end, represents gravitational wave research, for example. Interestingly, the Institute of Particle Physics, which is one part of the research center, represents the two extremes, the smallest and the largest structure. The other institute, the solid state physics research and optics, is more in the middle, somehow under the scale, which is closer to us, to the everyday life. So this is the atoms and the bulk material. Now you have to realize that quantum physics is something different. It's not on this line. It opens a new dimension to physics, because here it's not the object which is interesting, but the dynamics, the laws of motion, which changes and which takes place at all scale. So now there are also speculations that at the large scale, the matter at large scale, so the galactical scale, has manifestations of quantum effects. Now, of course, we start from somewhere from the middle, so our laboratory life, where we can realize quantum effects is connected to solid-state physics systems or atomic systems, atoms, molecules, electrons, ions, or quantum dots. But this is a different dimension which gives rise to completely new concepts. And such a concept is quantum information. Quantum information is a generalization of classical information in the sense that it has a basic unit, which is the bit, that is generalized to be a quantum. So rather than having two states, which is denoted by 0 and 1, now these two states of a bit is in the case of a quantum bit, these are two quantum states which can be in a superposition state. So this is the only addition, but this opens a completely new paradigm. And then this field of quantum information expands to the area of application where we normally encounter the concept of information classically. So there are quantum communication and quantum computing. So in both cases, we have a completely new area of research. How the Wigner is related to this research? So quantum physics at Wigner started long ago. Initially, this community featured only a few researchers, so 1 or 2 researchers and then students. So when we arrived at 2000 or somewhat later, a few years later, quantum physics research was conducted in 3-4 theoretical groups. A big change occurred in 2017 when in the frame of a national excellence program, the Wigner could embark on a new endeavor, namely experimental activity has been started here. So now, at the moment, there are 3 experimental groups on top of the 3-4 theory groups that run research in quantum physics. And now we enter again a new time, which is the time when a national laboratory for quantum information has been formed, and the Wigner is the leader of this consortial F4. What is this National Laboratory for Quantum Information? So let us define it in terms of the 3 strategic goals. So this gives a good picture of this initiative. So one, that we would like to create a quantum communication network in Hungary. So in fact, there will be a node at the Wigner Research Center and one at the Technical University, and these will be connected. So we can communicate quantum bit between these 2 partners. And the strategic impact of this, that we are going to be develop this capacity or ability, expertise to join a large-scale network. So there are projects under the European Union to create a European quantum internet, and Hungary will be able to join that network. The second is that we would like to develop hardware components for quantum computation. So Hungary is not a big country to be able to build a quantum computer, but we can aim at special quantum components which allow for quantum information processing, and we have to develop and maintain the necessary laboratory infrastructure and know-how to do that. And the third one is the quantum computation theory, and this is a very exciting field because there will be quantum computers that can be considered as large international infrastructures where one can have a remote access, but we need the background here. We need a group of experts that can compile on that computers, that can compile physics or whatever problems to run them on a quantum computer. A body of experts who knows what are the kind of problems that can be solved, so who are able to develop algorithms. So this is an important pillar of this national laboratory, to have these expertise or to form these expertise in the country. Okay, so just a few words about quantum experiments at Wigner. Here I highlighted two. There is an optically detected magnetic resonance. So this is the same device that you can find in medical diagnosis, so magnetic resonance investigation. The big difference that here you detected a single spin. You detect the signature, the signal of a single spin, nuclear spin. So this is why it is quantum. So it's a high spatial resolution ODMR spectrometer is running now at the institute, and nitrogen vacancy centers in diamond are investigated. The other one is, this is called a nitrogen vacancy center in a piece of nanocrystal. It's called an artificial atom because you have an ordered environment and there is one defect, but this defect is actually like complementary of something that you have an empty space and there is an atom. So it's called an artificial atom, and we are running experiments also with real atoms in an experimental setup that is referred to as the atom-photon interface. It's a cavity quantum electrodynamic system, and actually this is the laboratory activity I'm involved in, so that's my scientific interest is here. But one can say in general, though here I project the quantum states of a rubidium atom, but one can say in general that these quantum systems, whether artificial atoms or atoms, have well-defined discrete states, quantum states. Any two of them can be selected as a 0 and 1 of a quantum bit. And this is a laboratory for us. So you can imagine a small atom as a whole laboratory with a very rich life inside. So we have a hyperfine structure that can be operated or that can be driven at microwave frequency. We have optical transitions that we can address by lasers, and also the further means that we can apply to manipulate an object which you cannot keep in your hand, is magnetic field. So we can use the Zeeman effect to manipulate these states. So this is the whole word. And the aim of the experiments, or the aim of quantum manipulation, is to perform transitions, realize states, measure states in a controlled way. And then we can use these pieces as Lego blocks to build something complicated. So this is the elementary block of a quantum engine. And our aim specifically is to be able to perform all these manipulations, to have a perfect control on atoms. So for example, there is a protocol how one can convert a photon into an atomic state, or an atomic state into a photon. It's a this is just an illustration of such a scheme that with a time-dependent path, one can extract a photon and one single photon from an atom on demand. So it's a single photon source. With the reverse process, one can realize a complete communication toolbox between photons and atoms. And this is our goal as well. This is why we call our experiment atom-photon interface. So we can generate quantum bits, where the quantum bits are represented in this case, the polarization of photons. And then this quantum bit, the photon, which is the so-called carrier quantum bit, because it is used to reach large distances. And then this quantum bit encoded in the photon can be read out in another cavity QED system, so which is the quantum memory. So this gives you a flavor about this experimental development or the objectives. So now we have to realize physically those procedures, those processes which are trivial in the classical world. In the quantum world, to copy the state of one bit to another one is a very difficult task because we have to keep quantum coherence. Okay, so as I said, quantum memory is, for example, the interaction of two quantum bits, when we are talking about two photons, is very weak. So photons do not interact. This is why they are good for long distance carriers, but they are not good to perform gates because photons don't interact. But if we copy the state of a photon on an atom, then atoms do interact, so we can realize gate operations mediated by atoms. So the other long-term goal, which is linked to this level scheme I showed, that atoms are good interfaces between microwave radiation and optics. So if you want to bridge the two realms of quantum information computing, which takes place typically in the microwave regime, and quantum communication, which uses infrared photons. So if you want to connect these two in a quantum coherent way, you need an object that is resonant with both, and an atom is like this. So our other long-term goal is to build an interface between microwave and optical radiation. So these are the exciting prospects and a lot of work devoted to it, which is waiting for us. And for today, I wish you a good workshop and good platform to communicate. So thank you for your attention.
Thank you very much, Peter, and for this nice introduction. We have a couple of minutes for questions, if any, from, let me ask first from outside. No one from outside, inside. Okay, maybe I have a question in relation to, so what is the, let's say, the short range and the long range of this project, what was formed? So, I mean, I think you have a kind of work plan for the future. So what is the time scale of the short range and the long range of this activity?
So the National Laboratory has a program for 4 years. So the goals and objectives are defined to 4 years, and these strategy goals that I mentioned are included, so we have to reach them in 4 years. Concerning our experimental activity, in 4 years, we have the ambition to build, so we already have an experiment which is running close to the quantum regime, and we want to break now this threshold to go into the quantum level. So that's, and this we can achieve in 4 years.
Okay, so then I wish you excellent, successful 4 years. Okay, any other questions? Okay, so then let's thank Peter and maybe I can ask József Kadlecsik, who is the director of the Wigner Data Center or local host, and maybe later you will see us. You will see later us as we are sitting here, as we are closing the on-site presentation, and this will be the last item. And we have a long-range joint work with József and his group, because as the Wigner data center formed, we were not only involved in the proposal writing in the very beginning, but we had long range joint works with local computing facilities and both on hardware and software wise. And now I to give the word to József to make his presentation on behalf of the Wigner Data Center, presenting the local facilities and the future things here at the Wigner Data Center.
So, hello everyone.
Yeah, so we have some technical difficulties because we want to share the slides, and the slides disappeared from the server for a certain change. So please give us a few minutes to set up everything. Okay.
Megjött?
Nekem küldtek, vagy a GPU-ra foglaltam, azt én nem kapom. Nálad megvan?
Nem tudom, mindjárt.
Hát nincs fent a fájl. Ott van most.
Van? Kellemesebbet vagy?
Már meg lesz mindjárt. Okay, maybe you can start with the introduction and then
Sorry for the technical difficulties. It's a quite strange situation when we half online and find half leaving the conference. I'm the head of the Wigner data center here, so in a few slides I will introduce you the Wigner data center and also our cloud services and what kind of hardware and software makes possible to use these resources. And in the second part of our presentation, my colleague György Mező will talk about actually GPU usage in some case studies, how actually physicists and other scientists use our resources here in their research. So the Wigner data center belongs to the Wigner Research Center for Physics, and we have several services to scientists and other organizations too. First is the data center service and then infrastructural service. And we have an ongoing project in which we try to extend and give in the future platform service as well. Till the last year, we hosted the LHC Tier 1 data center for CERN. We then moved back to Union CERN itself. What actually data center service means? Of course, it is rack space, but rack space is a fully equipped environment, including PDUs in the racks and backup UPSs, huge aggregators. We have 2 independent power lines to the Hungarian power grid, just to make sure that the power is flowing every time, full day and time. Cooling, just a simple word, but actually it means a lot of equipment too. Devices, piping, monitoring everything. We have high precision fire alarm system without any fire extinguisher, just to make sure nothing bad happens with the devices. Of course, the environment is monitored, which including not only the temperature, but the pressure, voltage, liquid dropping, even closing and opening the doors. The operational staff is here 7 days a week and 24 hours a day. In daytime it means engineering and maintenance, and at night it means duty. And the whole area has a strong physical security, so which means cards, physical cards and pins, so it's a 2-factor authentication, which give access even to the staff to the areas which are needed for them to perform their job. And it's only that. Right, our data center as a services customers, first is government organizations. They hire huge computer rooms, also research groups like ADCF, and the ARTH Cloud itself also as a DCS customer. The infrastructure service at the moment means actually the ARTH Cloud, which started at 2016 as a scientific research cloud service and was funded by the Hungarian Academy of Sciences. This cloud service aims to give access to resources to any Hungarian research institute members, so anyone can come up with a project, submit it, and then a small active committee decides whether we can give access to resources and whether the 2 physical places, which one will serve best this given project. So we have 2 physical size places for this cloud. One is for the Institute for Computer Science and Control, Staki, and the second one here at the data center. The hardware currently we have combined at Staki and Wigner is more than 1,000 virtual CPUs, more than 3 terabyte memory, almost half petabyte storage, and 12 GPU cards. In the data center, we have a tape library as well, and we are working on to extend the cloud software and possibilities just for any cloud project to use this tape library as a long time archiving possibility. Our network was completely reworked last year. It's pioneer technology. It is capable of 100 gigabit per second bandwidth. At the moment, we use 10 gigabit, and our project aims to use this capability fully and to give 100 gigabit per second connection between every nodes and storage in the network. We use Ceph as a file system, OpenStack as a cloud software, and OpenVPN gives access to the scientists the given resource they were given in our cloud software. So that's it, and the next part will be actually GPUs and the case studies by you as well. Thank you.
Okay. I don't know how you would like to make it. So shall we ask questions now to your part, or maybe at the end?
At the end.
At the end. Okay. So now we are switching to the Mesel with the second part.
Hello to everyone. I am service developer in the Wigner data center.
Have you uploaded? Okay, so please.
Excuse me, I restart my computer to connect
Okay.
the projector.
Maybe I take the moment for the later speakers, so please send us your talk and try your connections with us for the next first coming talks. So is it coming now?
No.
Nálam megvan. Ez arra most ezt mit tudom csinálni, azt ki tudjuk küldeni? Abból baj lesz, azt
Hát tudom mutatni neki ezen a képen.
de akkor nem látszik ott.
Minden látszik. Hát, hogy megmesélem, és bemutatni neki, hogy van egy ilyen.
Okay, so again we had a slight technical. Most when you have your no, we don't have the. Okay, a few seconds.
So first, I show you the existing GPU infrastructure in the ERKH cloud. And next, I selected some projects that we made together, research institute, universities, and industrial company. And I show you the results and many videos of this project. But I analyzed this project from the data center perspective, the service perspective, and at the end, I show you the planned expansion of the ERKH cloud infrastructure. The ERKH cloud has two sides and two branches. One is the Wigner data center, the other the Institute for Computer Science and Control. This makes the possibility to make two strategies. For example, the GPU computation. The Wigner data center choose to one server with 4 GPU cards. The other side choose the 3 server and also 4 GPU cards. In the Wigner data center, it is possible to experiment how to connect together with the help of the NVIDIA link this 4 card, and the other side, other hand, seamlessly integrated the GPU servers in the OpenStack cloud, so the user can use just try to connect the OpenStack cloud. But in the Wigner data center, we service the user and project based. We discuss every project needs and try to make the best available techniques to solve the problems. Okay, I talk about this project. You see there are projects from research institute, namely, for example, the Institute of Experimental Medicine, Konkoly Observatory, universities, the Ötvös University, and also the Technical University of Budapest, and the company who is the distributor, the ANSYS program, the Econ Engineering Ltd. Okay, first, one project from the Konkoly Observatory. The user or the project director was expert to write C and C++ code for GPU cards. And also, Zsolt Regali has astrophysical simulation laboratory that heavily use GPU cards. But you can imagine when one student arrived in the laboratory and starting new tools. So to install every time new tools, it is difficult, much more simple to use the Docker technology. But with the Docker, there is many problems, security problems, and also in that case, how to remotely render the simulation. So in this project, we solved some of these problems, and the result was that the Konkoly GPU laboratory is using Docker technology on every server. The Konkoly Observatory has also a 3D projector system, and we made animation for the Mars surface, and it was an interesting experience to see that the blender able to use every NVIDIA card together, and other thing that the CPU is also used heavily. So when someone builds a GPU server, it has to decide the balance, the equilibrium between the CPU capability and the GPU capability. Okay, at the Concordia Observatory, starting and machine learning groups. In this day, many research centers interested in machine learning is a fashion today, and also very useful tools for data discoveries. So there are many groups that start using these techniques, and in that case, it is best to pre-install programs for these groups and help use these groups, these techniques. For example, my experience is that Jupyter Hub is very useful to service many users, and much more advanced user can use also the OpenShift that cover all the development phase for a project. There was also expert user with from the Witwatersrand University. They built a system that can able to decide that some patient tissue is have cancer or not. In that case, it was interesting that that when starting the project, the resource is not so high, but if we try to better allocate the resources, it is important to make, for example, burst infrastructure with orchestrating, with the help of orchestrating. So the Lanzo expert user can use the resources, and in the same time, the expert user sometimes use all the available resources. And other type of users of the clones, for example, in the field of life sciences, has sometimes concrete programs. In that case, the support just to install these programs and make comfortable the data upload and download, and to plan the resource uses. Okay, some engineering project. It was interesting to see the idea in the case of the new bridge of Comaron, that the technical university tried to build a digital twin model. This means that the model mirrors the physical reality, and they plan the operation of the bridge based on the calculation of this digital model. So we install the ANSYS program on the GPU server and start to build up the building blocks of this big model. But in reality, this project needs, I think, a separate, dedicated infrastructure to make, to reach the aim of this project. After we connected with the distributor of ANSYS program and made benchmarks. We benchmarking the ANSYS, how to scale up the different finite element analysis programs with the help of the GPU, and also benchmarking the cloud on servers and make comparison with the other high performance computing cloud. So there are many types of clouds, and it is a good question, for example, which cloud is the best for the user. At the end, the planned expansion of GPU capacities and services. In the Wigner data center, we plan to purchase 4 GPU servers with the newest NVIDIA cards, and the Institute for Computer Science and Control, they are planning to purchase 8 GPU servers with also NVIDIA cards, and the 2 entity planning to not just make infrastructure as a service, but platform as a service, so to build many orchestrated services. For example, to easily start in Kubernetes cluster, Jupyter Hub, and many other things. We hope that this happens at July. Thanks for your attention.
Thank you very much, Lee. So now we can have questions. Maybe you can also get the microphone. So both talks very quickly. As far as I know, we have one question from outside. So, is the LK Cloud event tomorrow at 1 p.m. open for external participants?
External participants, which means the external participants that university or just some company.
This could be an Ericsson question, I think.
Ericsson, okay.
Is this open? Tomorrow open 1 p.m. meeting on the ELKH Cloud event. Is it open for everyone or not? Your meeting tomorrow.
Tomorrow? Yes, it's open for everyone, yes.
So any industry and academic programs
attend. Yes, it's online meeting. Yes, it's open for everyone. Yeah.
Okay. Further, sorry?
Free of charge.
Okay. Further questions from outside? Local questions? Okay, so I think we are a little bit of late, so let's thank Julie again, and he will be here also for some time. Thank you very much. And now we are switching to the full virtual direction, and may I ask for the next speaker, who are also sharing the presentations. So this will be our industrial partner from the Lombik Limited, Zoltán Lehoczky, and our colleagues Ernő Dávid from the Wigner Institute. So Zoltán, can you hear us?
Yes. Hello, everyone. Can you hear me too?
Excellent. Thank you. And just one practical thing. So now we are switching to a fully online way. So we will turn on the video to see us, and then please you can start your presentation. And one more thing, that all the other speakers of the afternoon, please send us the talks in order to upload to the Indico web page. Thanks. So, Zoltán, please.
All right, thank you. Well, it's great to be here again. I was actually there on that very first GPU day in 2010, so very nice that it's been, well, 10 years already. It's crazy. Well, I hope that next year we'll be there in person again, but, well, we have to do just online now. What I would like to talk about with Ernő from Wigner will be our Heslier project and how we made it support the latest Xilinx Alvo data center accelerator cards. What's the Heslier project? You will learn about in a minute. But just a bit of introduction before that. I'm from a company called Lombic Technologies, and in day-to-day we are actually doing web development mostly with an open source content management system called Orchard. Orchard is a .NET based system, and we are serving customers all around the world with it, mostly in North America. And we are worldwide market leaders in that, working with companies like Microsoft itself, or the event organizer Fortune 500 company Live Nation, or institutes like the Smithsonian Institution. And we are glad to be a longtime partner of Wigner. And when we are not doing some web developments, then we are doing some research and development, like our Heslier project. First, in this talk, in the first half, I will talk about Heslier and the problem we are solving with it in general. And then in the second half, Ernő will talk about all the details behind the scenes, how the hardware engineering part happened here, because there will be some hardware engineering too. And a third colleague of ours, David El-Saig, also took part in this project, but he won't present today. But first, talk about you. Well, let's suppose that you're doing some number crunching, all right? And by number crunching, I mean something like AI, machine learning, or something with imaging, the image and video processing, or even computer vision. Or perhaps you are doing algorithmic trading on the stock market, like high frequency trading. Or you have some kind of application where there's a lot of data compression. Or, well, fitting the event, maybe you are doing some kind of scientific computations, or specifically working with physics problems. Well, then you have some kind of algorithm, and probably you want to make it faster. So what can you do to make it faster? Of course, you can profile the code and optimize it. That would be the first simple step. Nothing else needed for it. Naturally, you can parallelize it. So make it aware that there are multiple cores and a CPU nowadays, of course, so make it run in parallel. And obviously, you can also use faster hardware or more hardware. Now, let's pretend that you have done all of these already. What else can you do? Well, we are at GPU Day, so of course you can do some heterogeneous computing approaches. Specifically, you can use compute accelerators like GPUs or FPGAs. Well, let's talk about that last part, FPGAs, a bit more, because that's interesting, I think. Well, what are FPGAs? Probably a few of you here heard of FPGAs before. If not, a very quick introduction. FPGAs are, or field programmable gate arrays, are pretty much chips that can behave like any other computer chip, within limitations, of course. So that means that they can be dynamically rewired, or as we say, they can be reconfigured. Now, if you have used Bing, as you can say, you Google something on Bing, then, for example, you have used FPGAs before already, because Bing is accelerated by FPGAs for a couple of years. Or if you have utilized the Azure cloud computing provider, by Microsoft, then you have already used FPGAs too, because FPGAs are used there for smart network interface cards. Or if you had used some medical imaging devices like X-ray machines, MRI machines, do sometimes also have FPGAs in them for compute acceleration, just as sometimes even household appliances like routers or self-driving vehicles. The thing with FPGAs, though, is that it is a piece of logic hardware. You are creating a piece of logic hardware, so you have to be a hardware engineer to utilize them. And why would you do that? Why would you use an FPGA? Well, the reason is that they have some unique merits when it comes to compute acceleration. So let's compare different computing devices on a few factors. So let's talk about CPUs, GPUs, and FPGAs. Just a very, very quick, very rough overview, totally non-scientific, just to give you a basic idea here. And let's talk about parallelism first. So how many things can you compute at the same time on these devices? The chart on the left. Now, with CPUs, the bar in blue, the level of parallelism is on the lower end here. So, you know, in a consumer CPU, you have maybe 4, 8 cores, in 16 nowadays for the high-end ones. For server CPUs, you have 32, 64 cores, but that's about it. With GPUs, they are on the other extreme. GPUs have thousands of cores. Of course, those are different cores, but still, you can run thousands of threads there. And with FPGAs, it's kind of in between here. Although FPGAs don't really have cores, however, that's not entirely true nowadays. But still, the degree of parallelism you can achieve on an FPGA is roughly in the order of magnitude of hundreds. Of course, all of this greatly depends on the specific chips, specific devices, and the specific applications. But this is just to give you a rough idea. Now, let's also talk about the complexity of programs you can run on these devices. So, with CPUs, of course, they win here because if it's a piece of software, you can somehow run it on a CPU, possibly with emulation, but still. Now, with the GPUs, it's the other extreme again, but the lower end here, because GPUs are much more limited computing devices. And FPGAs are kind of in between again, although you don't really run a program on an FPGA usually. Still, the complexity of the algorithms you can achieve or implement on an FPGA are, I would say, somewhere in between. However, power efficiency is where FPGAs really shine. I would say that CPUs and GPUs are roughly on the same level here, again, greatly depending on a lot of factors, but FPGAs are really power efficient. And the reason is that with an FPGA, you are not writing a software for a processor, but rather you are kind of creating a processor for your software. You are implementing an architecture specifically for your problem. And that means that it can be very power efficient. And there is no instruction set to handle. There is no operating system to run, no other programs to execute. So an FPGA just computes what you need to be computed. But there is a big downside, and that is that it's very hard to develop with FPGAs, usually. Because programming CPUs is easy enough. GPUs a bit harder, but still it's programming. But FPGA development is something completely different. It's not software development, but it's hardware development. So you have to think in terms of you have to think in very low-level terms like gates and clock cycles. It's completely different than software development. So that sounds good. FPGAs are probably useful, but what is Hasslier then? Well, Hasslier is a tool that takes a computer program and turns it into an FPGA logic. for all the initiated here, we could also say that it's a software developer aimed high-level synthesis tool. We could also say that Hathier takes a computer program and turns it into a computer chip. Or we could also say that we take some logic which is expressed as software form and turn it into another piece of logic which is expressed as hardware form. And not just any software, actually, we are talking about the .NET platform. Probably most of you here have worked with the C++ or Python before. That is also available, although the primary languages of .NET are C# and Visual Basic. But you can also use functional languages like F# or scripting languages like PHP or JavaScript even. So all in all, what we are aiming for here is getting the computing benefits of FPGAs for all software developers. So FPGAs and Hathier is not a silver bullet, but if we are talking about compute bound, so CPU bound algorithms, which can be massively parallelized, then you can get a very substantial performance increase with FPGAs and with Hathier. And at the same time, you get a higher power efficiency. So you can compute more things with less amount of power. And if you are thinking about algorithms that run on dozens or hundreds of servers, usually the power efficiency gain can be a huge cost saver. In data centers, as I'm sure the previous colleagues here can confirm, power usage is one of the primary costs, power and cooling. But with Hathier, the whole thing is still software development as usual, so no hardware engineering knowledge required here. And we actually have some quite nice results already. These are some preliminary benchmarks for the Alveo cards, so we expect these to be much, much better still. We have tested a couple of algorithms which are available open source in the Hathier SDK, and all of the results and the details how we got there are also available online, but just a quick recap here. Usually we see some kind of performance advantage to comparable CPUs. Even on the small and cheap Nexus boards, you get a performance advantage compared to a comparable CPU, and you get a huge power consumption advantage as well. The orders of magnitude better power consumption for the same computation. And with the Alveo cards that Erne will talk about in detail, you also get multiple times of the performance increase as well as the power consumption decrease. But enough talk for now. Let's see a demo. And now I switch over to Visual Studio, which is the development environment that .NET developers usually use. But you can use any development environment. I will just show you a little bit of code. If you are not a developer, not very, it will be super simple. What we are looking at here is an algorithm called, well, parallel algorithm. And as you might have guessed from the name, this is a highly parallelized algorithm. This is just a synthetic example of the classes of algorithms that are suited to be accelerated by Hathier. So this is not a real-life example, just to give you a rough idea what's efficient here. And what this algorithm does, the core of the logic is here. It does a bit of conditional logic to simulate something like that, which is executed 10 million times. And this whole thing is actually executed in multiple tasks. You can think of tasks, this is a .NET notion here. You can think of tasks as threads for now. So basically, we are starting threads here. And we are starting this many threads. And this many here, oops, sorry, I misclicked. And this many threads are 260 threads. So we are starting 260 threads, which will be executed all in parallel. Now, why are we doing this? Why 260 exactly? Because that many will fit on this FPGA board that I have here for the demonstration. This is a Nexus board. The type of the board is called Nexus. It uses a Xilinx FPGA. And why I'm talking about the FPGA, because when we convert this whole algorithm into a hardware implementation with Hasleur, then on the FPGA, we will get 260 little cores. So for each of these threads, we will have a parallel execution unit there. We will get an actual hardware level parallelism of 260. Or we could also say that we are dynamically generating a CPU or a processor for your algorithm that has 260 cores. Whereas when I execute the whole thing on this PC that I'm running this from, these 260 threads will, of course, run still on these couple of cores of the CPU. In the case of my CPU, there will be 4 physical cores and 8 logical cores. So the level of parallelism we will get is much, much, much smaller. Actually, the .NET thread pool will take care of not to oversaturate the CPU, but still these 260 threads won't run at the same time on those just 8 cores. It will try to optimize it for performance, but of course the level of parallelism will be very, very low compared to the FPGA. And now let's also run this. This is part of a small console application that I will now execute. The API of Hasleur is quite simple as well. And all of this is documented. All of this is up on GitHub, so you can check it out in detail. What happens now is that Hasleur generates the hardware implementation for the FPGA. And once that is done, it will start communicating with this device I have just shown you here. First, it will execute this as software, just so we can have a comparison. And then it will execute it as hardware. So let's see. On the CPU, this took about 3 seconds, give or take. Although this is a very rough measurement because my computer is doing a lot of other things, etc. So this can be smaller, but just to give you an idea. And on the hardware, it took about 300 milliseconds. If we are talking about just the hardware execution, or about 400 milliseconds if we also take the relatively slow communication round trip into account. So that means that the FPGA was about 6 times faster, even on this cheap low-end boards here. And actually, if you take a look, on the hardware, it took exactly the same amount of time each 3 times, down to the 10,000th millisecond. And this is, again, because we are running bare metal. There are no noisy neighbors, no other software to run, no operating system. It just computes what you need to be computed. That was a quick introduction. And now I will hand over to Ernő, so he can also talk about the details of our Alvo implementation and Alvo support specifically. So, Ernő, up to you.
Switch to Ernő. Thank you very much. Now we can switch to Ernő. And Ernő, can you hear us?
Hello, good morning. Can you hear me?
No, perfectly, please.
Let's share my screen. Is it visible?
Not yet.
Now?
We have.
Is it visible?
Now it's visible.
Okay. Good morning. I am Ernő Dávid from Wigner Research Center for Physics, where I work as an FPGA developer. Zoltán already said few points why is a high-level synthesis tool like a Hasleur can be interesting for the software developers. Now I want to start with another one, why Haskell can be interesting for the FPGA developers too. In Wigner, in the data acquisition laboratory, we develop a hardware and firmware for physical experiments, like, for example, Alice experiment in CERN. And we found FPGAs quite useful for these tasks. As you can see on the left side, in the 80s, the physicists and the electrical engineers built digital designs from discrete components soldered to a PCB. But nowadays, with FPGAs, it's much easier. You put one or more FPGA in the middle of the board with few necessary external components around, and you can implement a wide range of digital designs without any soldering. Let's have a look inside the FPGA. On very basic level, we have small logic blocks with flip-flops to store the binary values, and with lookup tables to implement combinational logics. These logic blocks organized in 2D arrays with a routing fabric between them, which allows to make a connection between any two logic blocks. A very important concept here that every flip-flop can be updated in every clock cycle. This is the biggest difference between the software executed by the CPU step by step versus a digital design. On CPU side, the instruction sits in the memory until one of the CPU cores executes them. But in the FPGA, you can utilize all of the flip-flops, millions of them, for your task if you find a way. This basic layout remains same in the last 30 years. But with each new generation, we get more and more resources, like the Xilinx Alero data center accelerator cards. Our main target card is the U250, and this will be present in the Azure. It contains 1.7 million lookup tables, which means in this case 3.4 million flip-flops. And for some time, we have even more complex digital parts integrated in the fabric, like the flip-flops. For example, we have digital signal processor for faster arithmetics, internal memory blocks, gigabit transceivers for high-speed protocols like PCI Express and optical Ethernet, and memory controllers, and so on. You can see that we have Alveo cards with up to 64 gigabit DDR memory, or we have variants with 8 gigabit HBM2 memory with quite impressive memory bandwidth parameters. The Alveo cards connects to the CPU over Gen3 16-lane PCI bus, like the GPU cards. And there is even 2 QSFP connector on the board, so it can behave like a 100 gigabit Ethernet card also. In early days, in 80s and 90s, the developers were able to design the routing on paper and connect the few logic book by hand. Then later, the tool started to use schematics to capture the design, which is still usable today until certain complexity. The hardware description languages like VHDL and Verilog also appeared in 80s, but for a long time they were used only for simulation and verification for ASIC digital designs. But with time, the FPGA vendors adapted also for the synthesis. And currently, this is the most common way to implement digital designs in the FPGAs, especially when you're dealing with low-level protocols or with fast data acquisitions, when the exact timing is mandatory. But the increase in the FPGA resources allows us to move even more complex functionality into the FPGA, like why to send data to a powerful server for analysis when it can be implemented inside the FPGA in real time. The only problem that implementing a complex scientific calculation in VHDL on flip-flop levels is very slow and error-pruning process. it's like implementing a web content management system in CPU assembly language. So there is an increasing need and opportunity in the FPGA development for high-level synthesis tools like Hessler, where you can reuse an algorithm developed and tested in a high-level CPU language like C, C++, C#, inside the FPGA with ease. This is one of the reasons why we started to collaborate with Lombic in Hessler project 2 years ago. First, we started to implement the support for Microsoft Catapult platform, which was presented last year by Zoltan at this very same event. And now we have a working version for the Xilinx Alvo cards. Okay, let's go back to the software side. And let's play with the idea that to accelerate our .NET application with a Hessler generated core, VHDL core. Of course, this is just a theoretical exercise, since you will get a pre-built system as a Hessler user. Let's assume that you have a small standalone FPGA card sitting on your desk, and it's connected to the PC through USB or TCP/IP protocol. The basic operation of the Hessler acceleration that you send your input data from the .NET application to the FPGA card. On the FPGA card side, we need a so-called hardware framework around the Hessler generated core, which stores the data in the DDR memory, invokes the core, and when it's done, sends the results back to the .NET application. Actually, this is how the first Hessler version implemented, and which was Zoltan just demonstrated. Okay, let's move to the Xilinx Alvo card execution environment. Since we are at a GPU day, I am happy to inform you that Xilinx adopted the OpenCL API for their Alvo card development. Your .NET application communicates with the OpenCL API through the Hessler software parts. And on the FPGA side, the Xilinx provides the so-called shell, which manages the memory movement between the CPU memory and the onboard DDR memory, and the kernel invocation. Typically, the OpenCL kernel is written in OpenCL language, but since in this case, the target is an FPGA, the Xilinx tools allows us to provide the kernel source in the VHDL language, the generated core by the Hessler SDK. This is the so-called RTL register transfer level kernel option. During the development, we faced several challenging areas, and I want to mention a few of them. The first is the memory access. In the Hessler generated core, our internal memory bus is 32-bit wide, while the external memory bus can be between 32-bit and 1024-bit wide. Initially, we started a 32-bit external memory access, which resulted in rather poor performance. I will present some results on the next slide. Later, we implemented a small cache system built from flip-flops to speed up the memory read and write requests. And we are also playing with the idea to add the second level cache system built from internal FPGA memory blocks. We used our image processing algorithm sample to measure the impact of the cache system. This is our most memory intensive sample. We implemented different kernels with different AXI data bus width and cache width, and we tested the DDR memory and the HBM memory too. At first, we tested it in 32-bit mode, which means no cache, and found that the DDR memory only slower by 12% than the HBM memory. Actually, we hoped for much better performance with the HBM memory, but it seems that in this case, the single DDR memory channel versus single HBM memory channel nearly behaves same. But when we started to increase the exi data bus width and the cache width, we managed to gain significant speed up. With maximum AXI bus width, the speed up is between 7 and 8. Finally, we settled with the 512-bit because we found that 1024-bit causing kernel frequency drops in some test applications. Yeah, the second challenge, which I mentioned, the kernel frequency. To utilize the abundant resources in the FPGAs, we would like to extract the parallelism from our algorithm as much as it's possible. But this means that we have to distribute our input data to millions of flip-flops, and after the calculation, we have to collect them. And this means bigger and bigger combinational logics for multiplexing and demultiplexing the data. And bigger combinational logic means longer propagation delay, which means lower kernel frequency. Currently, our target frequency is 300 megahertz. And in certain cases, we observe a frequency drop above certain parallelization level. There are techniques to solve this, to inject flip-flops in the combinational logic network, to split them into smaller parts. This will produce a few clock cycle delay in the result, but the gain from the overall higher kernel frequency is much more important. Currently, we are investigating this approach. The last challenge which I want to mention is the build time. It is actually not a SLR issue, but Alveo card, or better to say a generic FPGA feature, FPGA development feature. Even the simplest design took 3 to 4 hours to build. The reason for this that the whole design is rebuilt every time when you change something, because usually you have to reconfigure the whole FPGA fabric to run a new design. It's like recompiling the whole operation system to run your application on the CPU. Of course, the existing FPGA configuration can be loaded immediately. There is a technique so-called partial reconfiguration, which is something like dynamic loadable libraries on the CPU, or like hot plug expansion slots on the memory, on the modern motherboard. Some area in the FPGA fabric can be prepared for dynamic replacement. In our case, this would be the kernel area. So if you change something in your .NET assembly, then you need just to rebuild the kernel part. This feature is already supported by the lower level Xilinx tools, but not in the Alveo card development flow. But there is a promise that this will be added in the future. While we are working on the Alveo card version to further improve, we are also looking for other areas where it would be also useful. Namely, we are thinking to develop support for the Xilinx Zinc family, wherein the FPGA fabric and ARM CPU is also integrated with capabilities even to run a Linux. This FPGA family already used on board of drones and satellites in aerospace industry, because it is very handy to run your higher level controlling algorithms on the ARM CPU and put the hardware related digital logic in the FPGA fabric. We think that if there is an image processing required, then we can accelerate it with the Hess layer in a competitive way. For this move, we need the industry standard AMBA AXI interface support, which we already developed for the Aldo card version. So we are optimistic about this plan. Okay, thank you for your attention. We are happy to answer your questions now, or you can get in touch with us via the links on this slide.
So thank you, Ernő and Zoltán. So it's time for questions for both of you. Maybe you can see both of you online. So first I would like to ask if there is any question from outside. Okay, so then from locally. Okay, that's Yuri.
Okay. Hi. My first question is, which is the cheapest FPGA platform, for example, for a student to try this as layer?
Thank you for the question. Let me answer that one. Actually, these boards that I've shown in my part, probably this would be the cheapest one. The list price for this is around $300 US, but universities and research institutes can get these for a highly reduced price or even for free via the Xilinx academic program. So this is not manufactured by us, just to make clear, we are using off-the-shelf hardware, but I think this would be the cheapest. But this is something that you have to actually purchase, even if it's for a reduced price. You can also use the cloud options with the various Alva cards that Ernő mentioned for $1 to US per hour if we are talking about just shorter tasks.
Okay, thanks. The other question is that you mentioned that using the FPGA is make parallels the programs. It is a good practice, and also to over efficiency. But I work on embedded system, and the timing is very important to make real-time system. And this newly developed S layer is support this real-time aspect of the FPGA using.
Let me also answer that one. Thank you for this question too. That's quite interesting question. This real-time usage is not something that we specifically support or specifically designed Hestia for, but it is actually it would actually be possible with the Zing platform that Ernő talked about the aerospace applications. So right now, the model that you use Hestia in is that you have some kind of program running on a CPU or a host PC, and you offload parallel computations to an FPGA. So we are using an FPGA as an accelerator, a compute accelerator. You are right that FPGAs can very well be used for real-time tasks, since, as I also shown, they are deterministic, since there are no noisy neighbors on the same chip. What would be possible in the very near future, as we are implementing support for embedded systems, is talking to peripherals directly from the FPGA chip. So you wouldn't go through the CPU and to a software layer and kind of break the real-time promise, because we are talking about higher level operating systems there, but rather you would directly communicate with other peripherals on the chip or off chip from the FPGA, making the whole computation real-time.
Okay, thank you. Any further questions? I cannot see any raised hand either from inside or outside. So let's thank to Zoltan and Ernő again.
Thank you.
Now we will make a short break, so they will leave us online, but we're coming back at 10:50 with a talk of Gyakorlás. Okay, so thank you for all of the speakers for this first session. Okay, teacher.
Hello. Hello. Gergely, hallasz?
Hello.
Hello, hello.
Köszönöm.
Hello.
Thank you so much. I didn't realize it's a break, so sorry.
So we can hear you.
Thank you. Thank you so much. When is the break over?
So we have a few minutes left, I think. Because not everybody is here right now. Can we test the sound?
Yes, that would be great. Megoszthatom a képernyőt, Gergely?
Persze, persze, nyugodtan.
Valaki más. Ja, azt írja, hogy nem tudom addig megosztani, míg valaki más megosztja.
Ja, bocsánat, akkor abba hagyom. Most próbálj meg.
Szuper. És... aha. Oké.
Jó.
Már látod, ugye?
Látom a bugjokat, igen.
Szuper. És akkor megpróbálok eljutni egy olyan diáig, ahol ez... Na, itt vannak például. Mondjuk, hogyha... Az a kérdés, hogy ezt lehet hallani ott. Lejátszottam egy hangot. Ti hallottátok, hogy hallottad?
Nem hallottuk sajnos.
Jaj, hát akkor ez így nem fog működni. Ilyet még sose próbáltam. Nem tudom, mit kell csinálni ehhez, de hát legfeljebb majd elmesélem.
Még egyszer próbáljuk meg?
Jó.
Nem, sem.
Jaj, szomorú. Aha, hát akkor ez így működik, illetve hát így nem működik. Jó, majd addig még nézelődöm, hát a közbe se kerül.
A saját mikrofonodra, hogy olyan hangosra állítod.
Aha.
De nem, mert az a baj, a beépített mikrofont használsz, gondolom.
Igen.
Azok önszűrősek mindig. Tehát, hogy kiszűrje azt az outputot, amit a gép kiad. Hát nem tudom, hogy legyen.
Jó, hát nem baj. Megpróbáltuk, majd elfütyülöm őket. Még lehet, hogy itt a gépemen lehet valamit állítani, majd még nézelődöm. De nagyon szépen köszi.
Szívesen.
Jó. Várjál, és akkor tegyük most le, és akkor beszélünk. Halló, akkor hallotok? Hallotok?
Bocsánat. Igen, most
Hallasz? Valami, Gábor, beszélj Tóri, légy.
Most le van némítva.
Oda megy ki a hang.
De Jakó van ez.
Tóni, le vagy némítva. Magadat némítottad le.
Most hallotok?
Igen.
Ja, szuper, nagyszerű. Jó, akkor egy share screen csinálok.
Jó, akkor let me switch to English again, and let's start for the locals. Unfortunately, the virtual coffee and the real coffee both are over. And now let me welcome Antal Jakovec, who is now the member of the Wigner Research Center, Computational Physics Department. And he will speak about artificial intelligence relations, understanding in the artificial intelligence and mathematical approach. So Tony, the virtual stage is yours, so please go and make your presentation.
Yeah, okay, thank you very much. Can you hear me?
Yes, yeah.
Okay.
The previous was better. Actually, the previous was better.
Previous was better. Then here, in this way, can you hear me?
Yes. Yeah, that's better.
Okay, that's better. Then I keep this one. So I share the screen. Okay. So can you see the transparency, the slide?
Yes.
Okay, great. Then I start then. So what I would like to speak about is understanding in science and in artificial intelligence. Okay, so let's start. What is the plan we want to go through? First, I would like to go through some notions, some challenges of understanding. Then let us start to define precisely what we are speaking about. So, what is understanding? This is the next question we want to answer. Then, how this works in artificial intelligence and how it works in science, and then comes the notion of relevant coordinates. If I will have time, probably not. I may speak some words about the learning process, and then some conclusions. Okay, so let's start with the introductions. What are the challenges with understanding? So I chosen a motto from Frank Herbert, the writer of Dune. You can read it here. Deep in the human unconscious is a pervasive need for a logical universe that makes sense, but the real universe is always one step beyond logic. And I would like to go somehow at the background of this feeling which is actually probably concerns all of us. So the first point I would like to pin down is that the technical evolution, new tools, new developments makes necessary to rethink old concepts, and understanding is one of these old concepts. Actually, understanding is a long debated phenomenon. So a branch of philosophy, the epistemology, deals with understanding, the aspects of understanding. And nowadays, two topics which challenge this notion. The first one is the artificial intelligence. I will go into detail later. And the other one is the scientific understanding, meaning that today the scientific models or scientific and technical models are so complicated that probably nobody in the Earth can understand it fully. For example, if you think about a structure of a CPU, so the question of how that, what does in that case mean understanding is a delicate question. So let's start. The first slide is about why artificial intelligence is necessary. I don't think I have to go too much into details. Everybody knows that there is a big amount of data produced daily, and even more are stored, and we need organizing principles. And moreover, these data are very valuable. So the economist says that it is the most valuable resource of in the earth, is more valuable than oil today. And so this organizing principle, if there is a known process in the background, then we can use science, we can use statistics, we can use the models, calibrating models, and then understand what is going on. But in a lot of cases, there are no known processes in behind. And then we have to use some computer methods, including artificial intelligence. So that's why artificial intelligence is unavoidable today. Artificial intelligence has a lot of successes and a number of challenges. The successes are always in the headline of all the papers. We know that table and computer games are in high level played by artificial intelligence. We know images like in the left hand side, which is a pure a creation. This person doesn't exist, for example, in the left hand side. This is image generation, image recognition as well. Natural language processing, translation is also a very in a very good shape now, and self-driving cars, albeit it's a little bit step back from the earlier expectations, but still it is developing in a fast steps. But nevertheless, there are some challenges we are facing. First of all, then the most severe of these challenges is they're showing up unexpected errors in the AI processes. Like in the right hand side, you see these two images which are almost the same, identical for our eyes, but an image classificator may classify the first as a school bus and the second, for example, an oyster or something like that. And here is this stop sign, which is we recognize without problem, but with the sticks on the table tablet, it seems for a classifier and something different. So these are very prone to adversarial attacks. And also long-range correlation is missing, but I don't want to go into details. So the main problem is are these which are made challenges which artificial intelligence is facing, and somehow one feels that whether or questions that whether AI does understand what it does, or just it's a pure coincidence that it sometimes or in most cases it guesses the right result correctly. So this is the artificial intelligence part, and that is the scientific part which challenges understanding. And let's for that let's go a little bit into details, but very shortly. So we know that so we are speaking about scientific approaches, and we know that until the mid 20th century, science worked. That scientists sat down and worked out the theory by thinking, by observing the world, and they used paper and pencil to solve this to solve these equations. But in this way, only the linear systems were solvable, or the systems which could be transformed to linear. And if there were nonlinearity in the system, then one had to use perturbation theory. This whole method of solving the system proposed a coherent worldview that a generic problem is solvable at all scales. We only need the tools. Actually, if we know the spectrum of the model, then we know everything. So it's a very coherent worldview was suggested by this method. But since the mid 20th century, a new paradigm shown up. This is the computers, and from then on, we use the theory which is settled by the sciences as given, but the solution was trusted to computers. So. And this made possible that nonlinear system to solve nonlinear system as well. And we have revealed a lot of new phenomena in this way. For example, chaos, chaotic systems, new phase transitions, and so on and so forth. So it was very, very useful and very powerful method. But the problem was behind, so the same method which provided us a new solution method made understanding a question mark so this whole phenomenon questioned. The main problem that we see the numbers, but we see the numbers also from experiments, and we suddenly realize that in vain we know the theory, we still doesn't know why this actual number came out. So this is a feeling of a lot of physicists nowadays, or since the mid 20th century, is that somehow understanding was forgotten in this whole process. And another interesting thing happened also, that if we have a multi-parameter model, like I used an example of event generators, but other models are good examples for this as well, then suddenly we didn't understand the meaning of each parameters in this multi-parameter model, because they have no meaning. So if we calibrated the model in a different way, it worked as well as good as in the original case. So while for example in the mechanics, we can identify that this term relevant for kinetic energy, this term relevant for potential energy, and so on. In a multi-parameter model, this clear separation, this clear understanding was missed. And in the 21st century, again a new paradigm, the AI, came along, and this stirred even more the notion of understanding. The problem is that nowadays more and more the strategy is that we even don't want to or can't write down the theory ourselves. We trust the computers to write down the theory, and we don't know the solutions as well. So we just provide the data for the computer, and it does anything. It does the magic, and something comes out. So the question is that what is understanding from this system? So I think that clarifying the meaning of understanding is very urgent now, especially in the light of the unexpected errors of the artificial intelligence. So let's go into details. I don't want to go very deep. What is understanding? First of all, what can be understood? We can understand a lot of things, like a formula, a book, a joke, image, and so on. The first question, probably, which we have to pose, is that is it uniquely defined or not? For example, if you consider the image on the right-hand side, I think I can move it down. Probably I can make it vanish, but it is better now. So you consider this image in the right-hand side, then we can describe it in the different ways. we can say that it contains colored pixels, and it's okay. It's true, and it's a perfect description of this picture. We can say that this is a picture, a work of Renoir. So if somebody tracked the movements of the paint brushes of Renoir, then he or she can reproduce this image correctly, almost correctly. But we can also describe it with human notions, like this picture depicts a woman with a tabby cat in a room, and so on and so forth. Or we can just say that this is Renoir, woman, and a cat, and then we can reproduce the same image correctly. So the message is that we can use different ways to describe the same image, and these are all legitimate understanding of the same image. Nothing is better than the other. For a computer scientist or us who deals with storing the image, colored pixels are the most important ones. As an observer, a human observer, these human notions are the most important, but the main message is that these are equally well, describe the image equally well. Now the problem, these are all legitimate understanding of the same image. When comes the difference? Difference comes when we have a lot of images, a collection or a set of images, then the different approaches make a difference in this case. So then we can try to loosely define the understanding. So as we have settled down, for a single image, any descriptions are equally good. But for a collection of images, we should reveal what is common in all of the images. And these common features provide us the notion of understanding. If we know what is common in the pictures, then it is easy to say that to tell that an image is an element of our collection. For example, if we collect cat images, then a dog image is clearly not an element of our collection. And also we can remember any image in our collection because we just assign a number to each images in our collection, and this number is much less than the number of all of the images, and so on. So somehow we have to approach this notion that we should reveal what is common in them in mathematical language. And actually this is what a classifier or an artificial intelligence does, although we may not be aware of that. So, okay. So our goal is to make this loose definition mathematically precise. Let's make some mathematics. I don't want to go into the details too deeply, but some thoughts how it can be approached in a mathematical way. So let's speak about this image again. These approaches, which I've listed two transparencies ago, these are all somehow describe the same image, and if you do it well, the same image with the same accuracy. So that means that all descriptions can be refined to give the same details, all of these which are listed here, oral equivalent representation of the individual images, and this means that there are somehow all coordinatization of the same image. So the main point here is that we have an image, and we can choose different coordinatizations, which for example, in this case, which chooses n pixel, and for each pixel nc colors. If you consider the finite set, X is a finite set, then the number of all possible images is this one, but this is so this is the number of images, but we can choose other coordinate system to describe the same image. Okay, so this will be our coordinatization, which assigns to X to some coordinates and coordinates, and we mostly use the binary base. So I is 0 or 1, and psi I X are the coordinates. And okay. Now the next point is that we have to reveal the common features. in the collection, in the set. For that, we use statistics or probability theory. This is the same probability theory that everyone knows. So this is the same notions, just to go through to speak in the same language. So if we have we speak about the joint distribution of some coordinates over the C, this is a conditional probability actually. In this way, so we count all of the, so we go through the given set, and we count the cases when the coordinates of this image are the same, the given coordinates of this image are the same, which are fixed in the left-hand side. And we divided 1 over C, so this is a probability. Then we can speak about expected value. For example, a coordinate function expected value is given here. This is the same expected value which is used in a probability theory. It is expected value over the C, so it's again a conditional expected value. A very important notion is that when we speak about independent coordinates, and this is the statement is that independent coordinates are the ones which are factorized in the joint distribution. So if the ith coordinates distribution is a product, shows up as a product in the joint distribution. If it is true, then all correlation functions factorize as well. And in a binary case, if coordinate function factorize, then the probability factorizes too. So then is a one-to-one correspondence. In a more complicated cases, it is not true. But if we speak about only the binary case, then these two statements are equivalent. Now we can speak about two special cases. One simple thing when a coordinate is deterministic. So if we go through any element of C, so this subset or collection, maybe that some coordinate is constant. For example, if we choose only black and white colors, then the statement that the image contains black and white colors, then it is a constantly true in the whole set. So these coordinates are deterministic. And on the other extreme, a coordinate can have a uniform distribution if in this set, in the C set, all of the values are taken uniformly. So all of the coordinates appear at least appear in the same times. Okay, so these are the usual notions about probability theory, and let's now use it for the for characterizing the image. But first, maybe we may go through some examples. For example, if our collection contains only a single element, then all coordinates are deterministic. If our set contains the complete set, then all coordinates are independent and uniformly distributed because all values occur in the same times. And this is a little more complicated example for 3 bits. And in this case, what we see is that, for example, the distribution of the first coordinate. What is the distribution of the first coordinate? Here is 0, 0, 1, 1. That means that 2 times 0, 2 times 1. So it's a uniform distribution over 0 and 1. And it is true for all of the 3 bits. You can check that it is true for all the 2-point correlations as well. But funnily enough, the 3-bit correlation is not uniform. Just to see that, we check that the 3-point expected value is how it is calculated. So sigma 1, sigma 2, sigma 3 is 0 here. 0, 0 times 1 is 0. This is 0. This is 0. And this is 1. So that means that the expected value is 1/4, which is not equal to the expected value of sigma 1, sigma 2, sigma 3, because each of one is 1/2, so it is altogether 1/8. That means that this example it clearly shows that in a subset, new correlations show up. And these correlations, which makes it difficult to understand this image. But if we reveal these correlations, then we are in the position that we have revealed the common features of this subset, so we understood this subset. So what we can understood, again, it is seen here, is a subset, and then there is a so we can have these common features. Okay, so then we can define what is understanding. I've mainly concentrate on understanding a subset. Also, it can we can understand also a disjunct subsets altogether. But the main point is that so we can define that we understand the subset if we can give a coordinatization, which I will call complete model, that all coordinates are independent and either deterministic or uniformly distributed. If it is true that all are independent, then we can easily generate a picture, an image from this collection, as we will see later. So this is really the mathematical definition of understanding. Actually, the same can be told for disjunct subsets, the collection of disjunct subsets or set of disjunct subsets. Then we can speak about a common complete model that all the coordinates are independent for all the elements, all CA, and also for the union set as well. And they are either deterministic or uniformly distributed for all of the subsets. Okay, let's have this is the proof of existence. I don't want to go into details too much. The main point is that one can prove that it exists. Always exists this construction. I mean this coordinate system. So this in this case, understanding is always exists for all sets. The essence of the proof is that these are this is for the previous example. These were our chosen subset 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, and we recoordinatize. So apply a bijection here in a way, which is in this case it's a permutation, that we sort all of the elements of our chosen subset to the front. And in this case, the new coordinates of these elements of our chosen C subset is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. That means for all cases, the first bit is 0. And that means that the first bit in this new coordinate system is a deterministic thing, and the second and the fourth are uniformly distributed and all are independent. So this is the essence of the proof. I don't want to go into details. Just I show another example here for 3 disjunct subsets. How can we understand them together? Here is C1, C2, and C3, and these are randomly chosen elements of all of the 4 bits samples. And what we do is the same trick as before, that we sort the elements of C1 to the first, then comes C2, then comes C3, and this is a numbered, so an index set. So these are the index of these elements is 1, 2, 3, 4, 5, 6, and so on and so forth. And the new coordinate system, so the bijection renders to this element 0, 0, 0, 1, to this element 0, 0, 0, 1, and so on. And what we see that for the first 4 elements, the first 2 coordinates are 0, 0. So these are deterministic. I will call these deterministic bits as relevant bits. And the last 2 coordinates are uniformly distributed and independent. And these I will call the irrelevant bits. So as you see, this is a very simple process in case of 4 bits. In case of 1 million bits, it's a little bit more complicated, and one cannot do it in just a simple way. This is why we need a computer to accomplish this task for us. Okay, how does it help understanding? For classification, for example, we have to consider only the relevant bits. For example, if we want to ask, well, I come back. If we want to ask that 0101 is element, whether it is element of C1 or not, then we have to see that 0101, what is the coordinate of the 0101? It is 00101. And we have to choose to consider only the relevant bits. So the first 2 bits, it is 00, and then go through, and we see that 00 corresponds to C1. That means that just to, if we know this coordinatization, we have to pick only the relevant bits, and this uniquely identify that subset that this belongs to, or defines that it doesn't belong to any of our chosen subsets. And we can also solve the decoding or lossless data compression. This last thing is very interesting. So for example, let's imagine that we have an element of some of the subsets that we know that means that we know that this element belongs to a given subset. Then how can we recognize, how can we compress the information that contains in this image? If we know, so this is a prior knowledge, so to say. The prior knowledge in this new coordinate system, it means that we know that all the relevant bits are deterministic. So it is not necessary to store the relevant bits, because the relevant bits are the prior knowledge. We have to store only that part which is not unique in this subset, and these are the irrelevant bits. That means that for lossless data compression, we need to store lossless data compression, we need to store the irrelevant bits. For example, in the previous case, to compress this element, we have to remember only 1, 0. Because the first 2 bits, if we know that it is element of C1, is fixed by 0, 0. Okay, we can also do a continuous approximation from the bits. We can provide numbers with the same significant binary figures. That means that, and then in this case, the distribution of our coordinates is either a fixed one, so deterministic, or a flat distribution, just like before in the binary case. Okay, how much time do I have? Time? I don't know exactly how. Okay, anyhow. Let's go a little bit into the question of how this applies to science. I don't want to describe too much details, only just consider an example. So in science, how we generate subsets, which is to be understood in science. And usually we take a measurement. For example, here the measurement is that in this system that we have a slope, let a ball roll down in the slope, and then it collides with another ball, which finally falls out of the table, and we measure the time difference between the collision and the fall off. So let's say that, but any other experiment is as good as this one. Now we observe different states and different processes in the world, and we assign them to different subclasses depending on the measured value, or measured delta t value. So this singles out subsets, and these will be the subsets which are to be understood in science. For example, if we change the height of this roll down, then it will change the delta t. If we change the person who makes this experiment, this will not change the delta t. So we can observe, so if we settle down these subsets and found the common model for them, common complete model for them, then can be different type of coordinates. One coordinates are the overall relevant coordinates. This doesn't tell anything more that we have. These are the experimental setup. These won't change in all of the experiments at all. These are not important. There are overall irrelevant coordinates. For example, what is the color of the ball? Who makes this experiment? These again do not influence the results, so we can forget about them. These are also not important. And that means that only those quantities which will change the delta t and will change in any of the experiments will be important for us. And it's very interesting in the scientific models that only a few numbers of these relevant or partially relevant coordinates exist. In this case, delta t, we know so we can solve it in physics, of course, it's this problem, and we know that delta t is influenced by only this s, the distance from the end of the table, the height of the roll down, and the gravitational constant, and the two masses. These are only the coordinates which influence anyhow this process. And these indeed. These are, at one hand, the partially relevant coordinates, the quantities for the common complete model, and on the other hand, these yield the usual concept of mechanics. So this is how understanding happens in science. Okay. This is the same thing. Let me skip this one, and maybe discuss this one. So how can we observe a natural law? It can happen that we use an overcomplete basis. For example, we observe that the value of the acceleration, the value of the mass, and the value of the applied force all are relevant coordinates in the sense of the previous study. But if we do enough experiments, we can observe as well that these three quantities are not independent from each other. So we have an overcomplete basis. And this is the way how natural laws can be discovered. For example, in this case, the Newton's law. Okay, so the message is the most important step is the distillation of the relevant or the partially relevant coordinates. And once we have found them, their relation can be studied and we have understood then the problem. Okay, this is not so important. Let me skip and let me speak about the number of relevant coordinates. So what is the difference between Newton equations and the cat images? Both, as we have seen, singles out some subset which is to be understood. So what is the notion of understanding is the same in the two. Then how it comes that mechanics has equations and we can compute mechanics and we understand it fully, but while the cat images we cannot assign kind of Newton equations for them for the images. Why is this difference? And the core question is the number of relevant coordinates. Okay. And for that, let me consider two images. One is the Ising configurations from a model where this is a binary model, and it is if you don't know it, then it is a scientific model, and where in some way we generate these configurations, and we do some measurements in it. So the main point is that just like in the mechanics case, there are a few number of relevant quantities. In this case, just 3 relevant quantities. But let us consider an image. In this case, this black square on white background. It is, as we can compare the two, and we see that it is a very, very ordered image as compared to the previous one. And indeed, we can argue that, so we can describe this image only giving by the coordinates of the left, top left corner and the edge size of the square. And as if we know these 3 coordinates, then all pixels of this image can be reconstructed. As opposed in the previous case, when we know these 3 numbers, just a set can be, this defines just the set where we picked up this image by random. That means that these 3 quantities are enough to compress, lossless compress this black square on white background image. That means that these are irrelevant quantities. So the main message is that in a scientific model, there are a few relevant quantities and a lot of irrelevant ones. In the image recognition, there are a few irrelevant quantities and a large number of relevant ones, at least in this very ordered image. So between the two, there is a whole spectrum, starting from the Ising model, so the scientific models, to the geometric images. The number of relevant coordinates decrease and the number of irrelevant increase. No, in the reverse way. So these are there is a lot of irrelevant coordinates and there's few relevant ones, and in this vice versa. And this is why science and artificial intelligence are different, because in science we are at this part of the image, and we have few relevant quantities which are all identifiable, and we have exact laws and exact relations, and this is the realm of science. While on the other extreme, we have a lot of relevant quantities which are and since these are a lot of quantities that are unidentifiable, then in a lot of cases they play similar role, and there is no exact restriction. And this is the realm of artificial intelligence. And in between, it is a good question what to use. So I think there is a mixture of the two, which has to be used in chemistry, biology, and also in nuclear physics and so on. Okay. This is the same which I told you, and okay, maybe okay. I think my time is over. I don't know how much time do I have.
We had a little bit of delay, but basically you are over.
Oh, I didn't understand it.
So yeah, basically you are over, but of course you can.
Okay, so I go to okay, I go to conclusions. I hope that the main message could be transferred. So my conclusions is that understanding is nothing else than finding the relevant irrelevant coordinates. It is of course a very, very hard task, but this is what exactly a human thinking and also artificial intelligence does. They must be independent and either deterministic or uniform. And if we know this system, then we have revealed the common features of a set or a set of sets. And then all artificial intelligence tasks can be easily performed. And what we have learned also that the number of relevant coordinates can vary vastly, that in scientific models, there are a few number of relevant coordinates in geometric images, a very, very large number of relevant coordinates are present. And that's why image recognition and scientific approach are somehow the two extremes of the same complete world of understanding. So thank you very much for the attention.
I'm asking if there's any question from outside. I'm checking the chat.
Hi.
Hi.
Hi. Thank you for the nice talk. I would have a more general question coming from the direction of neural science. There is a theorem that if the systems are near to criticality, the information processing is becoming optimal. So my question is, do you know if this principle is used in artificial intelligence systems, or especially when you spoke about the disadvantages of unknown long-range correlations? So exploring such unknown correlations or basic coordinates, this criticality approach might be helpful. Question.
Yeah, I think that as I've told you that in most artificial intelligence models, so it is very hard to find that thing what is criticality in this case. We have a very lot of, as I've told you, that very lot of relevant coordinates and very lot of irrelevant coordinates. So we usually cannot. So criticality is usually in a very short, very narrow range of the relevant coordinates, so I'm not sure that it occurs in for example image recognition. So it's a good point actually. So how could we reveal criticality in what does it mean at all? Criticality in kind of say pattern recognition. So it's really an interesting question. I have to think about that, but usually there are so lot of relevant parameters. Then if at all this exists, then it is very hard to find it. But maybe it may have some importance even when we do image recognition, for example.
Okay, thank you very much.
The chat, so Tamás Geszti, we have some questions from the chat. So Tamás Geszti, maybe if you are online, you may ask the question. Or Olena.
Hello.
Hi.
Yeah, I would love to ask a question. Very interesting talk. Thank you so much. And I'm very happy to hear some very general mathematical definition of understanding. Because all the time in physics or in text processing, people argue with me, but does the computer really understand what it's doing? And I had the feeling that it understands not more and not less than I, as a physicist, understand the physics problem, but it couldn't put it in such great mathematical explanation. Wonderful. But here, also my physics background screams that our science is not exact. So we don't have actually exact laws, and that maybe in mathematics somewhere in the infinite galaxy exists, but all things we do is always only approximations. And also in the language understanding, it's also only approximate. And so what can you say about such things that may be like approximate understanding or partial understanding? Can I put in your mathematical approach also such concept, because it's for me important. In text processing, when I try to define the answer to the question or the class for this text, then very often there are overlaps in the classes, and for some text I cannot define if it falls into CA or C2, at least in my limited, not infinite number of coordinates. If I think of the quantum field theory and infinite number of coordinates, and maybe it's possible in that approximation, but not approximation, that limit, but we always work with embedding of not infinite number of directions. And then I'm limited, and maybe this is why I only can have partial understanding. So what do you say?
Yeah, it's a very good point which you emphasize here. I skipped some transparencies. Maybe I will. Okay, in the complete talk, I skipped some transparencies. The point is that my understanding of the whole stuff is the following. Of course, when we started to gather information, then we have a limited subset, so to say. So that means that we can start to speculate or start to understand that limited subset of experiments or something like that, and then we then single out the relevant and irrelevant coordinates from the limited understanding, and then comes the new event, and the question is that whether it is a part of our collection or not in this general case, and probably since this is a new element, then if we do we study all of the in this new coordinate system, it will have those coordinates which should be relevant for the subset, and these which should be irrelevant. And we can and in this new element we have some numbers for that. And if the general approach of learning is that study the new element and use our coordinate system or established coordinate system and study the relevant bits. These will not all the same, like which already like in the already studied set, but if the most and this is a new, well, this is the art of this whole stuff. If enough number of the relevant bits are the same as or studied set, then we can say that it is probably element of our studied set. I don't know if it is an answer to that, but another point is which is very important here is that how can I tell it? So if we extend the subset from one element to all of the elements of the world, the number of relevant coordinates decrease and the number of irrelevants increase. If we have just a single event, then in any coordinate system, all coordinates are relevant. If we consider all of the events possible, then all coordinates are irrelevant. So if you have a measurement or a coordinate, then at some point it turns out to be for some extent it is relevant, and it becomes irrelevant after that. And this defines you a measure of relevance. Mm-hmm. Maybe it's too fast in this way, but I think this is a very, very important thing here. Exactly what you have told is that so assign the measure of relevance for each coordinate. And it can be done in physics by renormalization group, in computer science in this way that you change the subset, the studied subset. But I think this is also an important aspect of the question you have asked. So thank you.
So your transparencies are online, right? I can look at
it. Will be online, or will at least it will be online. Yes. And,
okay, great.
So thank you very much, Tony, again. And it started a very interesting discussion. And now let me switch to the next speaker, which is Sándor Sebő. Sándor?
Yes.
Tony, you are still in the main.
Hello, can you hear me?
Can you share your slides?
Yes. Can you hear me?
Yes, perfectly.
Cool. Okay. Hello, everybody. I'm trying to share my presentation. Yeah, I put it out. Do you have it? Can you see it?
Yes,
Okay, cool. Okay, hello everybody. I brought a quite different but hopefully an interesting topic for you. I'm a biologist and I'm interested in ecological studies and ecological studies, and I try to identify species by their sounds and I want to share my very first results, some preliminary results in this topic. And of course, it is related to the deep learning techniques, and that's why I'm here. Okay. It's okay. Okay, so nowadays, in the last couple of years, ecology really discovered the deep learning techniques for itself. That is indicated by the number of papers related to the usage of these kind of techniques. Mainly, they are related to the image processing and image classification. And these images coming from photographs, from video recordings, from satellite images. And based on that classification, we can identify individuals, species, we can assess or calculate somehow the diversity itself. This would be the first level, I would say, that is what is related to deep learning techniques. But there is a higher level where, based on this lot of data, actually we can build ecological models related to, based on deep learning techniques, and we can somehow predict the ecological changes. For example, what is the human impact on the ecosystems? And and what I'm really interested in is the passive acoustic methods. What is actually just we put out microphones or hydrophones into nature, and we connect it to autonomous recorders, and we just collect a lot of sounds. So that would be the very essence of that, and that's how after that, from the recordings, mostly based on the spectrographic representation, we can identify the different species on the recordings. And so these kind of techniques also emerging in the last couple of years. And as you see in this graph, we can have a lot of information from the recordings for given species or individuals. We can have somehow their activities and behavior. We can figure out what's happening in urban environment. We can, so a lot of, and we can use this data for conservation. And also, as you can see, that what kind of studies are these? Mostly they are related to the following the activity of the insects, the frogs, birds, and prominently the bats, actually. And in this talk, I'm really interested in the bats. And of course, I'm pretty sure you know that the bats, most of the bats are echolocating. It means that they are giving out ultrasound, and they are sensing the echo from the environment. So that's how they can orient themselves or find their prey. And it means that you know that bats mainly active at night. So actually the acoustic methods are very useful for that. That's why we have so many studies related to the bat sounds and the passive acoustic methods. And so bats, we find bats in many different environments, even in towns, but actually bats has to really, it's a really difficult and challenging time for bats and of course all the other species, that human really changing the environment. And so bats has to somehow cope with the changing environment on really large scale. Yeah, the climatic changes, the deforestation, and of course the mosquito killing and a lot of other problems. So, and all of the bats in Hungary, for example, protected, and they are endangered because of these things. But beyond that, actually, we can see that bats react to the changes of the environment quite quickly. So if somehow the density or the compound of the insect communities changes, that there will be some changes in the behavior of the bats or the occurrence of the bats. So that's why we say that bats are good indicator species. They can reflect the changes in the ecosystem. So it is really good to study bats because we know a lot of different aspects how the environment changes. Let me show some sounds. Ooh, I don't know that I shared this in a good way. Okay, can you hear this sound?
Yes, we can hear.
Okay, so what you can hear is that it is a greater horseshoe bat, and it's producing very high frequency sound, around 80 kilohertz, and I showed you a 10 times slower down recording just to make it audible for us. So this is a so-called constant frequency sound because you see that it's there is a quite long constant frequency sound, but we have other species, for example, the nutter's bat, that producing this very short frequency modulation signals that has very large bandwidth. Or there is another coil type that, for example, a common pipistrelle bat is producing. Also starts with the frequency modulated part, but there is a little constant frequency part in it. And lastly, let me show you a bat with alternating coil types. You can hear a lower and a higher pitch sound. Okay, so actually it seems bats are really different from their, so we can differentiate their echolocation coils, but most of the bats not so easy. So for example, the Myotis species, for example, Daubenton's bat and Geoffroy's bat, it is much more difficult to differentiate them. And it means that we have to really measure these sounds. For example, where is the at what frequency they have the energy, the maximum energy, or how long these coil times, what is the starting frequency, end frequency. So we can measure a lot of parameters, and that's how we can figure out what species they are. And for that, already a lot of people collected data, and we have big tables that we can follow, and a lot of times we can measure. I mean, we can identify the bat species, and we can make, of course, graphs to make it more clear. And you can see that with different symbols, you can see different bat species, and it is depicted by the end frequency of the core and the signal duration in milliseconds. And you see that there is quite large overlap between the species, so it's not as easy. So we have to maybe check other dimensions also. Maybe it is better for this Myotis naturae species. But what is the conclusion from this? That it is not easy to identify the bats. And the reason of that these sounds were not selected in the evolution for to be well differentiated by species, but they were evolved for the task, and the task was is to orient themselves in different habitats and to catch their prey. Okay, so we need automatic bat species identification because it is just really challenging to do it manually. And already there are out a lot of different solutions, commercial and free softwares, and they are not so bad, but they are around, they can, for example, for European species, they are around with the accuracy between 60 and 80%. That can be already helping, but it's actually, we always have to manually verify the results. So it is not very satisfying how this program is working. What is really good method, what they developed recently, is the not identifying the bat species, but without the species information, we can detect the bat coils, and it works really, really well. I use this method, and it works well with very intense background noise also. And nowadays there is already a solution. I mean that they started to work on the species identification based on deep learning methods also, and it's a developing field. And what my intention is to somehow join this field and making better better classifiers. So, and the actual project that I'm interested and I joined is that there was a very intense sampling in Vas County in Western Hungary, where we collected almost 5,000 hours of recording from more than 1,000 sampling points. And it is a very it would be really important for the national park to know that which forests are viable, which one they have to save from the forest management, for example. So it is a very nice task, but of course I cannot do that without automatic identification. So very first step that I did that I collected. I mean that with the help of my colleagues, we collected enough data. I mean that a lot of data from 12 species. Actually, in Hungary we have 27 species, but we concentrated on these species because we didn't have data from other species. And actually what we used is, we collected more than 65,000 bat calls that was coming from recordings where we already know that what individuals are on the recording, or we identify them after the recording. And there's another aspect of this project, and this one is that not only bats are on the recordings, but so hopefully you will hear it. So it's not a bat, but actually they are tawny owl chicks. So we can maybe detect other animals also that could be important for the national park and for the conservation. And so what we did is there is an open library for the bird sounds. It is called Xenocanto, and we downloaded a lot of recordings. And we made a database with more than 100,000 samples from 12 species. They are all nocturnal species. And we use quite the same technique for both birds and for bats. We built two different models, and the common approach is the image classification. So we generated spectrograms from the sound files. We can take them as images, and we can feed a convolutional neural network this information. And we use the framework, this darknet YOLO framework that I used successfully previously, and actually it is a simple image classification problem now with deep learning techniques. So I show some pictures from bat calls and bird songs or bird calls, and you see that they are not very. I used pictures and sounds with different background noises, with different kind of noises to make our classifier robust and usable later. Okay, and for both bats and bird model, we used quite a similar classifier with 10 convolutional layer, and I used the Wigner GPU cluster to teach these networks, and I got already pretty good accuracy, but they are just preliminary results. So I didn't make ROC curves, and I didn't go very detailed into I didn't go very much into the details yet. So that's how we have now, but I'm really interested in that, how we can even improve these results. And recently published a paper, they compare different network architecture, and they show that actually it makes sense to try out different networks. So this is one direction that I can go. The other one is that I didn't do any pre-processing of the recordings, and also we can use data augmentation to have more samples, and it means that we have to mix it with different background noises to make it more robust. And of course, I'm really interested in to include more species into this framework. Okay, and hopefully we can use it in this national park project. We can use it to figure out the habitat preference of the different species, to identify those forests that is really valuable, where there are many protected animals live. Also to figure out the ecological corridors, how the animal farms contributing to the conservation of the species, because we discovered and other authors also that that a lot of protected species are really interested in the insects that is related to these animal farms. And also what is I'm really interested is that there are huge solar panel fields we put out, but nobody studied yet that what is the effect on bats. So that would be my talk, and thanks for my colleagues for the data collection and data preparation. Thanks for the Wigner Lab that we could use the GPU cluster, and yeah, thanks for your attention.
Okay, Sándor, thank you very much. It was a very interesting talk. It was a bit long, but I'm asking whether do we have any questions from outside? Actually, here we have one. You can take that mic.
The darknet and the YOLO is for the fast detection, and perhaps when some bird or bat arrive the microphone places, you can rightly identify and make photo and other things. So you can real time.
I think it's a very nice idea, and it means that of course that we need these processing facilities on the spot, and it is a little bit different framework, but I think it's a very interesting that you are suggesting. So our framework now is that of course we collect all the data, process it, and we will give back the information to the national park. But as you mentioned, YOLO is really developed for very fast working, and it would be really cool to have such device in the future. Yeah, it's a very good point.
Okay, thank you. Sándor, I would have also some questions. One is a simple one. So what is the sensitivity in distance in these devices for the bats, for example?
Yeah, that's an interesting topic, because different bats has different sound level. So the sound pressure level for small bat can be just make it that we can only sense them from 5 meters. But other bats we can sense 50 meters, for example. So we really have to take it into account in such studies when we are interested in the abundance.
So basically you have about 50-meter diameter around your spots on the map, and that's what you can call it.
Yes, yes, yes.
And another question related to your slide, where you had the frequency versus timing and a huge statistics in relation with special bat species. So have you compared this to birds, because you have also several studies on birds? So what's the difference?
Oh, sorry, I missed the point. I missed
one of your slides. I couldn't remember the slide number. You had two plots. In the left side, you had something like the typical frequency versus the time in milliseconds.
I see. For the bats, yeah.
This was for bats, for one species, and the other was for another one.
I see now. Yeah.
The question is, if you compare this to birds song.
No, not yet. It would be nice to have the same plot for the birds. That's what you are suggesting.
Mm-hmm.
So I didn't do that actually. So I don't have that. I didn't compare them, but yeah, that would be nice to.
I'm using a very similar method to analyze the things in the deep learning way, but I mean, maybe you can just have to go on the old analog way to have a look at it, how, right? Whether the structures are similar or something.
Mm-hmm. Well, I'm a little bit lost, but that it is really embarrassing now. But I didn't get it very well. But maybe we can discuss it maybe later.
Okay, so thank you very much, Sándor, and let's switch back to the local room. And now we have András Pukic, who will speak about the breakdown of the photon blockade, a first order, and you know the slide. Sorry, the first order quantum phase transition.
I have some technical difficulties. But in the meantime, let me thank Gergő and the team for organizing this nice meeting and giving me the opportunity to speak. Can you hear me? Okay, so I'm from the group of Peter Novokos, and we do quantum optics. Yeah, but I cannot, unfortunately, I cannot concentrate on the cycle slides.
We have that in sim. So can you switch on?
No.
But that's yours.
It's mine, yeah. For some reason, it's like frozen, but it's not, because so here it switches. Maybe I just restart it. Okay, the computer. Okay, but in the meantime, I can tell you a bit about. So quantum optics is one of the main pillars of quantum science that is emerging today. And here at Wigner, quantum optics has a long history. Started out as a theory group, our group, and then we moved towards computational physics. Partly, I'm sorry to say that computational culture is in quantum optics is rather low in general. So people tend to use MATLAB or Python, or for heavier problems like ad hoc codes. Drawing még egyszer is akkor látjuk. Felismerni a
Yeah.
Okay, now it's perfect. Sorry for this. interruption. But overall, quantum optics is a very heavily experimentally driven, field of physics, and much of these quantum technologies that are emerging today are actually spin-offs of these quantum optics experimental techniques. So 4 years ago, as also Peter Domokos mentioned, we started building an experiment which has now started to produce new physics. But eventually our goal will be that we want to make the experimental and our theoretical and computational efforts converge. So this is another picture of our lab. This is a typical quantum optics lab, of which there are about 100 or a few hundreds worldwide. So in this talk, I want to tell you about a project which involved heavy computation, and it also involved experiments, although not from our part, but from an experimental colleague. So the basic physics behind what I'm going to tell you, behind the photon blockade and the breakdown of the photon blockade can be summarized very simply. So if we have a composite system, composite quantum system consisting of a finite level system, let's say an atom, which has an irregular level spacing, so the levels are irregular, and a harmonic oscillator, which physicists like a lot, because this is what we can solve, and it has one of the reasons why we like it so much is that its levels are regular level of levels. And for example, a single mode of an electromagnetic field or a microwave oscillator can behave as a quantum harmonic oscillator. So if we compose such a system, make these two systems interact, then what we will have is that the lower lying energy levels will give an irregular scheme, but on higher energies, we always have subsets of the spectrum which behave as a harmonic oscillator. So harmonic oscillator states, like a coherent state, can live on this upper part. So yeah, at high enough excitation, the spectrum always has harmonic subsets. Okay, so one of the prototypes of this kind of behavior is the Jaynes-Cummings model, which is a very simple model that quantum opticians like. So it simply describes a two-level system interacting with a harmonic oscillator mode, like an electromagnetic mode. So what it describes is that the two-level system can absorb a photon from the mode and go to the higher energy level, or emit a photon to the mode and go to the lower energy level. And this model has exactly such a spectrum as I told you about. So the lower part of the spectrum is anharmonic. It doesn't have a regular level spacing, but already at the level of 6, 7, 8 photons, the level spacing seems pretty regular. So this figure is to scale. with some reasonable experimental parameters. So in this case, what will happen is that if I drive my system with a frequency which the photons would like, so without a coupling to the atoms, I could excite a lot of photons with my driving. But due to the interaction with the atom, which makes this anharmonic lowest part of the spectrum, I cannot put photons into the system because they are not resonant, because the system is not resonant with the driving. So I cannot put 1, 2, or 3 photons into the system, but I can put many photons together. So if I can put many photons together to jump over this irregular part into this upper part of the spectrum, then I can suddenly excite a huge number of photons in the system. So this is what we mean by photon blockade, that as long as the system doesn't have any photons, it's very, very difficult to put in photons. But if I somehow manage to put in a lot of photons, so jump over this barrier of anharmonicity, then suddenly my system will have a lot of excitation. So basically, what we mean by photon blockade, so this system has 2 configurations which are stable, or let's say metastable. They have long lifetime in an experimental situation. So there is the phase when the photon blockade is intact. So most of my population is here. Some population can appear up here by quantum tunneling. This is a very, very quantum phenomenon. This is the photon blockaded part, and the other one is when the photon blockade broke down, and I jumped over this anharmonic part into the harmonic part of the spectrum, and I have a huge number of photons which like to live in this closely harmonic spectrum. And in between these 2 configurations, I have stochastic switching. So these 2 configurations are easy to understand. They are pretty deterministic, and the switching between the 2 are stochastic, and in each direction. So from the photon blockade to the broken photon blockade, and vice versa, the switching is induced by a single quantum jump, a single photon escaping from the mode. I will if I have time, I will talk about this in more detail. But basically, I can explain more easily the mechanism from the blockade to the broken blockade. So what happens is that even if most of my population is here, some population tunnels up here, and then I have practically no photons in the mode, only very little, only a very small number of photons. But if I observe a photon coming out from the system, then I know that it could not come from this part. Because from 0 photons, no photon can come out. So if I observe a photon coming out, which is a very rare event, then I know that my state is this. So basically, a photon which comes out projects the state of the system to this upper part, and then I have the drive which populates the mode. So this is a very quantum way of working, that the observation of the system acts back on the state of the system. And eventually, what I observe is a bistable behavior, a so-called telegraph signal. So my system is either in the blockaded state, for example, in this green plot, I am either here with no photons, practically no photons, or up here, and the switchings are basically instantaneous on this scale. So somehow my quantum jumps, these individual quantum jumps, are magnified. They are amplified to a macroscopic scale. I say macroscopic because the characteristic time of these switchings is much longer than any microscopic time scale of the system. So, for example, this is one of the longest microscopic time scale, this kappa microscopic time scale, which describes the photon emission rate, and you can see that that even this green line is hundreds of. So the dwelling time is hundreds of kappa, hundreds of 1 over kappa, and for the other. It can, so for other parameters, it can even be longer. And this is verified by the experiments. So the simulation method that we use resolves. This is the Monte Carlo wave function method. It is capable of resolving these individual quantum jumps. So we can see in the simulation that the switching is really induced by a single jump. So for example, this is so the system was in the dark state, no photon state, photon blockaded state, and then a quantum jump occurred. A photon escaped, which is signified by this blue peak, and indeed the photon number, which is the red, jumped up. But in this case, the photon escape was stronger than the drive, so it could not switch to the upper level. But here again, a single photon induces the process, but in this case it was able to build up the higher state, the higher photon number state, bright state, we like to call it, bright state. Okay, and this can be treated. And this was our most recent contribution to this subject. That this phenomenon can be treated as a first-order phase transition. First-order phase transitions are, of course, very familiar to everybody, like the freezing of water, and they are characterized by this that the two phases can coexist in a certain parameter range. So water and ice can coexist in a thermodynamic equilibrium in the same container, in a single container. And here, this bistability that in a certain parameter range, the two components, the dark state and the bright state, can coexist. And in time, they form this bistable behavior. This can be interpreted as a first order phase transition. And the coexistence of phases in this first order phase transition. So we can draw a phase diagram for physicists. This is very familiar. This is a phase diagram that we can draw for this phase transition. Okay, but actually, these long-lived bistabilities are not completely unknown in quantum optics, because this is what happens in the electron shelving scheme, which is a very famous scheme in quantum optics. It's used nowadays for state detection in ion traps, where a single ion can be trapped, and for long times, like even days, single ion in an electromagnetic trap. And to monitor the internal state of this ion, this electron shelving scheme was developed. They use it also in atomic clocks and also in quantum computers for state detection nowadays. So basically the idea is, it was originally developed for barium ion by Damert and co-workers. So the idea is that in barium, I have this 6s6p transition, which is a dipole allowed transition. So if I tune a laser here to this transition, then it will absorb photons from the laser and emit it to free space. So I will have a lot of fluorescence coming from the atom, as long as it cycles between these two states. But very rarely, on the time scale of 30 seconds, it can happen that from the 6p state, it goes to this 5d state, which is a so-called metastable state. It has a long lifetime of about 30 seconds. So when it's here, then the fluorescence ceases suddenly. And this was indeed seen. This is from images from the Nobel lecture of Damert. He was awarded the Nobel Prize for ion traps. This is indeed what we see in our experiment. So for certain time, I see a lot of fluorescence coming, and suddenly nothing. And when it's nothing, then I know that my ion is in this state, is trapped in this state. So this is also long-lived bistability, but the essential difference is that in this case, the time scale of this blinking behavior is directly derived from a microscopic time scale, which is actually nothing else than the lifetime of this 5D state, which is and this is in contrast with our scheme, where this bistable behavior becomes completely independent of any microscopic time scales. And so the switching time can be thousands or even more than the largest microscopic time scale. And this is what we proved here, that when this bistable behavior becomes macroscopic, both on time, in the time scale, and also the photon scale, this can be considered as the thermodynamic limit of this phase transition. Okay, I want to say a few words about the experiment. This is not a quantum optics experiment, but a quantum electronics experiment, which is a field, quantum electronics, which has been developed during the last decade or 2 decades. And nowadays this is extremely elaborate, and this is one of the. So on one hand, these devices can be used as analog quantum computers. So just simulating directly the Jaynes-Cummings model, for example. But on the other hand, they are also promising candidates. So this platform is one of the most promising candidates for this traditional gate-based quantum computing. So qubits and qubit gates can be realized with these quantum electronic circuits. So the idea is that there is basically a so-called strip-line resonator, which is nothing else than a two-dimensional coaxial cable, basically. So these are grounded plates, these two, and the middle plate is the core of this coaxial cable, which can take an input power, and then the output power can be measured. And they produce slits in this core, and then such a segment can act as a microwave resonator. So as you see, it has a 20 millimeter length. So it has resonances on the order of a few gigahertz frequencies. And then small superconducting devices, so-called Cooper pair boxes, can be integrated next to this resonator, and they interact simply. There is a capacitance form here, and they interact capacitively, these two elements. And this maps, for example, the Jaynes-Cummings model can be mapped on this system. So the photons are carried by this microwave resonator, and the atoms are these nonlinear finite elements. And okay, in practice it looks like this. So these are the input and output lines. It's all integrated on a chip. This is the cavity drive. Here is the actual experiment with the Cooper pair boxes. And then the whole this whole chip is put in a fridge. so-called dilution refrigerator, and it's cooled to a few millikelvins. And a dilution refrigerator, has everybody seen such a thing? It's like a barrel about this size. It hangs from the ceiling, and such an equipment goes into it, and all these plates represent different levels of cooling and of microwave power. So as I go down, I get cooler and cooler up to millikelvins, and the microwave power is getting attenuated more and more up to ottowatts or femtowatts, like. And of course, the other way around. So when I want to observe the output of such a system, then it has to be all this has to be amplified again. But the point is that these quantum phenomena survive these amplifications as the signal comes out from the fridge, from the chip in the fridge. So, okay, this field we like to call circuit quantum electrodynamics, and they are basically microwave electronic devices, but superconductivity is added on top of it, and since the input powers are very low, then this quantum behavior can emerge. Okay, and I won't go into more into the details. I just want to show what comes out of such an experiment. So, for example, for determining the parameters of the James-Cummings model that they map on this system, they can look at the splitting of the first excited state into two resonances, and this is the precision with which they are capable to fit Lorentzian resonance, and from this they can determine the coupling. As I said, the bell frequencies of the systems are on the order of 6 gigahertz, and in this photon blockade breakdown scheme, they are capable to see such bistability behavior. So as you see, these switchings occur on the time scale of 0.1 second in this case, whereas the longest time scale in the system is 26 microseconds. So indeed, there are several orders of magnitude separation between the two. So now we already have a joint publication in PhysRevX with them, but now we are working towards making the simulations and the experiment converge to such an extent that we do not have to use any fitting parameters at all, which is, I think, the dream goal in collaborating with experimentalists. Okay, and actually last year in last year's GPU days, I talked about my simulation framework, C++ QED, with which we perform these simulations, and also the Monte Carlo wave function method. So I think I'm going to skip this. I just want to say that this method is capable to resolve single quantum jumps, and we calculate the effect of the observation of the system on the state of the system. So all these quantum optical systems and quantum electronic systems are open systems, which means that they are subjected to continuous monitoring. So there are not single measurements, projective measurements, but the system is subject to continuous monitoring. And this Monte Carlo wave function method calculates treats the effect of such a continuous monitoring on the system of the state, the state of the system. So for example, any single photon detection is reflects on the state of the system, and indeed there are such situations when a photon coming out from the system increases the photon number within the system. And in this case, the energy is conserved only on average, on ensemble average of such trajectories. So on a single trajectory, the energy is not conserved. Okay. So as I said, our simulation tool is C++ QED. And if you want to know about more details, you can have a look at my talk from last year. I just want to mention that since this spring, during the lockdown, I started to update the whole thing to C++ 17, because I started to write it in 2006, and of course it's many components are very outdated by now, but hopefully it can come up to date. And the computational infrastructure that we used in this project was the Wigner Cloud, now ERKH Cloud, and I'm very grateful to them. It was 8x8 vCPUs. We installed a small Sloan workload manager, and just to give you an order of magnitude, this thermodynamic limit project took about half a year to collect the data on this virtual cluster. This is one of my, or I can say that this is the best computational infrastructure I use. I used a lot of different supercomputers in my life, but I'm very grateful to the cloud. So yeah, thank you.
Okay, thank you very much, András. So since we are very limited with the time for the lunch, so we have time for 2 quick questions. Anybody outside? Do we have any something in the chat box already? Let me see. Nothing. No. From here? Yeah, okay, maybe I would ask that you just mentioned this. Okay, so the question, when Hungary or when Wigner can have such a device at a certain time? So I think it's not a question of money, but it's rather a question of technology and development.
And human resources. Human resources is a huge problem. This we experienced in our experiment also. So we wanted to have such an experiment for at least a decade now. And for a long time, we hoped that someone will come home, someone who did a postdoc, let's say, at an experimental group in Germany, will come home and build such an experiment for us. But nobody came. And so at some point, we had to take a deep breath and start it ourselves. I would say that for this quantum electronics, there is a lot of expertise in the country, especially at the BMR, Szabolcs Csonka. And as far as I know, he wants to buy such a fridge. But yeah, he's doing a bit different things. Yeah, we will see. But I think he could probably make such a device in a few years, I think.
Okay, thank you. So I think I should close because we have to fill up the stomach. So for everybody outside, we will come back shortly before 2 o'clock when we have a special lecture from the CERN IT department, especially on quantum computing. So please come back until we will shut down the devices. Thank you. Ne öld meg azért.
Az üzét akartam berakni.
Hello, can you hear me?
Can you hear us? We can hear you. Alberto, our camera?
Yeah.
Okay.
Yes, I can hear you. Can you hear me?
Okay, excellent. Thank you very much. So we have a little bit of time. Can you just try to share your slides in order to see that if it's working properly? Most likely, but just we can make it. Oh, super duper. Okay. We can also see.
Yeah, I know. I move it on the other screen. Yeah, should be fine like this.
How is life at CERN?
It's probably like everywhere else. We are, I mean, we are mixing teleworking and on-site working. It depends a bit on the functions. Trying not to share offices too much. But it could be worse. I mean, the situation compared to the rest of France or Switzerland or other countries within CERN is not that bad. It's actually quite safe.
Sounds very good.
What about you? What?
So, well, we are ramping up, but I mean, there's a kind of limitation that we have. We are, I mean, by the government, we are doing limited number of tests, so we will not make a very steep upgoing. but otherwise, yeah. So well, we can see the growing numbers. We are doing the national records every day, but yeah, I think it's most likely due to the season, because that's actually the thing. So I mean, there's not so much movement outside of the crowd, the inside outside, and this is not there's not so much thing which could increase the numbers, but
yeah, but it's the same here, because it's becoming difficult to distinguish between COVID symptoms and standard flu symptoms. But every time someone has something that looks like COVID, the procedure has to be put in place. So it's difficult to organize activities, but I mean, we are entering into a bit of routine by now.
Sounds good. So unfortunately, you skipped the good Hungarian food, but I hope one time you can join us in real. And
yeah, yes.
So you can take this as a direct invitation, and anytime you are around here, I think Federico can make a motivation to come our country.
Yes. No, absolutely. I mean, I like interacting and giving talks, etc. And not being physically present has removed a bit of the fun of doing it. You're talking to people and seeing places was part of the interesting part of giving of attending conferences and giving talks. I look forward to moving again.
Yeah, me. I think everybody else around here.
Yes.
Balázs, can you just move a little bit camera, because only we are inside. So. That's video. Okay, so I think it's time to start. So welcome everyone. We see almost 20 people from outside and about 10 from here, which is the limits of the local rules. So let me very warmly welcome Alberto Di Meglio from CERN IT department, and I would like to ask you to make a presentation on the quantum computing project of the Open Lab and the same direction in the future. So please.
Excellent. So thank you very much. I think you can see my presentation. So indeed, in the next few minutes, I will give you some information about the recent CERN Quantum Technology Initiative. So this talk, of course, is given on behalf of a team of people. We have today a task force at CERN composed of people from the IT department, from the EP department, from theory, so experimental physics, theoretical physics, and the information technology mainly, to understand the potential of quantum technologies in the future for high energy physics specifically, but more in general for science. So I have a few slides about CERN, so I don't know if you know, I expect most of the people attending to be very familiar with CERN, so I will not go into details, but just to remind everybody, you know, how CERN typically works. CERN manages the accelerator, and the accelerator is used as an international facility for collaborations, the experiment, using it as a tool, as an instrument for fundamental physics research. And today, the main accelerator is the LHC accelerator. There are 4 experiments: Atlas, CMS, LHCb, and ALICE, performing different types of observations using the LHC. Now, from a computing point of view, of course, this is the starting point, the transition between the actual world and the computing and computer science world. It happens in the detectors. There are at least, I mean, very, you know, as a simplification, there are at least 4 main classes of computing workloads that we are looking at from a quantum technology point of view, quantum computing especially. And these classes are the data acquisition part, which is of course the initial collection of data from the sensors of the detectors. Then track reconstruction, where this data is transformed into actual tracks, you know, the traces of the particles generated by the collisions and traversing the detectors, and of course the final data analysis, where the reconstructed information is processed to actually, you know, go back and understand what was at the very moment of the collision. And of course there is the big class of simulation that, you know, tries to understand what would happen inside these detectors in the accelerator, try to apply the more theoretical aspects of physics to generate something that then can be compared to the experiment, to understand, you know, to prove or disprove theories and understand whether new physics has been found. So this is the standard model. Well, in terms of computing, is the default model working of all the experiments today. And as you know well, it has been until now very successful. The physics standard model has been sort of completed with discovery of the Higgs boson. Now, of course, you know, there is much more than this in the universe. You know, broadly speaking, the standard model is capable of explaining about 4 to 5% of the universe, and you know, there is a lot more outside there that today is not fully understood. You know, all the questions about dark matter, dark energy, the relation between gravity at the macroscopic level and the quantum mechanics at the microscopic level, and all the issues about why there is no actual antimatter in nature, although not only theory, but you know, even in practice, antimatter can be produced. So a lot of questions and more are still open. So the work of the experimental physicist and the theoretical physicist and of scientists in general in this field is far from finished. So the CERN and the LHC experimental schedule is still very much at the beginning. Now you have here an initial, a snapshot of the LHC program. Don't look at the dates. The dates are being revised. This is not up to date, and of course the current situation, sanitary situation in the entire world has already had an impact on the schedule. This is being revised, but broadly speaking, of course, for the future, we are looking first at the next evolution of the LHC, the so-called high luminosity LHC, where the luminosity should increase by an order or two of magnitude and allow to explore more in details not only the known physics but also look a bit beyond the known physics. And of course, we are also targeting in terms of technologies and looking into the futures. We are targeting programs beyond the high luminosity LHC, like future linear accelerators, and the future circular accelerators that are being designed and discussed. So our investigation in quantum computing and quantum technologies in general fits into this context. It's about looking at what technologies are coming up that could support, accelerate the computing aspects of the physics research in the next 5, 10, 15, 20 years. And of course, in this context, we have started looking a bit more in detail into quantum computing, which has seen a very rapid acceleration in the past few years. So already today at CERN, there are a number of unique activities and unique expertise in different fields, and especially in the 4 traditional fields of quantum information science. And these fields are, the areas traditionally are quantum computing, quantum sensing, quantum communications and networks, and the more theoretical aspects of quantum field theory, information processing, and direct quantum simulation. So there are a lot of these things happening already at CERN, but until now, we're not really classified as quantum technologies using more recent terms. So we started a process about a couple of years ago to rationalize a bit these activities and try to understand how to make them a bit more organized across CERN and also to support the high energy physics in more general ways. So 2 years ago, already as a CERN Open Lab, we organized one of the first, I believe, workshops to discuss about quantum computing for high energy physics. This was a very successful workshop. At the end, there were more than 400 people registered. At the time, almost everybody was on site. There was a very lively discussions. There were people from, of course, from the HEP community, from industry, from other sciences, discussing about the state of the art of the technology and the possible applications in physics and in other sciences. So since then, this happened about 2 years ago now. Since then, we have started a number of pilot projects and collaborations to explore a bit more in detail these emerging fields. Now, as a consequence of these initial discussions, we have proposed about a year ago, a bit less than a year ago, we have proposed the CERN management the possibility of creating a quantum technology initiative at CERN. So there are a lot of things, a lot of initiatives, a lot of projects and programs running in Europe, in the CERN member states, in the experiment member states, member institutes, and internationally. So this, of course, is not new. The CERN Quantum Technology Initiative has no claim of being the first in anything. Actually, a lot of things have started already in the past several years. But we thought it was time to understand how CERN and the HEP community that looks at CERN as a reference could invest a bit more effort, a bit more time into this into these activities and create a broader program of investigation. So this proposal, the initiative has been approved, and formally speaking, it has been approved in June this year by the Scientific Policy Committee at CERN, and in September by the Council. So all the member states. So the feedback was actually very positive. And now we are ready to start. So it is essentially an R&D program organized across the 4 areas of computing, sensing, communication, and quantum information processing. It will be mainly based on research programs and projects with students, doctoral students, postdoc, visiting scientists, but in a very important way, will be done in close coordination and close collaboration with any initiative happening in the member states, in Europe, and the neighboring countries in general, and also internationally. There will be, for example, an advisory board composed of representatives, experts in quantum technologies across the member states to guide our investigation and align what the CERN Quantum Technology Initiative does with the programs in the different member states. So what has happened until now? So far we have defined a set of high-level objectives for the 4 areas of investigation of computing, sensing, communication, and theory. Again, these are very high-level objectives. So these are our starting points. Now we are organizing a number of brainstorm events and discussions to go more in details in these events and understand what are the priority projects that CERN should support, should take part in, and how to do this in collaboration with the other national and international initiatives. So, for example, you see here a few ideas for computing. Our main objective is to assess the role of quantum machine learning. So of course, we see everywhere a growing use of machine learning, deep learning techniques in all the different computing workloads. For HEP, we would like to understand if there is in the future potentially an advantage in using a quantum approach to these machine learning activities. We want to build the experience in using the tools, the software, the hardware, quantum computing simulators, possibly have access to some hardware, and understand how to increase and to build the skills and the human capacity, the human knowledge of our community around these themes. For sensing, again, there is a lot already going on in, let's say, low energy experiment, more related to quantum, to dark matter searches, antimatter. So those activities will continue, but we will also look at possible applications to high energy physics, new classes, new types of calorimeters, of particle detectors, and understand what is the potential for future HEP detectors. Communication is also a very important class of applications. There are a lot of discussions today in Europe and in other parts of the world to build the next generation of quantum internet applications. So I will give you more information in a moment. And of course, the aspects of theory. And again, also, I will show you a bit more in a moment. So let me start with one important thing, of course, is knowledge sharing, education, and training. So we are talking about technologies that are really emerging, for which the people who can claim being experts on this are not so many at the moment in the world. So we would like to contribute to growing the knowledge and sharing this knowledge across the community. So as part of these activities, we will also organize education and training opportunities at all levels. So quantum computing, quantum technology courses, academic collaboration, but also training on actual technologies in collaboration with industry and other laboratories. So this is a very important part of this initiative. So let me start with quantum computing. So as I said, our main objective in quantum computing is to explore, especially the space of quantum machine learning. And we have started a number of investigations on different types of networks, of deep learning approaches, to explore the different workloads for simulation, classification, reconstruction, and so on. And we are looking also at the possible application of true random numbers, quantum random numbers, to see whether, for example, using these numbers might give advantages in certain classes of problems, so for seeding, track reconstruction, or for Monte Carlo models, for example. And we are also looking in the future at special application of quantum technologies for classes of problems that are not typical of HEP, but might have a very important impact in terms of science and also on practical applications like encryption, like security. And these applications are more typical of medical research, life science, or industrial applications. But as part of CERN Open Lab and as part of our collaborations with industry and multidisciplinary activities, this is also an area that we would like to explore. A few examples in this, so quantum generative models. So you might be aware of the fact that, and we use a lot of, for simulation, we are, of course, big users as a community of Monte Carlo models. And they are, of course, very, very efficient and very precise, but also require a lot of resources. And if you want to scale up Monte Carlo models, you also need to scale up resources, which has an impact in terms of the worldwide infrastructure we are using today. So in the past quite a few years, many people in the community have started looking at alternative models, like generative adversarial networks. It is possible to develop faster approaches to simulation that scale better with resources compared to current models. This has been proven to be possible. It is not production level, but it is very promising, and it is possible to show that at least under simplified conditions, these generative models have the same precision as Monte Carlo models with much better performance and scalability properties. So it is the same for quantum generative models. So we have started looking at this aspect, and with a sort of hybrid approach that puts together the two parts of the generative and the adversarial networks, combining one quantum network and a classic network as an experiment, as an initial experiment. So we are using a quantum generator and a classic discriminator. And on very simple initial models, one-dimensional, two-dimensional, again, we have seen that these models are actually quite precise. They give the expected energy profile, energy distribution of a particle, in this case of a single particle crossing a simple calorimeter. Now, one problem of today quantum generative adversarial network is that all the implementations we know of are able to sample, are able to embed the energy distribution, but cannot sample individual images, which is what you want with generative adversarial networks. You want to build synthetic but individual images very similar to what you would find in reality. So we have been working with Cambridge Quantum Computing and with IBM to move the state of the art forward. And we are experimenting today, still work in progress, but we have new models that are able to combine the existing technology, existing methods to embed the energy distribution in the quantum circuits with a method to extract individual images from the circuit. Again, this is not far from being production, but it shows promising properties. It converges very quickly. It is quite stable, and in these initial models, it shows quite interesting properties. A second example is track reconstruction. Again, track reconstruction today is done with methods like Kalman filters, for example, to follow the dynamic properties across the different dots and reconstruct the tracks. But already in the past, methods like graph networks have been considered to solve this reconstruction problem. There have been international challenges, for example, like TrackML, which and a couple of Kaggle international challenges to experiment with this model. So again, very promising, and we have started working on a quantum version using an approximation of graph neural networks using 3 tensor networks, a quantum implementation of tensor network. And again, on simple examples, this shows interesting properties, very promising. So you can see from the graph at your right bottom, it's a comparison of the performance of 4 different cases. There are 3 cases, the red, blue, and yellow, of classical solution to a simple problem of node identification, with increasing level of hidden layers, 1, 10, and 100. And the green one, the top one, is the quantum tensor network implementation with a single layer. And you can see that just with a single layer, the rapidity in converging to a very, relatively very accurate solution is superior to the other classic approach, even with a much higher number of layers. So again, this is a toy model. There are more sophisticated ways of solving these problems that don't require quantum computing. But comparing apples with apples, comparing the same conditions, the quantum version shows much better knowledge discovery and representational power than the classical counterpart. So worth exploring further. And also, in the third example is for classification. This is work that has been done by Professor Shaolan Wu as part of Atlas and the University of Wisconsin. And we have supported this project as Open Lab. It's about reproducing one of the channels of the Higgs boson decay. This was in practice one of the discoveries of the Higgs boson a few years ago, in 2012. And the Professor Wu team has reproduced the same case using a quantum support vector machine approach, which again is showing interesting properties. You see from the graph again, right bottom, that the quantum approaches, the red line in this point and the yellow line. The red line is on software simulation, quantum software simulation, and the yellow line is real hardware. They are comparable, at least, with classical method, classic SVM or boosted decision tree approaches for the same type of problem. But again, it has been seen that they converge rapidly, more rapidly, and they require less data than the classical counterpart. So all interesting things that are worth exploring more in the future. And the way we are going to explore this in the future is to contribute, at least to start with, to the creation of a quantum computing simulation platform that in our plans will be composed of both quantum computing simulation, so simulation on classic hardware, but eventually also composed of access to real quantum hardware in collaboration with companies that are producing today quantum hardware. And the platform, the idea is to capitalize on our expertise as a community in creating distributed infrastructures and create something that can be used to give access to a distributed community of researchers to, first of all, to learn how quantum computing works. The idea is to have prepackaged simulators of various types. There are many different simulators from different companies, Qiskit, Cirque, and Penny Lane, and many others. So we would like to give access to scientists and researchers to a pre-configured environments, Jupyter notebooks, code repositories, to let them start their learning curve and their investigations. And then in time, this platform, as it grows and as more and more qubits can be simulated, we will also start deploying more sophisticated experiments and projects on the platform. And the idea is to do this in collaboration with other sites. So if other sites are interested, if you can dedicate some of your infrastructure, typically GPUs, but CPUs are also efficient sometimes in this case, we would be very interested in discussing how to create different national, regional pools of quantum computing simulation facilities and work together in building a larger infrastructure. Now, in terms of sensing, I mentioned the initial investigations are more for low energy physics, antimatter or dark matter searches. There are many ongoing investigations on devices like magnetometers, squids, TESS, transition edge devices, and these are used already to detect, to build devices, very precise, very sensitive devices for measuring properties of particles. The gravitational effects, or direct measurements of mass or charge ratios and spin, direction, electric field, and so on. Now, this will continue, but it is based on something that is quite close to a standard quantum approach. It's measurement of discrete changes of quantum states. Now, can this be applied to high energy physics, where the scenario is completely different? We're not talking anymore about individual changes of quantum states, but of a continuous process of particle crossing the sensors and in the detector. So again, this is for the future, but we are brainstorming a number of ideas. Is it possible, as a question, to use nanotechnologies, nanodots, nanowires, special quantum mechanics effects to create, to build new classes of detectors, of scintillators, of particle identification devices, of calorimeters that can be efficiently used in this context, which higher sensitivity, lower energy requirements. So there is no definitive answer. Of course, this is an investigation. The idea would be to find a way of priming in some way these detectors, putting them in a special state that then reacts very quickly to the crossing of the particles across the sensors, but giving a much more precise signal. Or, for example, in case of a possible application of nanodots, they would be the effect of a particle crossing a nanodot is emission of photons, and these photons have a particular frequency, color, that depends closely on the size of the cavity inside the nanodot. So by building a controlled arrays of nanodots with different sizes, maybe you can detect very precisely where particles have crossed the detectors by analyzing the scattering, the scintillation, and not by connecting the sensors with wires, which would allow to work really at nanoscales. Is the speed enough? These devices react at the level of tens or hundreds of picoseconds. So it is not far from what is needed in the future, but there is still some work to do. Quantum communication, I mentioned quantum internet. As you know, CERN started the web in some way, but more in general, we have taken part in establishing worldwide international network infrastructures in Europe or internationally. CERN Open Lab specifically, almost 20 years ago, put in place a network link between CERN and the US, which for some time was the fastest network, transoceanic network link between Europe and the United States. So we have some history of doing this. so our plan, our objective there is to take part in all the initiatives that are happening today in Europe and in elsewhere in the world in establishing this new generation of quantum internet links, but also quantum internet devices. A big issue today is that quantum computing, quantum technologies are not very data friendly. So talking about big data with quantum today doesn't work. But if we can in the future come up with a quantum equivalent of today memory or storage devices, then it would become very, very interesting. And this has to be part of a future quantum infrastructure. So we are very keen in working on these topics. And in terms of, I mentioned our interest in working also on less physics related, more life science or security related activities. So we are discussing with initiatives in Europe, specifically with the OpenQKD project. OpenQKD is a project funded by European Commission to design, investigate the feasibility of deploying pan-European quantum key distribution links for secure data transfer. And we have recently been awarded a small sub-project as part of OpenQKD to investigate how to use a quantum key distribution on a proof of concept of end-to-end data analysis pipeline. So the idea is to start with data at rest, move the data across links, analyze the data, transfer the results back, audit and monitor the transactions, but by securing with QKD all of these links. So to have data encrypted at rest, moving encrypted data on encrypted channels, doing data analysis on encrypted data using techniques, for example, like homomorphic encryptions, and then implementing quantum version of blockchains to complete the picture. Again, it's very speculative. A lot of this cannot be done today. For example, doing really doing data analysis, especially training using deep learning on homomorphically encrypted data today is a big challenge. But this would be one of the first investigations to explore the end-to-end data analytics pipeline in this kind of scenario. And finally, in terms of theory, this is something that it's a frontier for many universities and research labs in the world. So there is work going on at CERN on a number of theoretical aspects, lattice, QCD, simulations, and information processing. A lot of the work done today, especially work to go beyond the standard model and doing dark matter searches type of activities, rely on Monte Carlo, very sophisticated Monte Carlo simulations that require HPC type of infrastructure. Nonetheless, even having all the HPC resources that we can think of, there are problems that per se cannot be solved by classical methodologies. The finite sign problem, the sign problem is one of these type of problems. The special effects in parton showers, real-time transfer phenomenon. These special quantum mechanics classes of problems are hard problems to solve, hard also mathematically, and cannot be easily or not at all solved with Monte Carlo classic approaches. So maybe these are classes of problems where a quantum approach and developing appropriate methodologies and algorithms would allow moving the state of the art and the knowledge forward. Direct quantum simulation of less accessible quantum systems on quantum hardware and extract information directly from this simulation. So there is a lot of work to do, and this program is really at the beginning. We have some ideas. We are looking for more ideas. We are looking for for collaboration and for working with a much broader community than just CERN. So of course, we welcome all sort of input at this point. If anybody has ideas, wants to explore these ideas together, take part in our exploration, or invite us to take part to their exploration at all levels, engineering, computing, sensors, networks, of course, we are absolutely available to discuss about doing this. There is at the moment a placeholder website. As I said, the formal approval only in September, so we are building this. There is a placeholder website called simply quantum.cern. It's just a web page with links. We are preparing a more interesting website with all information about the activities, the projects, the training opportunities. That this will be available in a few weeks. But in the meantime, please feel free, go to this website, contact me, and I'll be absolutely interested in discussing with everybody. Thank you. Thanks a lot.
Okay. Thank you very much, Alberto. Can you hear us?
Yes, I can.
Oh, okay. So first of all, we have 2 questions in the chat. So maybe can I ask Zoltan Lehotsky to make his first question? Zoltan?
Sorry, I was muted. Yeah, so I would just be interested in what collaboration you possibly have already with Wigner in the field of quantum computing, given that as I see, not just from this event, but also from various EU events, that quantum computing is seems like a very much strategic field in the foreseeable future for the EU.
Yes. So yeah, absolutely. So I mean, I didn't get whether it was a question or a comment, but in any case, yes. I mean, if you have ideas to collaborate, or if you are suggesting ways of collaboration, absolutely yes. So in terms, you mentioned Europe, so we are not directly part today of the quantum flagship or project in the Quantera program, but we are in close connection with them. We are taking part in we are associate members of the quantum project that has been funded by the European Commission to explore quantum computing for HEP, and we are increasing our participation as a CERN in all these activities.
Okay, thank you, Zoltan. So there's another question from Zoltan Cimborás. Cimbi, are you online?
Yes, thanks.
Please make the volume a bit higher.
Yes, thanks a lot. I hope you hear me.
Yes, I do.
So thanks a lot for the really nice talk, and also about these quantum machine learning type of enterprises. By the way, there will be a talk after my talk, which is also concentrating on quantum machine learning by Dani Nagy. My question is that what you skimmed through were always qubit-based quantum machine learning algorithms. Of course, we know that there are those photonic quantum computers built by Xanadu. I mean, you mentioned, for example, PennyLane, and Xanadu is the one that is doing the software PennyLane, which is also good also for qubit-based, let's say, machine learning, and also PsiQuantum. And those are actually somehow a more natural generalization of, say, certain type of continuous neural network models. So are you also planning to look at Q-mode based, so photonic based quantum machine learning algorithms? That's my first question, and then I have another one.
Yeah, very, very quickly, yes. I mean, we are already doing that. I didn't mention this, but especially for the GAN investigations, we are looking at continuous variable approaches, because as you say, those problems are better suited for photonic approaches rather than qubit-based. We are discussing both PsiQuant and Xanadu on possible activities. Absolutely, yes.
Mm-hmm. And my other question is, so it's more based around simulators. So are you trying to develop both hardware and a new type of software, let's say, based on, I don't know, tensor network models simulators in CERN or something like that? Because we have this quantum initiative here in Hungary, and we are also trying to do some stuff like that, actually.
So yeah, for this I don't have a definitive question. So it might be at the moment the answer would be no, because I don't think, very humbly, I don't think that we have enough knowledge and enough resources to really commit to developing new technology, hardware or software. However, it is not excluded. There is technology at CERN that can be used for quantum hardware, traps of various types, so cryogenically cooled electronics. Cryogenics is a big component of the infrastructure. So that is possible. And in terms of classic simulation, we are investigating, for example, some FPGA-based approach of simulations, but these are very, very initial discussions. Again, I cannot tell you in this case, I cannot tell you anything concrete, but I'm certainly interested in discussing more in the future.
Thanks a lot. I'm also interested in discussing this. Thank you very much.
Sure.
Okay, thank you, Cindy. Anybody else from outside or inside further questions? I cannot see anybody. Then I would make also just to make a kind of a little bit of advertisement like question to you. So if somebody would like to join to these activities at CERN, so should it go bottom up or up bottom? So shall I go to you with a kind of certain problem which I would like to solve and maybe discuss with you, or the other thing that I should find a proper person in the CERN system? For example, if I'm interested in quantum sensors or future detector developments based on these techniques, then I should go directly to the certain point. So which is the most efficient?
So you put me in a difficult position. So let's say that if you know someone at CERN that is working on things you like and you want to talk to them, by all means, absolutely, I'm not telling you that you should not talk to anybody. However, the CERN Quantum Technology Initiative has been created exactly to rationalize a bit all these contacts. So at the moment, I'm the coordinator of this activity. The task force has specific coordinators for quantum computing, sensors, networks, and theory. So at the very least, we can help you understand, unless you have a specific person in mind. If you contact me or one of the coordinators, we can tell you what is the state of the art and who might be interested in what you want to discuss. So both approaches are possible. My suggestion would be to at least let us know that you have this interest, so we can set up some more structured collaboration.
Yeah, good. This is what I told. Just I wanted to let to the others, because maybe they are also they not really know the CERN structure as you mentioned. But maybe one further thing that I can imagine that you most likely have regular events where even newcomers can join. Do you have something in the near future?
Meetings for? Sorry, I didn't understand.
Yeah. Something like meetings or which is not super specific, so more general in relation to this quantum initiative, and then join and learn and try to figure out. I mean, this used to be the case when you start something that you don't really know what you want to learn or do. So
yeah, correct. So we are building that. Let's say we are going into, it's like concentric circles. So there is a task force. It's about 10 people. We are organizing now in November a CERN internal brainstorming meeting to understand who is interested in CERN in working on this. And then the plan is to organize a much broader meeting to create this kind of links. So it will certainly happen, and I'm absolutely interested in understanding the right timing, the right contacts, the right place, the right channels for doing this. And at the same time, we are organizing education events. So this is something, if you have people that are interested in knowing more about the technology, then we will provide free access. This is Zoom, broadcast-based courses on quantum computing. There is one that will start in November for 6 weeks, 2 hours per week, as an introduction to quantum computing that covers the fundamentals, the basic quantum computer programming, a bit of a hands-on exercise. It's really introductory, but this is not to discuss, it's for learning. So what you mentioned is absolutely necessary. We are not there yet, but we need to do it.
Okay, thank you very much. This was a very important information. So I would appreciate if you have something on this and send it to me, then maybe I can share with the local communities, and then we can make more progress. And I know that you are very busy. I would like to ask you that if you have some time to join us for the rest of the afternoon and tomorrow, we are very, very welcome. But I can also understand the situation if you are not. But thank you very much. Your presence and your announcement.
No problem. I will stay for as much as I can. I may need to jump in and out for some moments, but I will be here as much as I can.
You are absolutely welcome.
The invitation. Thanks. Very nice.
Okay, so let's switch to the next speaker, who is one of the oldest member of the Wigner GPU laboratory from outside. This is Geza Overdor. Geza, are you online?
Yes, I think so.
Okay, so you will speak about critical synchronization dynamics of the Kuramoto model on a large human connect count. Please, can you share your slides, please? It's not yet seen. Geza, are you online?
Yeah. I am.
Okay.
I'm trying to doing, but I have never done it. Is it not seen?
Not yet. You can see it yourself.
Because I push this share screen button.
Now we can see you. This is better.
And you don't see the...
Not yet. Maybe it's not on the proper window.
Not the proper window. I don't really understand. No?
Not yet. Ah, it's there. Now you just have to make it full screen.
Okay.
Okay, so please.
Yes. So good afternoon, everybody. I would like to talk about our latest progress, which we started some years ago, and in the 1 year ago or 1.5 years ago, me and Jeffrey Kering already gave a talk about the beginning of our GPU computations on synchronization problems. Since then, I made extended simulations in collaboration with Gustavo Deco, who is head of a department of brain sciences at the University of Pompeu Fabra in Barcelona. And we obtained some interesting results, which I would like to share with you. Okay, so theoretical research and experiment suggests that brain operates at or near critical state between sustained activity and an inactive phase. And it is known, as I already mentioned in my comment, that optimal computational properties can be found at criticality. So for those who this criticality is not so well known, just to remind you, this criticality occurs usually at second order phase transitions, and when you have a diverging correlation length and correlation time, and fluctuation and susceptibility also high. So this makes a neural or a brain system highly sensitive if it is in the critical state. Another thing is that individual neurons are known to exhibit periodic signals, even without contact. So this brought up the idea that we can have critical behavior at the synchronization transition point. And this is what we were planning to investigate with simulations on a large human connectome. The model we used was this so-called Kuramoto oscillator model, invented in 1975. And this is just a set of ordinary differential equation where you have phases theta I located at nodes, and the difference of the phases is a function of psi. This gives you the interactions between the nodes, and they are coupled together with the, which is denoted by a Wij. It's a coupling weight matrix, and summed up for J. And there is a global coupling in the system. So just to remind you, up to this point, this is, for physicists, it is something like the XY model. But on top of it, we have these omega I zeros in the equation, which are intrinsic frequencies of the oscillators. These are fixed in time. So this gives you some kind of quenched disorder to the system and some very non-trivial behavior. Yeah, so we have a phases and a global coupling, weighted adjacency matrix, okay. And so if you follow the evolution of this system, you can calculate an order parameter, which is just the average of phases denoted by R. So the absolute value, which is a complex number in principle. And this order parameter changes at the synchronization phase transition. That means if you have high coupling, then the R goes to some constant values, into some steady state constant values in the infinite time limit. Or if you are below this KC critical point, R goes to 0, but in finite systems, it doesn't go exactly to 0, but it has some remanent small fluctuation, which is characterized by 1 over n to the 1/2. So there, it is something like the independent oscillators had some intrinsic small Gaussian fluctuation remained. And if you are just at the critical point and you start a system from an incoherent initial state, a random state, the R behaves in a scaling way. So that means it grows by theta time to the eta exponent. So it goes with a power law. And also there is a factor of n to the minus 1/2, which is just the size dependence times a scaling function. But the main point is that there is this power law behavior at the synchronization transition. Now the graph we investigated was a huge structural graph, which we could download from the repository of the Open Connectome project. It has something like 800,000 nodes and 4 times 10 to the 7 power law distributed weighted links. We investigated such a huge systems to get rid of the correction to scaling, which can blur real scaling behavior at a critical point. And topological features of this graph has been shown by our paper with Michael Gessner in 2016 in Scientific Reports. So we have also shown in a previous publication in 2019 that in this model you can find dynamical scaling behavior, and below the critical point there is another scaling, extended scaling region, which is called frustrated synchronization region. Okay, before going further, let me just mention a few technical details, but I don't go into very deeply because if you are interested, it is recorded by Jeffrey from the previous year, and I'm not an expert on it. So just to remind you, we have this Kuramoto equation, which is a coupled ordinary differential system, and you plug in the connection matrix at lambda jk, which is just provides a sparse, almost random-like graph. And this requires explicit storage of the network topology. To enhance the performance, we use some sparse representation by a list of the connections. And this calculation requires techniques of single instruction, multiple task vectorization tuned by operation and memory ordering. Okay, what we used were just standard libraries. The Boost libraries, which is a template library for solving ordinary differential equations. And the program was written in CUDA. And another library Jeffrey used, it was this VexCL, which is a library for offboarding vector expressions. It is also available both for CUDA and OpenCL. And we used these libraries for solving the equation with the fourth order Runge-Kutta solver. So computing the derivatives remains to be the most time-consuming part of this whole problem. So this is for the implementation. And the efficiency, just to remind you, I just provide some figures which Jeffrey already showed you. It was measured on a Tesla P100 card, and main conclusion is that this remains to be a memory latency bound problem due to the random access of neighbors. But the implementations could achieve the integration of random graphs with a speed up of something like 20 improved throughput over a single CPU socket. And we want to mention that this method is also adaptable to other models, something like the second order Kuramoto, which we are also using for describing electrical power grids. So going back to the physics or statistical physics, what we have done after solving these Kuramoto equations, we wanted to determine the characteristic time tau t. And so we started the runs from incoherent state, and the graph, you see the time evolution of single realizations, for many single realizations. In particular, you see R, this order parameter, which starts to grow and fluctuate, and after some time it can dip back to this 10 to the something like 10 to the minus 3, which is just the square root of 1 over n corresponding to the incoherent state. When the system dips back to this value, we considered this spontaneous synchronization, so-called avalanche, finished. And we measured the times of these avalanches and made a histogramming for 10,000 independent random conditions. Here the randomness comes from the omega I, the intrinsic frequencies of the systems. And the histogramming was done at the transition point, which was tuned carefully. And after making the histogramming, we obtained these distributions for different coupling parameters, 1.7, 1.6, down to 1.2. And you can see some power law tails of the durations of these desynchronization events. And you can fit power laws on the tails of these distributions and obtain the critical exponents. So just at the transition point, which is about 1.6, you got the exponent 1.2, but this does not agrees with the brain experiments, because the experimental values provided by the Finnish Palva group from 2013 gives you for this tau t a value between 1.5 and 2.4. The interesting thing that if you go below the transition point, you still find these power laws. And this is due to this disorder and the so-called frustrated synchronization subcritically. This we have already announced and published in the previous work. The new thing was in this collaboration with Gustavo Deco. He highlighted some points coming from experiments. One of them is that brain experiments are done with omega i's intrinsic frequencies greater than 0. And of course, we don't have in the eye rotating things, but just oscillating neurons. So omega I should be greater than 0. And also the distributions that are very narrow. So we have a very low frequency oscillators according to the measurements. The mean value of the omega I is just 0.05 and sigma is just 0.02. But fortunately, it turns out the Kuramoto equation can be rescaled, because the Kuramoto equation is known to have exhibit a Galilean invariance in terms of this omega I velocities of the angles. So if you rescale the omega i's by a factor of a, you have to rescale the time and the couplings, and the results which we obtained earlier could be valid even for this low frequency range dictated by the experiments. That is a very good thing, because if you want to investigate directly this small omega i's you would need a very strong couplings, and the stability of numerical solution of the Kuramoto equation breaks down and makes the problem very unstable. But with this rescaling, gauge invariance, you can solve it much easier. Another thing was that we can have a stochastic noise. So we added Gaussian distributed annealed noise to the Kuramoto equation, and we were curious what happens to the solutions in the presence of this stochastic so-called annealed noise. And as the figure 4 here shows, it turned out that this weak, if we have a weak stochastic noise, it can have a very negligible effect on the distributions. So you have the no noise points, and which is the blue ones, and those which have a small amplitudes of additional stochastic noise, and the distributions do not really change. So it means the stochastic noise is not relevant. And we published the results in arXiv, and it will appear in Journal of Neuroscience soon. So finally, let me summarize the results. Jeffrey implemented the Kuramoto ordinary equation solver, which is running efficiently on GPUs, even in case of sparse random graphs. My experience was on a Mare Nostrum 4 machine, which is in Barcelona Supercomputing Center, is the following. This is a huge supercomputer which has IBM Power 9 CPUs and 4 V100 Volta GPUs per node. So it's a very fast machine, and I could measure a speed up of something like a factor 100 with respect to my CPU runs at home on my machines. So it's very remarkable, and it allowed us to show the effects of weak thermal fluctuations, something like in a visit of 2 weeks in Barcelona. And we like to acknowledge support from the HPC Europe C program, also from OTCA, and the publication in Neuroscience is scheduled. We want to give a technical paper with Jeffrey, and a continuation to study on a connectome of the fruit fly is founded. This has an importance because this only have 40,000 nodes, but these nodes are exactly determined, unlike the ones which we used, which were obtained by tracked racing algorithms. So it's not fully exact. So thank you for your attention.
Thank you very much, Geza. I'm asking the audience from outside for questions. I cannot see anything in the chat box, but there might ask some. Anybody else from inside? This is a rather technical talk. Not really. So maybe I can ask just a simple thing that finally for this calculation you are using your own devices or the laboratory devices or the Wigner cloud. So which is the most efficient for this?
Finally, we used both the BSC Mare Nostrum supercomputer and the NEF supercomputer in Debrecen 2 in Hungary. Used both of these huge machines. we didn't use the Wigner GPU system.
Okay, so maybe you can have a look for the forthcoming new devices which Joska mentioned in the beginning of this program in the morning. Okay, anybody else?
Thank you.
If no, let's thank Lisa again, and then let's go for the next speaker, which will be locally again. And let me see. So, Gábor Daniel Balogh, algorithmic differentiation of structured mesh applications. Take this one. Okay, it seems. Okay. It seems locally working. Shall I turn over the... Is it visible now?
Nem látom, nem, az látható, hogy kicsit még fordítsd le. Erre? Arra, hogy az egész slide benne legyen az. Még nagyon... Pillanatot kérek még.
So these technical things make life complicated, but yes. And we are setting. We hope you see the slides as well, and the speaker, and please, and action. Please.
So, hello everyone, my name is Gábor Daniel Balogh, and I will talk about algorithmic differentiation of structured mesh applications. So, algorithmic differentiation is a set of techniques to evaluate derivatives of a function defined by a computer program. And why do we need that? So, a lot of numerical methods require derivatives, and there are three major ways to compute derivatives. We can use finite differentiation, which is can be a bit easier to implement, but in some cases it's too slow and does not give exact derivatives. We can use symbolic differentiation, but again, that may not be applicable for some programming constructs. And so algorithmic differentiation promises us the exact solution, and it promises it will be fast, which means that the evaluation of the derivatives will be comparable to the evaluation of the original program. So let's take our program as a function that takes some input and generates some output in another space. So we want to compute the Jacobian of the function. Well, at least the part of the Jacobian, where every element of the Jacobian matrix is the derivative of some output with respect to some input. So how do we get there? The thing that we want to try to do is consider f as a composite function with k functions. And from that, we can write the Jacobian as the product of the Jacobians of the composite functions. And here comes algorithmic differentiation, which computes the action of the Jacobian to some variable. And there is two cases. The forward mode AD computes the action of the Jacobian to a vector in the input space, which means the action of the Jacobian with a vector in the input space. And the backward AD computes the action of the transpose of the Jacobian into into a vector from the output space. And the second case that we will be dealing with today. So we want to compute the action of the transpose of the Jacobian. And we want to compute it as a series of basically matrix vector multiplications. So the trick is that we want to choose the W vector in the output space in a way that it will have only one non-zero element, and if we choose it to be 1, that non-zero element is 1 and all the other elements are 0, then the action of the Jacobian, transpose of Jacobian to this vector will be a row of the Jacobian matrix. So, and if we can do that matrix vector multiplication, then we have the Jacobian. So it won't be that a great deal, but we can evaluate from the right to the left. So we need only one Jacobian matrix of one subfunction at a time. The catch is that to compute the Jacobian of Fi, we need the state of the program at the point where we evaluated Fi. So there will be some trickery there. Commonly, backward AD implemented with operator overloading. So basically what they do, they create wrapper classes and overload all the operators, so addition, multiplication, and so on. And then the backend basically registers all the operations that done on the type itself. So this leads us really simple Jacobian matrices. But the catch is that we register each and every operation separately, which will lead a really huge control flow graph, which is hard to deal with and consume a lot of memory. So this is the point where we want to improve a bit with our approach. And for our background, we do implementing and developing domain-specific languages for high-performance computing applications. The motivation there is that we have a wide range of applications, and from year to year, there are newer and newer hardware available. And it is basically just unfeasible to port each application to each new hardware. So the idea is that we hide the platform-specific details of the parallelization from the developer into a library or of some kind. And this way we ensure future-proof and performance-portable implementations of the high-level application. And in this talk, we talk about structured mesh applications, which means that all the applications are operating on some sort of grid, like in the right-hand side on the slide. So OPS is a domain-specific language embedded in C++, which means that from the user's perspective, it's just a library with high-level application calls. We can define blocks or grids, we can define data on these blocks, and we can call loops over these blocks with accessing data on the blocks. So the application developer has to form their application in terms of these operations on the high level. And OPS will take the code, and at compile time it will generate a parallel implementation for each hardware that the user wants to run the code on. So the question is, how can we do AD with OPS? And the first step is to note that each computational step, each computational loop has to be a call to OPS bar loop, which will be the implementation to that function will be generated at compile time. The OPS bar loop takes a function pointer as parameter, which is the loop body, which will be called for each iteration, for each grid point. and it will get descriptors for the data sets that will be passed to the function. The descriptors contains the access type for that data, so whether it will be read or will be written, and the stencil to describe the access pattern to that data set. And from these data, OPS can generate the parallel implementation for the loop. But from only this information, can it do AD? Well, we're still missing the Jacobian for the loop body. But if we have the Jacobian for the loop body, let's assume we have. For the current application, we can use Stepanate to use source transformation to generate the derivative, which can be a bit buggy sometimes, but for the measurements we implemented the adjoints for the derivative loop bodies ourselves and feed it to OPS as well. So if we have the loop bodies, then we can generate code such way that we generate a parallel implementation for the primal code and the parallel implementation for the derivative function. And we can formulate a chain of loops at runtime, and then we can reverse the chain, so we can perform the derivative loops in reverse order. So we are almost there, but we're still missing two features. The first is that we need to feed the intermediate states of the primal code to the derivative functions. And the second is that we need to reverse the data flow, the data dependency inside the loops. So for the first problem, we are the ones that generate the code for the parallel loops. So we can generate code that just takes copies of each data that will be written. So that's basically what we do. We created a new data structure in OPS called tape, where we store the chain of the loops, and we store all the data that will be that is overwritten during the primal code. And in the backward sweep, when we compute the derivatives, we call the derivative function for each loop, and we feed the data that we load from the tape as well. So that's solved in this way. And for reversing the data dependency inside the loops, OPS gets the descriptor for each data set that accessed in a loop. And OPS is kind enough to require that each of the written data must be accessed with the getter operation, which means that only the data that is corresponds to the current iteration will be written. And this way, it ensures that the primal loops, so the original OPS par loops, are trivially parallelizable. So we can we don't have to deal with race conditions in the primal code. But that's not holds for the derivative codes. So let's take an example. In the left-hand side, we have a kernel where we compute the mean of the surrounding grid points. So we will write the current point, and we'll read the surrounding 4 points in the grid. So if we want to compute the action of the Jacobian of this function, we read the derivative on the point that we are iterating on, and we will write the derivatives to the neighboring cells, which means that the nice gather computational pattern that we had in the primal will be a scatter on, which means that we cannot run neighboring iterations in parallel. So we have to kind of deal with this problem. And what we did was we had two approaches to deal with it. One is for CPU, and we take the easy way for GPUs. So for CPUs, we did red-black coloring of the iterations. Basically, we took the whole iteration range, divided among the threads, and for each thread we had the domain, and we had to use a red-black striping inside these domains, in a way that each thread will execute the left-hand side stripes at the same time in serial manner inside the domain of a thread. In this way, there will be so the iterations will not write the same data. We define the stripes in a way that this is ensured. And then we have a synchronization, and then each thread will execute the red stripe as well. So this way, we have one synchronization point in CPUs, and then again we can run the iterations between the synchronization points in a parallel manner. And for CUDA, we take, as I mentioned, we take the easy way. So we overloaded the operators and used atomics for the computations, which we will see that this might not be the best way, but the current implementation does this. So for performance on CPU, we get the derivatives under 6 times as much time as we evaluate the original function, which is quite a nice result, since the theoretical optimum on operation numbers is, I think, 4. So we can say that we can compute the derivative with 4 times as much operations as for the primary pool. But we will have a little bit of overhead with all the storing and loading data. Yeah, so the CPU performance, I'm quite happy with it. But for the GPU, on our naive current implementation, we take a little bit more time. So to compute the derivatives, we take from 10 to 25 as much time as to evaluating the original program, so the primary code, which is quite a lot, I think, and we have some ideas where to go from here and how to optimize this to get closer to the prime node. Yeah, and we have another big problem with the current implementation, which is the memory requirement. So, as I mentioned, to compute the Jacobian, the action of the Jacobian for each intermediate function, we need to feed the data in the same state as it was performed in the primer run, which means that we currently store each intermediate state, and we can see in the table that it can explode quite a bit as we increase the iteration number. So, for example, the primal implementation, the only function takes 200 megabytes of data to do the simulation, and we will get 200 iterations, and we will have a tape with more than 20 gigabytes of data, which is quite a lot. So this kind of kills the current implementation, but our plan is to introduce checkpoints into the implementation, which means that we don't save each intermediate state, but rather just a few checkpoints of the states. And from those checkpoints, we can recompute every intermediate state, which of course will increase the runtime of the computation, but will drastically decrease the memory requirement. So in conclusions, we started to implement adjoint API for OPS, and we showed that we can parallelize the computation of the derivatives on both CPUs and for GPUs as well. And we have quite nice runtime performance on CPUs and not so much nice for GPUs at the moment. And we have plans to reduce the memory pressure of the current implementation. And thank you for your attention.
Thank you very much, Trevor. It's time for questions. First from outside? Anybody? Nobody from here? Of course, I will have questions. One of the things that, as I understood well, you can only use this for functions which are not coupled. So you have to have independent step-by-step functions. Otherwise, if you have a coupled things, then it makes life complicated, and you cannot really provide a proper separated checkabilities.
You mean the functions of the decomposition are independent? Yeah. So we use the functions as interchangeable with loops. So we have a series of computational loops that are independent from each other, and we take the derivative, the Jacobian for those loops. Yes.
The other question is related to the memory problem. So I'm not fully understand all the steps, but what I can see that in some cases you can have a very block diagonal or not, maybe not diagonal, but blocks in your problem. So should it help to find where the blocks are, and then based on that kill out the rest of the zero elements? Shouldn't help?
Yeah, so I think I got this question before.
Maybe I'm wrong.
So yeah.
I just had the feeling.
Basically, we see the derivative of the output at one point, and we will propagate the derivative from that point, which means that for a few iterations, we will have a lot of zeros in the derivatives. Which, if we do lazy execution and we know which point we will seed, then we can reduce the memory usage at that point. But for
maybe just like reducing the whole matrix.
Yes. But for now, we do the checkpointing at the same time as we evaluating the primal function, and we will need the result of the primal function before we see the derivative. Therefore, we don't know which parts of the matrix can we eliminate at this point.
Okay. Anybody else? Further questions? Nothing. Okay. So let's thank Robert again, and let's ask the next speaker, who is also a local speaker, and Balin Chidoshi will speak about bitwise reproducible execution of unstructured mesh application. As you are super clever using the same topic. Thank you. Please.
Hello everyone, I'm Balin Chidoshi, a PhD student of the Pazman Peter Catholic University Faculty in Information Technology and Bionics. And in the following few minutes, I would like to share our work about how we achieve bitwise reproducibility over unstructured mesh applications. First, I will introduce the problem, or the source of the problem, which we want to address here. Also, I will talk a little bit why it is important to, or why is it useful to solve this issue. Then I will introduce this OP2 DSL, which is really similar to the previous OPS DSL, but I will tell the differences. This is where I implemented, or we implemented our work. Then I will introduce our main strategies, how we wanted to solve this problem, and at the end I will show some numbers about the performance. So one problem comes from the IEEE 754 standard for floating point representations. This standard defines behavior for floating point numbers, correct behavior for most of the operations, but also it introduces some roundings. So for example, there is a little example. I just searched for Google's calculator. I entered to add 1 billion and 0.001, and to the answer again 0.001, and so on 10 times. I received the different outputs. Then I would do first the little parts together, add them together, and then add 1 billion. That's a different answer. Most of them kind of correct. We can accept it with some error bound, but they are different. Until now, we use these representations. This is one of the most popular ones. And still we relied on our results. They were correct, but always with this error bounding. But in a parallel environment, this different final output can really become with this difference. Because in many cases we have no guarantee about in what order we will execute our applications. So in industries, there are some areas where it is really important to have exactly reproducible final outputs in a program. For example, in aircraft turbine design, it is necessary, or there are other places, for example, in algorithm trading, where it is necessary to reproduce all results by some organized by some law enforcement things. It is checked by regulators frequently. But from the developer side, it can be really useful to have reproducible programs, mainly in debugging. For example, if we have an error once we want to examine what happened, then it would be useful to reproduce the same error again. And also, when we handle parallel applications, it is a really common technique to check whether we have a correct parallelization technique to compare the outputs to a one-threaded non-parallelized run. And if they are the same, then our method is correct. So far, we use this error bound. We check the numbers. It is in the error bound. It is fine. It would be much better to have the exact same final output at the end. There are some already existing approaches, but all of them has a price. For example, there is this Raptor project. They have a bin representation. They introduced a whole new representation for the numbers. But they introduced a 5 to 9 and floating point operations awareness, which can be accepted in some cases, but it is really general way, easily can be used. There is another solution in Flash, but that solution can be only applied for just one part of the application. Our solution is that we force such an ordering which can be reproducible in any time or indirect increments. Also, we have a method to force this reproducibility while we apply reductions, and this is even true when we run the application on different numbers MPI processes. But we have also a price. The application must fit into our domain. So as Danny mentioned before, we can define some applications on different type of grids. We have structured and unstructured. Danny introduced these structured ones. They have a logical indexing with implicit connectivity, can be really simply parallelized for GPUs, for example, or sometimes a bit more difficultly, but it is really nice in many cases. And we have unstructured grids. We have collections of different sets, nodes, edges, cells, and so on, anything. And we have an explicit connection between them. For example, we have mapping tables. defining that this edge connects these two nodes, and we have a list of these edges and connections. It is much more difficult to parallelize because if we check one element of this grid, we have no idea basically about all the other part of the grid. But for many interesting cases, the unstructured meshes are the only tool which can be used. In our research group, we try to help other researchers, as Danny mentioned again, that a physicist, a biologist, or anyone else who would like to make a simulation, he does not have to care about the low-level implementation of the always changing hardware architectures, for example, and so on. We try to create a domain-specific language where the user must declare the problem which must be computed without specifying the implementation while using our language. So he must use domain-specific constructs in the declaration. And then he can apply automatic techniques or language, for example, and that generates automatically optimized implementation for different hardware architectures or with different parallelization techniques easily. So the OP2 is an open source project. It is based on the OP+ Oxford Parallel Library for unstructured solvers. Mainly, it is developed for CFD codes. It looks like a conventional library, but it uses code transformation to generate the parallel codes, and it also suffers support from not just C++. Here is a small example how we should use this library. In this example, we have this res kernel function, which is a really simple function. It can be defined on an edge or can be used on an edge, and this edge increments the neighboring cells value. This is what this simple kernel does. And then the user must write an OP loop call. They're defining some more details, which kernel function he wants to call, some names, which set elements he wants to call this function, and some other arguments with some access patterns. And then our library generates code. For example, this code is generated with MPI parallelization techniques for CPUs. Also with the kernel function as it was, we generate an OP loop for every code kernels. So here we have an OP loop address. We prepare some of the arguments. Because we use MPI, we distribute the graph into different parts. We need to exchange some data on the hello element. And at the end, it is just under the slide, but trust me, there is a for loop, which, well, the for loop is here, but the kernel code itself is under here, under the bottom index preparation, which calls the kernel function. Okay. Here is another example of the problem that we wanted to solve now. Again, a similar function. We have edges and we increment cell values from the edges. Once, for the first time, we have such an ordering that the cell is incremented from the top one, then from the right, from the bottom, and from the left side. then there is no guarantee that it will be the same. Next time, the edge 0 will be run first, then edge 1, edge 2, and edge 3. So we can have a different, we can have a different final output here. For this, our solution is a little bit to swap the execution. First, we iterate through all the edges, as we did before. We calculate the increments, which in this previous case was really simple, but in some applications it can be more complicated. So we calculate the increments, but we do not write it into the style. We do not apply it. We store it in a temporary array. And then later, we go through all the styles, and for each style, we gather the increments values from the neighboring edges by using the original global indices. This is the one common seed which we have the same always. So we use these indices, and then we can apply the increments in a fixed order each time. Another thing that we had to solve is reduction. If we have multiple MPI processes, which can be different number of MPI processes, of course, we might have functions which want to apply reduction. So far, we could have different final outputs. We we apply the reduction within each processes, and then we added them together. It can be different. What we done here is a little bit of cheating, but it works. We applied the Rappleblass project's build representation for this reduction part. They have their number representation, which will be reproducible with the overheads, but this overhead is acceptable in this case. And we have same final outputs. Another problem which came up that in some cases the applications have some read-write access methods. So far we had only increments. We wanted to increment, so we calculated the number and we wanted to add it to the goal element. Now we want to read it first and then calculate its new value and then write it back. So we really have to apply the kernel on the executed element. Temporary storage is not enough. What we do here is we apply a regular coloring scheme, which we have before, for the race conditions, and that can solve this problem. And the question is how we can achieve this coloring to be always the same, even if we have different number of MPI processes. There are two solutions. The first one is the easier one. We color the full mesh on one process. So first we need to run our application on one process. We color it with a 3D algorithm, maybe. Then we save this coloring. And next time when we run a different number of MPI processes, then we load this already calculated coloring, which will be definitely the same. Another solution which might work is if we can develop an algorithm which can generate the same colors in a distributed graph, started from different points. So we from each MPI processes, then it might, well, it definitely would be better. There is a trivial solution for this. If we give to all elements as a color its own global ID, but if we have millions of elements, then it wouldn't be really efficient to have millions of colors to run this one. So solution one is working. but for this, the whole mesh must be able to fit into the memory. And also, we need to run it first to generate the colors. Yeah, on the second version we are working. If you have any suggestions how to find such an algorithm, I'm really open to discuss it in later, maybe to work together. For testing these methods, we set up two environments, one for the CPU-related test, one for GPUs. For the first, we use 4 Intel processors with 16 cores per processes, so 64 processes altogether. For GPU-related tests, we use the DGX station with 4 NVIDIA V100 GPUs. We used now 3 mini applications. The Alpha is a very simple finite volume CFD code with 3 different mesh sizes. Aero, which is a bit more complex, also with 3 mesh sizes, and MGCFD, which is similar to Alpha, but it has a multi-grid structure. And here we can see the runtimes. Of course, we must have some overhead because we do extra calculations. So always we must be aware. These are the runtimes of the different methods compared to the original, the non-reproducible methods. What we can see here is that, for example, on the CPU version, this is the top graph, the LRO application is computationally much more intensive. So the extra communications are smaller compared to the core runtime of the application. And on GPUs, sadly, we have really big overheads so far. And also, we have a few ideas how to get better, and we are working on this part too. Yeah. This is what I wanted to share. If you want to contact us anytime, you can find us on these links. And thank you for your attention.
Thank you very much, David. Questions from outside? Online sleeping is a very difficult thing. We have so these OP libraries are generative code, actually, so they are like preprocessors or
yes.
Like the C++ preprocessor, or so they use macros, or
they use
macros. They use macros.
No, they are source translators mainly.
Okay. So they precede the normal C++ compiler.
Yes.
Okay. Further questions? I would have one. So maybe this is a naive question, but do you have a limitation on the number of colors, or how is it? How it will makes the life more difficult if you go with the number of colors to infinity?
Well, it makes we just have less opportunity to parallelize. Mm-hmm. So if we have fewer colors, then it means that we have more elements with the same color. Mm-hmm. And if elements have the same color, then we can execute those elements at the same time. Okay. This is how we try to parallelize it. And if we have the same amount of colors as many elements we have, then it means that we cannot parallelize anything. Okay. Yeah. And this is why we want to get to that.
No, what I mean that I cannot get the last figure of this. So do you have this? This is not the one I was thinking of. Okay. Anyway, so do you have such a performance plot where you changing or restricting the number of colors for a certain, basically which are the number of parallel stuff, and then you see that how it performs depending on the airflow or the other mode.
Well, we have two options. What we try to do here with this coloring method.
Mm-hmm.
First is we color the whole thing in one go.
Mm-hmm.
For that, we applied a greedy algorithm, which is really efficient. So it already have, I'm not really good now with the math, but as many colors as the biggest degree or something like that.
Okay.
So that is not a really big number. For the other one, we want to have something, but so far we do not have anything. So we never tested this, that we say we have a maximum amount of colors, because we were not able to generate colors which are less than the number of elements. So, yeah.
Okay. Anybody else? Okay. Thank you very much, Valin. So now it's time for both virtual and real world to have coffees in order to continue with the next talk after the coffee break, which will be starting from like 4 o'clock in 5 minutes. So let's make it quick, because we would like to take the
Yes, I'm here.
Okay, Cimbi, te működsz, ugye? Visszarakunk.
Szerintem igen, megnézem most akkor.
Jó, éppen kirakunk. És azt nézd meg, hogy ez így most jó, kb.
Pillanat.
A kép az előfelé jó.
Ez jó, nem?
Igen.
Oké, köszi. Szuper.
Don't issue one. Azt most az összes kintről megy már, ugye? Igen.
Jó, de nem. Elég nem próbáltuk. Ja,
Most vagy Cindy, can you hear us?
Yes, do you hear me as well?
Or if you can make it more louder.
Okay, I try to be louder like this.
No, it's okay. I know your voice in real life, so get covers to that one.
Okay, I try to be louder.
Welcome, Zoltán Cimborás, who is a member of the working at the Wigner Research Center, and he also key member of the Hunkutec laboratory and QU Hungary. So Zoltán will talk on the current status of quantum computing. So please.
Thank you very much, Gergely, for this nice introduction and invitation. So it was a pleasure for me to hear all these talks, and also including two quantumish talks, which will actually help me. One by Peter Domokos about the Hungarian Quantum Technology Initiative, and also this new Quantum Informatics National Laboratory. And also Alberto's talk will be very much related to what I'm saying actually. I will ask the same questions, but from a completely different angle. And actually, of course, in a 35-40 minute talks, it's completely impossible to give a deep introduction into quantum computing. So the GPU laboratory did last year in their series of modern scientific computing lecture series, together with me, we made a complete lecture series about quantum computing, where at least we could cover some of the ongoing things. And this year, Gergely had the idea that we might also have a satellite event for those who are interested in more in the deep or more advanced knowledge. So because of that, we decided that my talk should be more like a general talk about quantum computing and the current status of quantum computing on a an overview type of talk, not too deep. And then there will be, of course, a talk by Dani Nagy from Wigner and Ericsson, who will talk in more detail about quantum machine learning that touches also on Alberto's talk a little bit. And tomorrow we have this event, this satellite event to the GPU days, right after, or almost right after the end of the GPU day. So we start at 1 p.m. You can register at that homepage, and I also give there like a little bit introduction to our organizations and other organizations that are teaching people quantum programming. This is Q World, and also we are involved in Q Hungary. And after that, there will be 3 proper talks. One will be a demo talk by Ákos Budai and András Pályi from the Technical University, where they show like the elements of a quantum programming language Qiskit, and they will also run an online accessible IBM quantum computer. And then there will be a talk from János Asbolt from also the Technical University / Wigner about Google's quantum supremacy experiment, and the talk also by András Guillén about new type of classical algorithms that actually were realized only after the quantum version was up. I mean, typically there is this Netflix algorithm that was actually shown that there is a quantum algorithm that is exponentially faster, and then people looking at it and trying to show that quantum is always exponentially faster in this respect found actually a faster classical algorithm. So it's this type of quantum-inspired classical algorithm. So because of this, these will be like these 3 particular talks. If you are interested, just come. And right now, I'm only giving an overview, and the next talk in Dani will go a little bit deeper into quantum machine learning. So of course, you are all aware that there is a huge hype on about quantum computing. It's all in the news since, well, I would say maybe 2013 or 2014. And one of the biggest news was that I would say there were two big news. One was Google supremacy experiment, which was actually, I mean, IBM is saying that it actually didn't show a supremacy. I will slightly mention it, and tomorrow Ashby will talk, János will talk more about this. And also the other one is those online accessible quantum computers. And of course, since there is this much buzz, of course, politicians are also talking about this. And these are actually three very important pictures, I think, that shows well the world situation. In one, there is Trudeau, and who is going to the Institute of Quantum Computing, IQC, in Canada, Waterloo. Actually, Canada invested heavily in quantum computing already 10 years ago. So they are very, very well off. And of course, he was super proud when he gave a talk then, like 2 years ago. And on the other hand, Europe, at least in making like many qubit quantum computers, are lagging behind. And this is also very interesting that now they are trying to catch up. So this is a picture of Angela Merkel, who actually made a decision, or the government of Merkel, of building together with IBM to join German IBM quantum computers. And beside that, Germany will build one more on its own. And there is also a European initiative, Open Supercube, beside that. And also, following the Trump joke of Gergely in the first talk, I also have to show the third one, which was Ivanka Trump's Twitter post, where she announced that quantum supremacy has been reached in a collaborative effort. Look at the order by the Trump administration, Google, and the University of California, Santa Barbara. Okay, so what is the structure of this talk? I will give you a very, very short physicist view on what quantum computers are, and perhaps what quantum computers are good for a little bit. Then I will give a little bit more deeper and perhaps not that conventional view about what the current stage of quantum computing is, although I would say it's still the main view what I'm going to tell you. And since there are many companies coming to this event, I also would like to stress that actually right now within quantum computing, there is a huge surge in collaboration between different fields of science and technology and companies and research institutes and universities, and I want to talk a little bit about that. And then the involvement of Hungary in quantum computing, although I will only slightly touch upon that because Péter Domokos already gave a pretty good overview of that. So, of course, if you're a physicist, you know that quantum physical and quantum chemical problems are intrinsically hard. I mean, if you want to like find the ground state of a molecule, like with many atoms, many electrons, to do it like even numerically, explicitly, it's very, very hard. And what lies behind that actually of this intrinsical hardness is that it's basically the principle of superposition and something that basically follows from this quantum entanglement. And what does this mean? This means that if we have some physical quantity, okay, say the magnetic dipole moment of an atom that can be nucleus that can point upwards or downwards, then in fact in a quantum mechanical state space, you can take the linear combination. So it actually always the state space is basically a linear space. It's so that's very different from our ordinary state space, which are usually like discrete. I should also mention this, that computer scientists, just from theoretical point of view, have actually almost come to similar mathematics when they describe something called like the linear logic, when logic was not like of discrete object, but also from like a linear space, like the truth contents of logical statements. And why is this a special issue? Well, in the case when you have one qubit, like 0 and 1, and as Peter mentioned, then you can take a superposition of those two in some way. It doesn't matter too much, but suppose you would have like 5 qubits. Then what will happen is that a state, at least a pure state of a physical system, can actually be described by a linear combination, complex linear combination of 2 to the 5 different objects. Like, of course, like let's say, as I told you, that we are talking about the nucleus and like, let's say, a quantized dipole, magnetic dipole moment of the nucleus that can be either upwards or downwards, and let's call the upwards 0, downwards 1. And then if you have 5 of them, then of course you have all the 2 to the 5 combinations, like 0, 0, 0, 0 is when all of them is up, and so on. 1, 0, 0, 0, 1 is down, the others are up, and so on. And describing that state, you would need actually more or less 2 to the 5 complex numbers. And of course, it's still okay, not so many, but we know from the famous exponential wall picture that this gets really bad when you go to the 40s, 50s, 60s. So still, for example, here you can still depict, if you depict in billions, which you can still imagine in some way, how far you could go with let's say 2 to the 33. But when we go further and further away to 40s, 50s, 64, then it becomes very challenging to show this. For example, on this picture, if 1 would be 1 billion, that exponential wall. And that's also what is the moral of the legend about the inventor of chess. And actually, there it plays a very, very big role. This 64. It was very smartly chosen, because if chess would have been made of 32 squares, maybe the inventor could still get his prize, but it was unfortunately more, and he got killed. You remember the story. He asked only for a grain of rice on the first corner, then 2 on the second one, 4 on the next square, and doubled. And after 33, you have 512 giga of grains, but after that, you don't want to go. So, and actually those numbers like 40, 50, 60 comes up exactly when we are talking about quantum supremacy, about, for example, the Google experiment. So as I told you, you have to have those, if you have these 200 qubits, say 200 atoms with magnetic dipole moments either pointing up or down, you would never be able to store on a classical computer the generic state of 200 of these, so of 200 qubits. So that already shows that there is something difficult in simulating quantum physics. And of course, this was what was realized by Feynman. And I'm not giving the quote because also I'm a little bit tired of it, and so everybody is giving the famous quote of him. So in this talk from 1981, which also got into press in 1982, that damn it, nature is quantum mechanical. You need to simulate it quantum mechanically. Instead, I'm going to give another quote, which I think is a little bit deeper. How can you simulate the quantum mechanics? Can you do it with a new type of computer, a quantum computer? Here the word quantum computer appears for the first time as I know it. It's not a Turing machine, but a machine of a different kind. So from the physicist point of view, it came up as something natural, like if we could somehow make a quantum mechanical system to work to calculate for us, then we could simulate other quantum mechanical systems. But then came a surprise, exactly because mathematicians took up the challenge and computer scientists, and actually they also say that also some classical problems could be solved by quantum computers. And I don't want to dwell now too much into these classical or orthodox aspects of quantum computing. Just let me mention quickly 2 things. One is the famous Bernstein-Vazirani problem, which András will talk about more tomorrow. but it shows somehow the strength already of quantum computing. Namely, suppose that you have a secret bit string which is contained in a mystery black box, and you are giving another bit string. And then what you are doing is that you are multiplying the first bit that you are putting in with the first bit of the secret string, and the second bit that you are putting in with the second string of the secret bit string, and so on. So like 0 times 0 is 0, 0 times 1, 0, 1 times 0 is 0, 1 times 1 is 1. And you just add them, these, modulo 2, and then give the output. And then this output you are giving out. And then you can ask, how many queries do you have to do to determine the secret bit string? And actually, obviously, as you would guess, you need n number of queries. Basically, you have to put in the bit string 1, 0, 0, 0, 0, then you get out as 0, the first secret bit, then 0, 1, 0, 0, 0, and then the next one you get out, and so on. And there is no better way. In a quantum mechanical way, as will be shown by
Can you hear us? We have a connection break. Something happened.
I'm sorry, there was a family interruption. Sorry for this. Now you cannot see me, so I just stop the video, okay? So the Bernstein-Vazirani algorithm, and András will talk about this, where you actually only need one shot for getting out the secret bit string. For the case of the Shor algorithm, it's another very orthodox quantum algorithm where you can actually show that you can use it also for other tasks quantum computers could use. This was in like more than 10 years after Feynman's famous talk. As the best classical algorithm that factors composite number into prime is actually has to take exponential number of times in the, well, 2 to the n square root of n time, where n is the number of bit described by the, which we describe this big composite m number. So it takes exponential number of time, while the quantum algorithm takes only a polynomial number of time in the number of bits. Okay, so let's come to the title question. What is the current stage of quantum computing? Well, we have come a long way from Feynman. And actually since 2016, 2020, there has been like a commercial boom. Like it's of course a speculative boom, but many things have happened that, in particular, I would say an important thing has been that they are building bigger and bigger quantum computers in the number of qubits, and also the gates and the qubits are becoming less noisy. And so here we can see like before Feynman, there was only one proposal which was not about quantum computation, but how quantum mechanics could be an important asset for cryptography. It's Stefan Wiesner's quantum money proposal, which is basically very close to the Bennett-Brassard cryptography proposal, but on the quantum computing level, basically there was this Feynman's proposal, which was coming from physics, and then in '94 there was the Shor algorithm, a lot of classical algorithms. And then, of course, people realize that one has to, that the qubits will be noisy, and one should do error correction. And now there is a scheme for quantum error correction, which is pioneered also by Google, and well, John Martinez was at that time at Google. And one more thing which is very, very important is the supremacy experiment, which I will talk about. So, I mean, there are many potential platforms for quantum computing. So when we are talking about qubits, one which is used by Google, IBM, and also many other companies like Rigetti are the superconducting transmon type of qubits. They have good scalability, rather good controllability and coherence times, although the crosstalk error are big. One that I should want to mention are trapped ions, which has also super good, even better coherence times, even better controllability. The big problem there is scalability, how you put in more and more trapped ions into one trap. Actually, what they want to do now is to have more and more traps, and they somehow, by a micro wave communication, they do coherent communication, so quantum communication between the traps, and try to entangle different traps like that. And one that I also want to mention is photonics. There also the coherence, if it's linear optics, is very good. The control is also very good. At the moment, scalability is not so good. However, it doesn't seem to be like a fundamental problem like in the case of trapped ions. Okay, so let's talk a little bit about the quantum supremacy experiment that János will talk a little bit more about. So this was done by well, actually by a 54-qubit quantum computer of Google, but one qubit didn't really work, so effectively it was a 53 qubits, where in a rectangular 2D shape, where they put after each other 20 layers. And actually, it was the algorithm what they showed. I mean, what does quantum supremacy mean? First of all, it means that you give a problem, and you can solve that problem in really in a way, you can solve that problem in a quantum mechanical way, or lifetime, or very quickly, in such a way that the problem on a classical computer would take really long time. So they estimated that that this strange task, which was the following: take this particular quantum circuit and then measure the outcome of the quantum circuit. What do you get? Well, you get a machine that samples from 53 bits. So it gives samples like 111000, so numbers like that. So it samples with respect to some probability distribution that the quantum machine produced. Can you make such a classical algorithm that can actually describe, like, let's say in a Monte Carlo or in a different way, make a similar sampler? And the Google scientists, they said that you cannot, and with the best classical simulator, you would need 10,000 years. I have to first of all say something here, that basically the state that came out is not really the pure state that would have been produced by an error-free quantum computer. Instead, actually, it's a mixed state, and you can imagine the sampling in the following way. It's a mixed state, and it's like white noise up to 99.9%, and only this quantumness comes into as a 0.1%, this pure state sampling. So you can imagine that out of, like, this sampler makes the following thing, this quantum sampler, it samples out of 1,000 experiments 999 times. Of course, you don't know when because it's probabilistic, from the white noise, like every string has equal probability, and only 0.1, like 1 out of 1,000 times, it samples according to probability distribution described by this circuit, or the pure state as an outcome of this circuit. And still, you cannot really simulate that classically. You would need, for such a sampler, it's still a very highly entangled state, by the way, interestingly, you would need a classical machine that would calculate it in 1,000 years. At least that's what they claimed, using a type of Schrödinger-Feynman algorithm of the Google scientists. Then IBM computer science suggested that maybe if you use some very tricky supercomputer in a very tricky way, could we go down to 2.5 days, but it's still unclear. Maybe they will at someday show it. On the other hand, I have to tell you that, I mean, if you go up to 60 qubits, then there will be no classical computer that can do. Of course, you can say that this task is not super interesting. And you might be right in that, but let me tell you something about this. So here, this probability distribution was not particularly interesting, but there are other ways of getting interesting probability distributions. For example, through bosonic quantum computing with a sampler called the boson sampling algorithm. There, the probability distribution could be obtained could be related to permanence of some matrices, and permanence of matrices are hard to calculate. And that has much more structure. And of course, if you want to do quantum machine learning, then one key ingredient in many machine learning algorithms is to produce some interesting probability distributions or learn some interesting probability distributions. And in fact, this could maybe not be done that efficiently by a classical computer, as classical computers cannot really produce that many interesting or that many probability distributions efficiently than quantum computers. I will come back to this point a little bit. So what is Google's roadmap? Actually, this picture that I'm showing was presented first just a few months ago, 1.5, 2 months ago, in the academic symposium or Google's academic partner symposium. But then they showed it also at other places. They tried to mimic John Fitzgerald Kennedy's approach to the moon, landing to the moon, who said that within the end of the decade, we will be in the moon. And that actually succeeded, that program. And what they want to do is that they want to build very similar to this, they want to build bigger and bigger superconducting quantum computers. And within the end of the decade, or before the end of the decade, 2029, they want to build 1 million qubit quantum computer. However, I have to say that these are physical qubits, and they will be noisy. So you can fight noise with something called error correction and do very perfect qubits. For that, with the good noise level, which is still not reached by the Google team, by the way, you could perhaps encode one logical qubit in 10 to the 3, so in 1,000 physical qubits. This would mean that 1 million physical qubits would amount to 10,000 logical qubits, but then they would be really stable logical qubits, so you could do any quantum operation. And actually just a few weeks after that, of course, IBM also produced their roadmap, and similarly, like Google said that in 2023, they will have already 1,000 qubits. That's what IBM also said, like 1,121. And they didn't put a date for the 1 million physical qubit one, but they just said and beyond, and they wrote 1 million qubits here. And if you go to PsiQuantum's homepage, you will see the same thing. It's a photonic quantum computing company, very successful. They also want to do, although they also don't put a date, build a machine with 1,000 qubits. And all the three are, of course, talking about fault-tolerant quantum computing. So using qubits that are protected against errors, and where the qubits can live very long and the gates are very good. But how can we reach that? Okay, so here you can see the number of physical qubits on the x-axis and the error rate of the two qubit gates, let's say 1 qubit and 2 qubit gates. And you can see that what they want to reach is this 10 to the 6 number of physical qubits, where you can actually do useful quantum computation, so quantum computation with 1000 qubits with error correction. But we are still not there. We are still not exactly at the, even at 100. I mean, maybe next year there will be some companies coming out with 100 qubits, like Google promised that, for example, in 1000. And although the error is small, it's not completely clear what kind of applications you can do. For sure, if you do quantum error correction, you will have too few qubits. And it's also unclear whether how long we will be in this shaded near-term application era, which is also sometimes called the noisy intermediate scale quantum device era, NISQ era. And if it's more than 10 years, we have to actually think about useful algorithms there. Okay. Okay. And if we think about useful algorithms in this current era, we have to like step away from those algorithms that I mentioned, like the Shor algorithm or these orthodox algorithms like a Grover search algorithm and the relatives. And we have to build algorithms for near-term quantum computing. And as I said, one of the best options for this is quantum machine learning. I mean, of course, you could first think about quantum machine learning that quantum computing is hype, machine learning is hype. You put them together, it's super hype. And it's also partially true, but also I would say that there is actually a deeper reason behind this. And the deeper reason behind this is the fact that right now what we can do is with quantum computers, better than with classical computers, is to produce samplers like probability distributions or samplers of probability distributions that you cannot produce those probability distributions by classical means. And thus you can learn using those in a better way. And in general, you can also perhaps do optimization in a better way. And both of these are related to variational or hybrid classical quantum computing, which has the following, which is illustrated in the following picture. Basically, what you are doing is that you are putting as much computational power to the classical computer as possible. What does that mean? So, for example, I go to the next stage. For example, suppose that this is a very typical algorithm, what I'm showing this called the quantum approximate optimization algorithm. And here you might want to calculate the so-called max cut problem, which means select those edges which select all those vertices in one group such that if you cut out those vertices, then you have to cut edges with maximum weight if you add those weights on the edges. And such a problem, if you want to calculate such a problem, or the traveling salesman problem can be also formulated like that. It amounts to finding the ground state of basically of a classical Ising model, and there is this algorithm that tries to find this called the QAOA algorithm, which starts from the so-called plus state, which is actually a linear combination of 0 plus 1. And if you take it in all of the qubits, what you get is uniform superpositions of all bit strings. And then apply up to some time gamma 1, first this Ising Hamiltonian, then you apply an X gate, which is basically flipping up to the X gate would be that it flips completely, but maybe you only want to flip according to some probability, like you make a small X rotation so that you don't completely flip the spin. So with beta 1 parameter shows how much you flip coherently the spin. So if beta 1 is 0, you don't flip it at all. If it's pi, you flip it completely. And you apply after each other these gates, these unitary gates that you can decompose efficiently into 2-qubit and 1-qubit gates, and then measure, and then maybe you get a good value for the or maybe a bad value. You can see what kind of ground state you get. So like you get a value for the optimization problem. And then with the classical optimizer, maybe using gradient decay or maybe some other method, optimize these parameters. So the classical computer has also to do a lot of things. And the hope is that you can actually use a path in the Hilbert space that you wouldn't have been able to do using classical optimization. So this is basically what variational computing is about for optimization problem. But you can also use this also for finding eigen states of complicated quantum Hamiltonians, and also for machine learning to produce very interesting probability distributions, for instance. So I would say that currently the best hope for quantum computing in the NISQ era would be, first of all, quantum chemistry and quantum physics using these variation algorithms, and similarly using variation algorithms, optimization, and machine learning. Factoring is not really in a NISQ era algorithm, but there have been serious improvements there as well, and there have been papers showing that it may be 8 million qubits you would be able to factor numbers that could break the RSA code. And of course, it's very important to have future ideas. And I will finish soon. Of course, many people are claiming that now quantum computing can have effect on everything in quantum chemistry, quantum simulation, quantum communication, quantum machine learning, and you can see pattern matching, protein folding, everything. And I mean, it's not true per se. However, I have to say that as the number of as the physical gate length in classical computers becomes smaller and smaller, I mean, quantum effects will be there inherently. So I mean, these classical computing paradigms maybe in 10 years or maybe later, but it will be over up to, yeah, well, it could be over up to soon, and then quantum computing must be really taken seriously, even for those who are skeptical of this, because there is no way out of it. But to me, make a more positive ending of the thing of this talk, I would say that actually online accessible programmable quantum computers became democratized actually quantum computing a lot. I'm also using them. I'm finding out new error mitigation schemes than other people use, and also startups can use this. Of course, multinational companies themselves build those things. So this time is a very good entry point for virtually everyone who is interested and who believes in quantum computing, and there is great software for it. We are at Wigner also involved in trying to write good software for actually photonic quantum computation. And what is important in this current stage is this collaboration across disciplines and across the academic and also company landscape. I mean, there will always be some domain experts who are coming that they want to have a solution for their problem, for, let's say, telecommunication or something else. And then nowadays we have to talk about if they want to have a quantum solution with quantum information scientists, and then go even deeper, like which hardware we should use for that, because as I told you, different hardware has different merits. For example, if you are good with shallow circuits, but you need many qubits, then you should go with superconducting qubits. there are plenty of those quantum computers around and they are building it. If you have to have deep circuits and you don't need that many qubits, let's say 100 qubits, but you need really deep circuits, many layers of 2 qubit gates, then you go with trapped ions and so on. So this is a great place. And of course, the premier workshop and conference for this is this Q2B since a few years. This is the practical quantum computing workshop, which also will be held this year. Now it will be online, where actually it's exactly about academia and companies discussing like which practical question can be solved in the near future by quantum computing. And maybe Peter already talked about this Hungarian quantum technology program. So I will not really talk about this too much. I'm just showing the partners. I don't know if he mentioned them. It's like we have here 3 academic partners, which is Wigner, the Technical University, and Ötvös University, and also the Energy Research Institute is also involved. And we have also industrial partners. In particular, I am, for example, collaborating a lot with Ericsson. Then also Nokia Bell Lab is a partner. Then Femtonics and Bonn, the company Bonn is also a nice partner. So I would like to end my talk with that. And I'm saying that if you want to have more particular, know more about more particular questions of quantum computing, about the supremacy experiments, about the demonstration of how to program IBM's quantum computers through the cloud, or about quantum-inspired classical algorithms, then please come to our site and sign up for this satellite event. Thanks a lot.
Okay, Cindy, thank you very much. And it was a very nice introductory and even deep talk. So, is there any question from outside? I can't see. I cannot see in the chat. Anybody else? Somebody from here, locally?
So it's completely dark here. I have to turn on the light.
You are in the dark. Arpi would like to ask something. Arpi, please go ahead.
Yes, about Moore's law slowing down. I would like to ask if you know the reason. So is it a technical reason, or is it just because there is less money in it, because the present computers we are using do what we want for most of the people willing to pay for it, so they don't buy new ones?
So look, I mean, you can say that there is a commercial reason behind this Moore laws in general, how it evolved and how it goes. But I mean, if you look at the size of one single gate, I mean, it's so small. I just depicted them. I mean, the quantum effects are there, right? I mean, if you go even to a smaller region, how can you avoid it? Like, I mean, physically, that classical computing, the usual way to have definite bits and so on, that the quantum noise, I mean, if you can call it, it's for the classical computer scientists, this noise is not present. How would you be able to avoid that? This is my question. Like, I'm asking this back. Do you want to build bigger devices?
What I was asking is, how far are we with the present computer from the quantum limit? So my feeling is that we are pretty far, because I mean, the present CPU is quite hot, so there are huge thermal noises, and still it works.
Yeah. Wait. Of course. I mean, look. I mean, the thermal noises are there, but if you go to smaller and smaller regimes, of course, the thermal noise will also you will also have issues with that. I mean, what I can show you are what I showed you here. Maybe I can share it again. Are the wait, how can I share it? Or the gate how big this one gate is, or one wire here. I'm sharing it, sorry. So maybe you are far away, but how far away? I mean, would you say 10 years? I mean, here you can see physical gate length in nanometers. I mean, nanometer is already the scale where quantum effect starts to become relevant, right? So, I mean, they showed it what happens until 2030. Of course, you can also have build bigger computers and make better software usage, everything like that. But I don't think like in our lifetime whether this can be avoided.
My question was more related to something short term, because what you're saying is that Moore's law has to slow down in whatever 2030 because we would reach something.
Mm-hmm.
But Moore's law already is slowed down in the previous 10 years. And that's what I wanted to ask, if the reason was reaching some technological boundary, or just that there is not enough commercial incentive to develop faster computers, because our present computers pretty much do it what the average users want to do, so they are not buying new ones. And if we already reached that point, then so my question was this, that
yes, so I don't know if I can give a very educated answer to this, because this was just like a small part of my talk, because I don't know what you can reach with technology. But for me, it seems evident that this has to come in. And I would say it would be strange if there would be not enough incentive to make faster computers, financial incentives. For me, I would find it strange, right?
Yes, I also would find it strange.
Excuse me, can I just cover this question, because we have to move on, because we still have talks and some time limitations. So I'm very sorry to cut this thing, but let me thanks again, Cindy, and let's move to the continuing of this. Actually, Arpi and Cindy, you can still discuss in the chat box. So,
sure. Thanks.
I'd be very interested in the final answer, but we have to move on. So please. So let me call next speaker, who is Daniel Noy, a student working on the GPU laboratory facility. Also, in this topic, Donnie, I can see your face. Can you share your slides and give some noise?
Yes, can you hear me as well?
Super, please.
Okay, so now you should see my slides and you should hear my voice. Is it the case?
Yeah, please go ahead.
Okay, so thank you everyone for inviting me. And my talk is as a follow-up talk after the ZIMBY. Let me introduce myself very shortly. My name is Daniel Nagy. I'm currently a master student at Eötvös University. I am also a student intern at Ericsson, and I am also researching closely together with ZIMBY. So this is why you see all the three logos here. I will talk about quantum machine learning a little bit in more depth. ZIMBY and Alberto also mentioned this topic, and I will talk in particular software environments which we can use if we want to do quantum machine learning research. So some of you already know machine learning in detail, but I wanted to remind you about how do we classify these algorithms. First of all, we have supervised learning, which needs a lot of data, and this data needs to be labeled carefully. Otherwise, these algorithms cannot learn the patterns. On the other hand, we have unsupervised learning too, which is designed to learn from unlabeled data. one of the most interesting algorithms are from reinforcement learning, which is when a computer or an algorithm tries to learn from the environment. So why do we do machine learning, quantum machine learning? Most of machine learning algorithms are composed of linear algebra and some non-linearities. And these non-linearities are essential in learning distributions. And quantum mechanics is inherently linear algebra plus measurements, and these measurements are non-linear and stochastic. And machine learning in general deals with probability distributions, which naturally appear in quantum mechanics. And this is why one should think about why don't we do machine learning with quantum computers. Also, as Cimbi mentioned, the dimensionality of Hilbert space scales exponentially if we add more qubits. If you don't know what a Hilbert space is, just think of a linear space with complex over the field of complex numbers. And it was also mentioned that the quantum circuits can generate probability distributions that are impossible or nearly impossible to generate with classical computers. And from this, we might assume that quantum computers may be able to learn these distributions, such distributions that cannot be learned with classical computers. How do we classify the quantum algorithms, quantum machine learning algorithms? And here is a figure that is almost always showed when one talks about quantum machine learning. We have to compare the type of the data and the type of the algorithm. And on the upper left corner, you can see classical data and classical algorithms. This is every single machine learning algorithm that is used by Google and Facebook and all of you know CNNs and recursive neural networks and everything that is classical. Then we have CQ, which means that our data type is classical. For example, we have images of cats and dogs or galaxies or something else, and we want to do something with them using a quantum computer. The third one is when the data type is quantum and the algorithm is classical. Here we have, for example, when we have a noisy qubit and we want to apply some classical algorithm, machine learning algorithm to make them more reliable. For example, we want to use the toric code or other quantum error correction codes and decode the syndromes with machine learning algorithms. And the fourth one is when both the data type and the algorithm are quantum. And this is very interesting. Here are two papers I mentioned. One of them discusses how to use quantum autoencoders to denoise the quantum data. And the other one is how to use variational quantum circuits for quantum state tomography. Most of my talk, I will talk about supervised learning, and I will just remind you about how this works. So we have some data points labeled X, and then we have a model, which is an almost differentiable function. In classical machine learning, I mean deep learning. This function can be very complex, but it's still differentiable and is still parameterized by real numbers. And we evaluate this model at each point, at each data point, and we get predicted values. This can be classes or can be real numbers. And we have to define a loss function, which has to be a scalar. And for supervised learning, we also have labeled data. And the loss function takes the predicted data and the label data and gives us an error which has to be differentiable as well. And there is the gradient descent rule, which states that we have to update the parameters of this function with respect to this gradient and the learning parameter. This learning parameter can be dependent on time or can be dependent on the gradient, but in the most vanilla case of gradient descent, this is just a constant. How do we make all these quantum? Well, we introduce a very important step. We have to use this classical data and embed it into a quantum data. So make a quantum state according to the classical data. And this embedding process is a very important part because the performance of the algorithm depends heavily on the proper embedding. In most cases, we can use computational basis embedding or angle embedding or amplitude embedding, but I work mostly with continuous variable quantum machine learning, where the psi is not a qubit state. Instead of that, it is a q-mode state. And in that case, we have another embedding methods. And after we produce this quantum state, we replace the function with a unitary, which is a quantum circuit, and we measure the expectation value of some observable. And every single quantum circuit can be described with a unitary matrix, although it is a very big unitary matrix, and can be parameterized with real numbers. And another important thing is that we cannot measure the exact expectation value. We can estimate it with a number of shots, for example, 1,000 shots or 10,000 shots. And we have to replace the previous loss function with another loss function that takes the true values of y and takes these estimates of the expectation values. And this has to be still differentiable with respect to the expectation values. But the parameter update rule can be the same as in the previous case. We can use common optimizers like ADAM or RMS-prop or stochastic gradient descent. So this is what quantum supervised learning does in a nutshell. However, here is a big issue. We have to calculate the gradient of a quantum circuit, and this step is non-trivial, and it has its own literature. But basically, there are two different methods for calculating the gradient of a quantum node with respect to a parameter. And the first one is the parameter shift rule, which is very easy to do with a hardware. It is basically you have to evaluate the same circuit at two different points, and you have to take the difference between them. And the C and S here are finite parameters, which are looked up from a table. For every single gate, quantum gate, you have a different C and a different S, and in each point, when you want to calculate the derivative of that quantum gate, you can use this formula. When you cannot use this parameter shift rule, in those cases, you can use the finite difference method. Actually, there are three different types of finite difference. One is the forward, one is the backward, and this is what I shown here. This is a centered finite difference method. Okay, and how can we use this quantum machine learning? Now, the problem is that we have very noisy and very small scale quantum computers at this moment in 2020. but we have high performance classical computers. And the idea is that we should use quantum layers, and we can place these quantum layers anywhere in our model. So as you know, every single deep learning model is basically a directed acyclic graph, which consists of nodes, and each node has an input and an output, and you have to define the derivative of each node. When you can do this, you can basically arrange anyhow these nodes. And the idea of hybrid quantum machine learning is that you may define a quantum node for feature extraction and then use classical nodes as here in the center, or you can use totally classical methods for feature extraction and then use quantum machine learning, a quantum node for regression or classification, or use classical methods both at the beginning and at the end of the circuit, but you can use a quantum layer anywhere inside. How do we do this in practice? Now, fortunately, we have a very good software stack for doing this. You may also heard about Xanadu, which is a Canadian startup, and they have a very good software package called PennyLane. I use this package for work, but I have to mention that Google developed their own TensorFlow quantum package. Both of these are intended for quantum machine learning, and both of these algorithms are software packages are free and open source. So TensorFlow is a software framework for quantum machine learning, and PennyLane is an automatic differentiation framework for hybrid quantum classical computers. And the QoS Foundation made a very nice comparison between these two frameworks. The reason I use PennyLane is because I love PyTorch, and unfortunately TensorFlow Quantum uses only TensorFlow as a machine learning framework. But if you use PennyLane, you can use whatever PyTorch, TensorFlow, or Autograd. Now, PennyLane is a front-end language, and it can use backends, quantum backends, and most of the currently available quantum chips are supported by PennyLane. So if you are using PennyLane, you can test your code on Rigetti computers, on IBM, or Xanadu's their own quantum chip. Yes, and PennyLane is an agnostic approach that allows you to program in your own ML framework. And even better, if you have your own quantum simulator, for example, you came up with a very good idea on how to simulate a quantum circuit, or you have developed your own quantum chip, then you can write a plugin to PennyLane, and everyone on the world who uses PennyLane can use your chip without thinking about the details. Now, I prepared a little bit of technical introduction on how to use PennyLane. It is very easy to define a PennyLane, a quantum circuit in PennyLane. Basically, you have to define which kind of device you want to use. You can use a simulator. PennyLane has a built-in simulator called default.qubit, but you can use IBM's Qiskit, even the simulator or even the physical devices. And then you define a node, which is a quantum node, and it is basically a function where you define a quantum circuit, but this is a high-level definition, so it's completely isolated from the details of the quantum chip. You just define the circuit, and the PennyLane will translate these gates into the particular gates supported by the device of choice. And then you calculate the function and you get the result. But what is more important, then you can interface the code with PyTorch. So if you have an existing model, for example, you have a very good convolutional neural network, but you want to extend your network with a quantum layer, then you can define a quantum node just like before. You can also define the simulator, but here you can define the interface. So at this point, this quantum function accepts only PyTorch tensors as their parameters. So here theta and phi are PyTorch tensors, and the result is also a PyTorch tensor. And what is even more important, that Penny calculates the Jacobians or gradients for you in the background. You don't have to worry about calculating the gradients. You just call the Jacobian of this circuit, and then you can evaluate this Jacobian at any point in the parameter space. And after you are done with designing your circuit, you can define a layer and use it in your existing PyTorch model. For example, you can create this quantum node, you add some weights, and all you have to do is to specify the shape of these weights. The first parameter of the circuits in this case must be named inputs. And Penny is converting this quantum node to a layer, which is a fully featured PyTorch layer. And after you are done with this, you can use an existing model. For example, you can combine this with a simple linear model into a sequential model where the first layer is the quantum layer and the second layer is the classical layer. And you can evaluate this model at any point and calculate the gradients and use the optimizer of your choice to update the parameters. And finally, I brought you an example, which is actually from Xanadu's own website. They have made a quantum convolutional network trained on the MNIST dataset, which is a very frequently used dataset. And what they do here is take an image, and for each pixel, they encode this pixel information with a rotation embedding into a quantum state. And then they apply a unitary matrix, which is at first randomly initialized. So at first, at the beginning, this is a random matrix. And then they do the measurements and feed the output of these measurements into the classical layers. And in each step in the optimization, this unitary matrix will be improved and improved. And finally, you will get a model that converges to some 70% accuracy. What we see here is that it is not absolutely clear that the model with the quantum layer is much better, but at least it is not worse, or at least the same, or at least as same good as the without quantum layer. So the challenges and open questions, and here we have what I said before many times, that the currently available devices are noisy and small. And in contrast, the simulation of large qubit systems is very computationally expensive and slow. And at this point, it is hard to test quantum machine learning models because of we do not have real quantum computers that are capable of running any kind of quantum machine learning algorithm, but we also don't have the right classical computational performance to simulate anything what we want. Another question is how to guess the ansatz circuit, the initial structure of the quantum circuit. It is a non-trivial question. How do we do it? It is rather ad hoc. You just came up with an idea and test it, and if it doesn't work, you test another. So it's like buying a lottery ticket. Another question is that can we prove that quantum machine learning is better than machine learning? The problem with machine learning is that very few algorithms can be proven that give the right answer. For example, when we classify dogs and cats, we cannot prove that our convolutional network will always give the right answer. However, we can test that, for example, 99% gives the right answer and 1% it gives the wrong answer. And this is the same with quantum machine learning. We cannot prove that quantum machine learning algorithms will give the right answer, but we cannot prove either that it will perform better than machine learning algorithms in all cases. So it is a matter of experimentation. We can empirically conclude whether they perform better or not. And another question is, at least for me myself, that classical machine learning relies heavily on nonlinearities between the linear layers, but quantum layers are only linear. So you cannot produce a nonlinear layer in a quantum computer because quantum circuits are unitary and unitary matrices are linear. The only way you can produce nonlinearity is by measuring something. So my question is that should we find a way to add nonlinearities into these quantum machine learning models, for example, by partially measuring the circuit, or not, or this is good as it is. So okay. So these are the open questions. If anyone has further questions, I will try to answer it. And thank you for your attention. And you can contact me on this email address.
Interesting topic, but let's see if someone has something. No? Okay, maybe I make a quick question, but I want a quick answer. So what's exactly the next step with your studies?
In my studies?
In this project.
So can you ask it again, please?
So what's the next step in this research project? What you are aiming to do as the next step?
I am currently working on reinforcement learning, and I am investigating how can we use reinforcement learning and quantum assisted reinforcement learning. For example, an agent that is boosted by a quantum layer, or another approach would be, can we use reinforcement learning, classical reinforcement learning, to improve our quantum algorithms or quantum computers. So I mostly work with reinforcement learning, and that is my choice of further research.
Okay, so good luck. Thank you very much, and let's call the next speaker, who is Karol Kubicku, and he will make a presentation here. So I'm switching over to this direction.
Please go over there. Okay. Okay, the next speaker is Karol Kubiczko, and let me make this title quickly. So, quantum chemical investigation on the metabolism of the endogenous psychedelic dimethyltryptamine molecule by a monoamine oxidase A and C. I can get the prize for this. So do you have, is it ready now? How noisy. Tudjuk ilyet csinálni, vagy említeni? Tudjuk azt is, hogy itt persze. Jó. Akkor nem tudom, akkor csícs be ide, és akkor ilyen. De nem azt, hanem most éppen csak a Firefox-on megosztva, és nem találom, hogy hogy. Ez is ezeken, de most te látjuk. We are sorry for the technical difficulties. Many systems
several connections and
Miért a böngészőbe? Mert a böngészőt vetítettem ki. Teljesen észre. Nem a Zoomból csak a Firefox-on jelen pillanat kivetítve, semmi más. És nem akartam nyomni a kontrollpanelje a Firefoxnak. Hát, osztja. Szoktam már ennyire a Firefox-tól. Megvan a kinti videója. Jó. És kéne kitalálni itt. Megvan. Igen.
so we have the slides. We can also see Ragor. I hope we can see you. So what happened? Don't touch the system. So you're giving the presentation now. So okay, we have this. Okay. Okay, you can come over for this area of community. Oda rakjuk ki. Ne rakd most ki, menj formális, mindenki nézi.
Okay, so I welcome the audience, and I'm proud to be here and represent our results. At first, I will do some very brief introduction of the choice of the topic. Then I discuss some of our results, and then I make some conclusions. And the last part is the proposal for future investigation. So we start with the Born-Oppenheimer approximation. There's a time-independent Schrödinger equation. Using that approximation, the electronic and nuclei, the motion of electronic and nuclei problem can be solved. Separately. In our work, we focus on the electronic problem. DFT methods, density functional methods, can be used for large systems. Enzymes are large-scale systems, so if one should use DFT methods, it doesn't work. It will not work. The size of the system is too large, maybe thousands of atoms. So the question is, what can we do? There are some QMMM methods, such as Onion, which combining other levels of theory, divide the system in 2 or more parts. The most important atoms are created in QM theory.
No, azt ki van kapcsolva.
Okay, so I said the Onion approach, which combines other levels of theory. We can divide the system in 2 or more parts. The most important part of the enzyme, such as the substrate and the reacting center of the enzyme, are created in quantum mechanically description. The rest of the system is created by, for example, molecular mechanics, classical force fields, which are really cheap compared to the QM levels. So some aspects of the potential energy surface, searching chemically relevant species like reactants, transition states, maybe there are some intermediates and products. In quantum chemistry, this corresponds to finding critical points of the potential energy surface. Local minima points correspond to the reactants, intermediates, product, while the transition states is first order saddle points between 2 minima. One of the most important part of determining chemically relevant data, such as activation energy barriers or activation Gibbs free energy barriers, and the corresponding reaction rate constant. The lowest lowest reaction constant is the rate determining corresponds to the rate determining step of the reaction, which has the highest activation Gibbs free energy. Some details of the choice of the system. The enzyme is the monoamine oxidase. It has 2 isoforms. In this project, we focus on the A type. There's another form, MoB. They are shares about 70% of structural identity. Mo enzymes are important because they regulate the levels of neurotransmitters in the brain, and the other choice is the ligand, which were the N,N-dimethyltryptamine and its primary amine analog, the tryptamine. DMT is important. It's an interesting compound because many people may have heard about the very powerful psychedelic substance. It's usually regarded as the spirit molecule, and it may have therapeutic potentials. In addition, which makes the whole thing more interesting, the human body contains DMT in trace levels, and it also can be found in plants. It has proven that DMT has a role in immunity, tissue protection, and inflammatory responses as well. So it's a very interesting substrate. So this scheme represents how monoamine oxidase enzyme works. We focused on the right side, where the flavin adenine dinucleotide cofactor of the enzyme is reduced to quinone or hydroquinone form. Then the other step is the flavin is reoxidized by by molecular oxygen, producing hydrogen peroxide. So some of our results, we calculated the estimated distribution of DMT and tryptamine substrates, and we found that the protonated form TH plus or DMTH plus is the most abundant in the body pH and body temperature. So these protonated substrates should be conserved in mechanistic aspects. Okay, so there are many scenarios in the literature has been suggested for the mechanistic description of how monoamine oxidase work. In the first 2 rows, there are literature mechanism for primary amines. In the first row, in the first row, one can see that the amine lone pair attacks this carbon atom, and the nitrogen abstract proton from the substrate, and by this the flovin get the reduced form. The another suggested scenario is that the flovin ring may not accept a proton. It also can accept a hydridion, and the next step is so in the next step there's an adduct formation, and by two H2O molecules, the proton from the amine can go to the flovin NH atom, and thereby we get the neutral imine form of the substrate and the full reduced hydroquinone form of the enzyme. So I speak about our proposed scenario, which is similar to this one. Just the difference is that we suppose that it may be possible that a protonated substrate, because of the ratio in the body, a protonated substrate enters the active site of the enzyme, and this proton exchange happens prior to the enzymatic reaction, and then the flovin ring becomes positively charged, and then hydrodion transfer mechanism can be accelerated so much. This is so this graph shows our results. This is the reference point, the reactants, and one can see that the usual form of the coenzyme, the neutral fat, has activation barriers for the tryptamine and dimethyltryptamine. And if we suppose that FAD-H plus is a possible form, then one can see that the activation Gibbs free energy barriers are reduced in about 2-4. So these new activation barriers are nearly 2-fold decrease compared to the neutral fat form, which makes very interesting this FAD-H plus of the coenzyme, and we suggest further studies to evaluate can this could this FAD-H plus coenzyme could this FAD-H plus coenzyme form before the hydrid transfer reaction. So now we make some conclusions of the results in both coenzymes, Fed and Fed-H+. The activation GIPS-free energies is lower for dimethyltryptamine than tryptamine, which the reason behind this phenomena made that the hyperconjugation effect of the methyl groups on amine nitrogen. The other results that this novel Fed-H+ cofactor decreases the activation barrier for tryptamine and dimethyltryptamine as well. For tryptamine, the decrease is 38 kilocalories per mole and 11 kilocalories per mole for dimethyltryptamine. So, as I said before, our suggested new Fed-H+ coenzyme nearly decreases the activation GIPS-free energies by 2-folds compared to the usual fadinidine dinucleotide cofactor. We made some proposals for future investigations. As I said before, one should elucidate the possibility of Fed-H+ formation. Maybe that the protonated substrate somehow can bring the positive charge via H2O molecules to the flavin edge atom here, and we made efforts to examine this process, but they are results in very expensive calculations, because the water molecules should be in a high layer, which is described by quantum mechanics theory. This is important because of the cleavage of bonds and the formation of bonds, best described in quantum mechanically methods. Other interesting questions is what is the final product of monoamine oxidase catalyzed oxidation of amines. For positively charged iminium cation, so just a minute. Positively charged iminium cation only forms in reactions by tertiary amines such as DMT, because it's the only possibility, since tertiary amines don't have any mobile protons on each amine nitrogen. The neutral imine or iminium cation is another question. Our results reveal that for the primary tryptamine substrate, it depends on the substrate. So the Fed and FedH plus form of the coenzyme. In the former case, with Fed, as shown before, neutral form of imine can be result. So the reaction can result in neutral imine instead of positively charged iminium cation. In the latter case, FedH plus results in iminium species are the only option if we concern primary amines. So thank you very much for your attention, and I hope that you enjoyed the presentation.
Thank you very much, Carol. So time for questions. I think it's anybody getting so tired. I would have a question. So how much speed up could you gain from the CPU, GPU thing, and what? Yeah, basically.
Yes, the most so in geometry optimizations is the goal that finding local minima or transition state structures. The most expensive part of this optimization technique is maybe the Hessian calculation. So, which means that we suppose that the potential energy surface is quadratic. For transition state computations, calculate the Hessian matrix, which is very, very expensive. So it depends on the computer. It can last weeks for big systems like, for example, this monominoxidil system. And this is a very high cost part of the optimization techniques. We found that in many cases, so the Hessian should be computed in each optimization step, not only the first, in each reaction step, which makes a huge computational effort, but using that Hessian calculation in each step can reduce the optimization step, and one can lead. So this usually led in better convergence, and instead of not using this Hessian approach, the optimization cycles is about 300 or more. But if one use this Hessian calculation in each step, the step of reaching the convergence, the stationary bound, maybe in 5 or 10 steps is possible.
Okay, so thank you very much, and thank you for the talk. So let's go further to the last talk of this day. We are very, very much late. So I ask Tamás Nagy to...
Yes, here I am.
Excellently. Switching. Can you share your slides?
Yes, I'm trying. Okay. So
I give you the stage.
Okay. Thank you very much, and welcome everyone. I'm Tamás Nagy, and during my master's thesis, Tamás Hegedűs was my supervisor, and we were working with transmembrane proteins, and we ran molecular dynamic simulations to better understand their dynamic behavior. And at this point, you may ask what and why. And well, cells in your body have membranes, and they metabolize. And the membranes separate the intracellular space from the outside environment. And during metabolization, the cell should carefully consider what goes through its membrane. So there are many ways of this transport could take place, but the two main categories are, the first is passive transport, which means that the substrate goes along its electrochemical gradient. And the second one is active transport, in which case some energy is required to move the substrate against its electrochemical gradient. And this energy can come from ATP hydrolysis. And ABC proteins are a good example for this kind of transport, where ABC stands for ATP binding cassette, and this is basically a super family of proteins. And inside this super family, you can find ABCG2, which is the second member of the G subfamily. And this protein is responsible for many functions in the body. And an important one is the multi-drug transport, which means that it exports a wide variety of cytotoxic molecules from inside the cell into the extracellular space. And this behavior helps defending the brain, the embryo, and the newborn children, because it is expressed in the blood-brain barrier, the placenta, and the breast. But this ability can be detrimental too, because cancer cells can develop multi-drug resistance, and which means that the drug concentration is lowered in the cell, and this hinders the effect of chemotherapy. And then other function is uric acid transport, and the specific mutation of G2 makes it unable to transport uric acid, and thus uric acid concentration will rise in the blood, and it can lead to gout, or Köszve in Hungarian. So here's the structure of ABCG2. The functional structure of the protein consists of two polypeptide chains, which two protomers that together form a homodimer. And here you can see two different conformations for this specific protein. On the left side, the invert open conformation, which enables the substrate to enter the protein and allows ATP to bind. On the right side, you can see the closed conformation, which occurs while substrate exits into the extracellular space. In green, you can see the nucleotide binding domains, NBDs. And as their name implies, they are responsible for ATP binding and also other tasks. And in gray, you can see the transmembrane domains, which are forming the translocation pathway across the membrane. So inside the transmembrane domains, we have site 3, or the main binding pocket. This location is targeted by many studies, and it plays a key role in substrate recognition. So along the path leading to site 3, we suspect the existence of site 2 on both sides, and which may act as a preceding filter to substrate recognition. And even though we have these structures, we know little about the dynamics of the transport mechanism and substrate recognition. So to discuss this further, I'd like to propose an analogy to the basic dynamics of the process. So here you can see a canal lock where the shift corresponds to our substrate that we want to move out from the cell. And as it enters the binding pocket here, it hydrolyzes ATP, the conformation of the protein changes, it becomes closed, and the energy level rises. And the substrate, or ship, is released into the extracellular space. Okay, and at this point you may ask, all right, but why are you here? And well, we are investigating organic macromolecules, and we want to observe their dynamic behavior on atomic level resolution. So most experimental methods are not suitable for this kind of observations because, for example, the cutting-edge cryo-electron microscopy only creates static images because the protein is frozen. So, but we want to learn about the dynamics. And for this, we are running molecular and dynamic simulations. So here you can see one of our systems, simulation systems, which contains some water, the extra and intracellular space, separated by the membrane in green, and you can barely see our protein in blue. And this system consists about 200,000 atoms, and the computer solves Newton's equations of motion. But it takes a lot of time because of the many atoms and the many interactions. So actually, 500 nanosecond simulation took 3 weeks with 4 high-end GPUs. And during these simulations, after every other step, we write the state of the system into the disk. So we end up with a trajectory containing all the coordinates at the given time. And this is the data that we can analyze. So here you can see a movie from this trajectory. All right. So we have existing experimental data about the regulatory effects of cholesterol. Basically, the cholesterol presence in the membrane increases the activity of ABCG2, but the exact mechanism of this activation was not known. So to gather more insight, we run molecular dynamic simulations for cholesterol-containing membranes and membranes without cholesterol for simulation for each case. And on the following diagram, you will see that the locations of the intracellular ends of the helices in the membrane. As you can see from this little picture. And here, each cross corresponds to the initial position of one helix end. And the top diagram shows the cholesterol-containing membranes, and the bottom one is for simulations without cholesterol. And then this heat map shows how frequent was a given coordinate during the time span of the simulation. So a brighter red color means that the helix ends spent more time at a given location. And what we observed is that in case of the simulations with cholesterol, some central helices were much more likely to close. These helices are marked with a red cross, the initial position. And to quantify the results, we plotted the distance between these two central helices. And then this is what you can see on the right side. As you can see, in the case of cholesterol, the central helices were much more prone to close. Then the distance was much more likely to decrease between time, as the time increased. And in contrast with the membranes without cholesterol at the bottom, where we can see they were even opening in some cases. So we concluded that cholesterol exerts its regulatory effect by helping the structure to close. And to allude back to the canal lock analogy with the ship, cholesterol basically acts like a grease that helps the closing of the gates. After that, we ran simulations with uric acid molecules around to observe the interactions with the protein. And during one of these simulations, the uric acid entered the protein. And on the figure, you can see the initial conformation of the protein, but it's important to note that it's not stationary during the simulation. It's moving, but it's only for visibility. And it interacted with some amino acids at site 2, and then went on the translocational pathway as the time increased, and it reached the main binding pocket, or site 3, but it wasn't able to go through into the extracellular space because the energy barrier for this was too high. So then it moved towards site 2 of the other side, and that's where its journey ended. And the simulation gave us some key insights about the first part of the pathway, but to gather more information about the second half, we had to overcome the energy barrier. So for this, we used metadynamic simulations. And during metadynamic simulations, we define a reaction coordinate, for example, a distance between specific amino acids and the substrate. And then we monitor the value of this reaction coordinate. And if the system stays too much time the given reaction coordinate, we artificially increase the free energy level of the system at that point to make the system move. And you can see these steps on the right side of the image, on the right side, where the reaction coordinate is in the horizontal axis and the free energy level is on the vertical axis. So you can see that the system is trapped at the local energy minimum and moving it away. And this method is good because we can measure how much energy is needed to get over these energy barriers, and thus we can get information about the system. So we've run metadynamic simulations for the inverse closed conformation of the system, and we define the reaction coordinates as the distance between the substrate and some amino acids of the protein. And we've run 6 simulations with this system, and we were able to observe the substrate exiting into the extracellular space in all 6 cases by interacting at various locations along the way. And we also measured the energy requirement of the translocation, and in 3 cases out of 6, it was below the ATP hydrolysis energy level. So this implies that the results are realistic. So in summary, we determined the exact mechanism of cholesterol's laboratory effect, and our results show that it helps the closing of the protein structure. And we also determined key points, binding pockets along the translocational pathway involved in the substrate recognition. And as you can see, this kind of research requires a large amount of computing capacity. So I'd like to thank Wigner GPU Laboratory that they provided their GPU clusters to aid the research. And if you are interested in the topic, you can also read our recently published paper or visit hegelog.org. And I'd like to thank you for listening, and I'm here to answer your questions. Thank you.
And thank you for taking the time. Anybody outside or inside questions? Time is pretty much over. I would have a question in relation to the slide 13. So, I mean, you know, we are dealing with giga and tera electron volts, which are a bit larger energies in some sense. So, you said that on the middle of the figure, there is this number of simulation versus the free energy in kilocalorie per mole. So when you presented that you have this potential with a certain forms, so is this within the uncertain? So I mean, I cannot really get the energy range. Okay, so I see that between the different simulations, you have like 3-5 kilocalorie over mole energy difference. And is it in the order of kind of how do I say, uncertainty, or so this somehow was not clear for me. I know the question is kind of silly, but I didn't get this point.
So this is just for presentation purposes. It's a general graph or image.
Mm-hmm.
I said so. It's not related to our system. It's just to visualize what's happening during the multi-dynamic simulation in general.
Okay. Another question is we have heard several machine learning like or based studies today and even tomorrow. So don't you think to use such techniques could be order of magnitude higher result, produce much more faster results than the standard methods? Are such things available for these kind of problems?
Well, the problem is that to get our data, we had to calculate, so run the computers for a long time to get our basically raw data that we can analyze later on. And I think that machine learning algorithms work great when the data is plenty, I think.
Okay, anybody else? Okay, so thank you very much. Tomorrow we will have the continuation of the GPU Day, and don't forget this part which was advertised by Cindy. So the first part is mostly GPU machine learning. So we will start with Gabor with a Monte Carlo simulation, and István Hopp, which is a very, very important talk, not only important but interesting talk on this newly formed monoplasmonic laser fusion group, which is given large amount of governmental money recently, and a couple of astronomy talk, and then finally a closing comparison of very deep learning performance and GPUs and CPUs by Wigner. So please come with us tomorrow starting from 9 in the morning. Take care, and thank you very much, and all the speakers and all for the whole meetings. Okay. Köszönjük szépen.
Köszönjük szépen.